definition and identification methods. My name is Chao-Quing Lo from University of Texas at Arlington, Texas, USA. This is outlines of my talk. I will talk of first generation, second generation, new omega method, third generation, and Nutex, Nutex omega method, Nutex core-line method, and Nutex-based new fluid kinematics, and some conclusions. We know vortex is omnipresent in universe everywhere, like tornado, hurricane, turbulence, galaxy. However, do we have any mathematical definition for vortex? No. So there are 3 generations of vortex definition. The first generation is given by Helmholtz in 1858. His definition is mainly about vorticity tubes, vorticity filaments, etc. And then we have second generation, which are currently very popular for the vortex identification, like delta, Q, number CI, number 2 method, etc. Today I report is about the third generation, including omega, Nutex, Nutex omega, Nutex core-line methods, dated from 2016. First, we talk about the first generation of vortex identification. It is vorticity-based definition given by Helmholtz in 1858. He defined vorticity tubes, filaments as a vortex. However, can vorticity represent vortex? In general, no. Which has been proved by many scientific and engineering applications. Vortex is not vorticity filament of vorticity tube. Look at this earlier fluid transition. The green one is vortex. This section is in the middle of the flat plate. The color represented the vorticity strength. Red means strong, large in vorticity. Green, smaller, and blue is small. We found the vortex happen in the place where the vorticity is rather small, not large, not in the red area, in the green area. Robinson actually in 1989 found vortex happens where the vorticity is rather weak. We look at this vortex isosurface and the vorticity line. we will find the green tube are isosurface of vortex. The lines are vorticity line. So the vorticity is larger outside the vortex. Inside the vortex is rather small. Not only in the magnitude, also the direction is different. This is the vorticity direction, and that's the vortex direction. They are totally different. Therefore, we cannot use vorticity to represent vortex. They are both vectors, but are totally different vortex. Definition. We also look what is local rotation axis. We give the definition. A local fluid rotation axis is defined as a vector that can only have stretching or compression along its length. That means the vortex axis cannot rotate it. So this will give the dV. dV is the velocity increment. According to mathematics, it should be equal to gradient of vorticity dot R. R is the real eigenvector of the velocity gradient matrix. So this means dV only can along R. R is real eigenvector. Therefore, the real eigenvector is rotation axis. Well, this is nothing else but a Lutex. The Lutex, the definition is its real eigenvector of velocity gradient matrix. How about the vorticity? Well, that's the theorem. Vorticity is not local fluid rotation axis except for rigid rotation. It can be proved easily. Same thing along the vorticity vector. The dV is del V dot omega. Well, the gradient of velocity tensor can be decomposed to be A and B. We know B is antisymmetric. It's easily to prove is 0. R1, R2, R3 are eigenvector of A. So A R1 equal to lambda 1 R1, etc. We cannot take the lambda out. We cannot. Because lambda 1 is not equal to lambda 2, lambda 3. If we can take out unless lambda 1 equals 0, lambda 2 equals 0, and lambda 3 equal to lambda. In such a case, the fluid is pure rotation or rigid rotation. So in general, vorticity vector cannot be local rotation axis, where A and B are symmetric and antisymmetric submetrics. Since vorticity cannot be used to represent a vortex, there are quite a lot of vortex identification criteria developed in the past 4 decades. More popular ones are Q, delta, number 2, number CI, etc. Q, given by Hunt, 1988. Delta, Chong and Perry, 1990. Number 2, John and Hussein, 1995. Number CI, Zhu and Adrian, 1999. Well, we have problem with the second generation. First, they are all scalar, but the vortex is a vector. 2, physical meaning is not clear. What is Q? What is number 2? Etc. 3, they are all contaminated in some degree by stretching or shearing. 4, they require a threshold. Threshold is not unique, but some kind of arbitrary and man-made. Different threshold will give different vortex structure. For instance, even for same DNS data on the late boundary layer transition, if we pick large threshold of number 2, we get a vortex breakdown. However, if we pick the small threshold, all the vortex are linked. There's no breakdown. Look at these figures. When number 2 is negative, 0.017, all this vortex breaks down. However, if we reduce number 2 to close to 0, for example, 0.003, all these vortex are linked. There is no vortex breakdown. If we look at this movie, so we change the threshold, we get a totally different vortex structure. That means the vortex structure is determined by the threshold. Doesn't make much sense, not make much sense. Therefore, we try to develop a new vortex identification method we call it omega. Omega use A and B. We know that A is the symmetric part, B is the antisymmetric part, or we call the vorticity submetrics. So omega equal to B normal square divided A normal square plus B normal square. This is pretty much like a relative stress. Here we have a small number of epsilon to avoid the division by 0 or very small number. We give some empirical formula for the epsilon. Well, the omega method has some advantages. First, is easy to perform. Second, is normalized from 0 to 1. Third, is insensitive. We pick omega equal to 0.52, which can work well. When we change from 0.52 to 0.6, even 0.7, the vortex structure change very little. Four, they're also capable to capture both strong and weak vortices simultaneously. So we receive many reports saying omega method is better than any other second generation of vortex identification methods. It is really for the relative strength of the vortex. Now I introduce the new definition, Nutex, which is a mathematical definition of vortex. Nutex is a vector. The direction is the real eigenvector of the velocity gradient tensor. The magnitude is given by this formula, which is given by Dr. Wang and others in 2019. Dr. Wang is the chairman of this workshop. So, Nutex is a quantified vector which opens a new gate for quantified vortex and turbulence research, not only for quantitative research. Here, the omega is vorticity, or is real eigenvector of velocity gradient tensor, and lambda Ci, it is the imaginary part of the complex eigenvalue of the gradient of velocity tensor. Nutex is a mathematical definition of vortex because the Nutex direction is really the vortex rotation axis. Well, here is the real eigenvector of del V. And the magnitude is exactly twice the angular speed of the fluid rigid rotation. Therefore, the Nutex, it is mathematical definition for vortex. The major idea is to extract the rigid rotation from the velocity gradient tensor. Nutex was born in 2018 at the University of Texas at Arlington. People spent 160 years since Helmholtz, 1858, and finally found a mathematical definition for vortex. Since then, we have published 3 books about the Nutex, one by Bentham, the other by Elsewhere, and the third one by Springer. And we have published more than 40 SCI papers, most of them are highest cited. The Nutex and the Nutex dynamics is very important, since vortex exists everywhere in the universe. A mathematical definition of vortex or Nutex will play a critical role in countless scientific research areas. There is almost no place without vortex in fluid dynamics. The Nutex theory will be critical to research of hydrodynamics, aerodynamics, thermodynamics, oceanography, meteorology, metallurgy, civil engineering, astronomy, biology, etc. More important, it is critical to the turbulence research, turbulence generation, sustenance, modeling, and control. Since Nutex is the vector definition for vortex, so it directly can be used to show the vortex, not the vorticity. No, that's the vorticity line. And the blue one, the green one are vortex isosurface. You can see the blue one, a vorticity line, you see, they are not coincide. They are totally different directions. But look at the Nutex. They have same direction as the vortex structure. So Nutex can directly use to show the vortex structure. We know that velocity vector can show the streamline. Same thing, Nutex vector can show the Nutex line, Nutex 2, but not Q, number 2, etc. They cannot get any line since they are scalar. Vorticity tube is not vortex, but the Nutex tube is vortex. So we can see that the vorticity line is not vorticity line is not vortex, but Nutex line is. I would like to recommend some new methods. The first one is the Nutex omega method. The basic idea is Nutex can represent the rigid angular speed without shear contamination. It's a pure rotation. The omega can capture both strong and weak vortices. So we just try to combine Nutex and omega methods. How to do that? Well, it is the Cauchy-Stokes decomposition for the principal velocity gradient. So we can do the Cauchy-Stokes. Originally, omega method is b squared over b squared plus a squared, which really have a lot of shears. So for the modified Nutex omega, just take these shears out. So we only use the rotation, maybe some stretching. So this formula can get the explicit formula because we know the definition of R, beta, and alpha. Finally, we get omega R tilde equal to this formula. We can see we take out the shears. However, we still have a small number of epsilon which needed to be adjusted. On the other hand, the omega R, we pick 0.52. It works very well for a lot of cases. If you adjust a little bit of the threshold, it's changing very minor. So we say that's insensitive to threshold change. And that's the graphics we used to modify Mutex omega method for vortex structure in the bound nail transition. We can see they capture both weak and strong vortices. Yeah, like this is Tobin stitching wave of vortex. Well, this is the lambda vortex, and we are Harping vortices, and until we get more and more complicated. Then I also would like to introduce the Mutex core line definition and identification. The idea is that on any Mutex isosurface, the dr is 0, the isosurface, but dl is dr dot dl, which means dr, the gradient of Mutex, and dl, they are always orthogonal. The dot product is 0. However, the dr and dl are not orthogonal only if dl no more in the isosurface, dependent which is the rotation axis. Rotation axis is not isosurface. So we give the definition. What is rotation core? It is the line, the gradient of R, cross product with the Mutex is 0. That means the Mutex gradient is parallel to Mutex. The Mutex core line is unique and threshold free. We don't need any threshold. How to do that? So we need to first calculate the gradient of Mutex, this dr. Then we need to give definition of what I call. What I call is defined as a concentration of Mutex gradient vector. Or we say that's a local maxima of the Mutex. Then we need identification of what I call. Really, the method we just located the local maxima. See? Then we just draw the Mutex streamlines, the Nike streamline, to show what the core line. And look at this graphics. So if we draw the Mutex gradient lines, they're all concentrated on some lines, which apparently is the rotation axis. Where we can see from this graphic, they always locate inside the isosurface because they are local maxima. We take them out, we get the vortex rotation core line. We can see from here, they always inside the Mutex isosurface. Now we look at the Mutex core line for boundary layer transition. All kind of vortex identification method depend on the thresholds. Different thresholds will give different vortex structures. There's no proper or improper thresholds. No one knows. the Newton's core center is uniquely determined, which represents the vortex rotation center or axis. The Newton's core center lines give the unique and correct vortex structure with strength of vortex and are threshold free. So we look at some examples. First, we only need to find local maxima points, these local maximum points. These maximum points will give the Newton streamlines. That's Newton streamlines. With the strength, it's not threshold. The threshold give isosurface. So the red one means strong. The yellow one, a little bit less. Green one, smaller. And the blue one is very small. So we can find the Newton's core lines with different color to represent the different strengths. For the earlier transition, we have lambda vortex. We can take these core lines out. Well, we can also find it. This core lines is inside the isosurface. This little lid, this is only for the Newton's core line. This is Newton's core line and isosurface. This even later, we have a lot of vortices. We can find the vortex lines. Also, the vortex line will be inside of the isosurface. Again, this is just the the core line and the isosurface from different angles from top. So the conclusion of the numerical results are the Newton's core line is the best vortex identification method for several reasons. First, the Newton core line is the only method that gives a unique vortex structure, which is threshold free, not the others. Second, they shows the strength of the vortex by the color. Third, they also show the direction of the vortex. We can look at these graphics and movies. We can see when you change the isosurface, you will see that the isosurface will be gone, but the water core line is never changed. Also, the Newton's core line also can show the rotation axis direction. We can find it. What is the rotation direction, but not for the Q or lambda to lambda Ci. No, but the Newton's core line. We can compare with the Q method. Well, we know Q method is threshold dependent. This is the smaller threshold, 0.005. You get a more structure. If you use large Q, you get a much less vortex structure. But anyway, for this area, we can find it, or that area, where we have a lot of vortex structures by Newton's core lines. But we find little when the threshold is small, we have nothing when the threshold is larger. But this structure never changed because they don't need a threshold. So this is unique. Apparently, a lot of vertex structure is lost if we use the Q method or other second generation of vertex identification method. For the other example, is about the same. You see? So we can, when the Q is small, we can get some structure. Yeah, but Q large is not all structure. But look at the Nutex colline, a lot of structures, which Q and other second generation method cannot capture. Now we come back to the Cauchy-Stokes tensor decomposition, where we know that the velocity gradient tensor can be decomposed to be symmetric. They call it strain rate, and the B is they call the vorticity. A is symmetric and B is anti-symmetric. But people usually think B is for the rotation, but no, we cannot say that. So the problem with the Cauchy-Stokes decomposition is the vorticity cannot represent the fluid rotation. The vorticity tensor really is a mixture of vorticity, shear, and rigid rotation. For the strain rate tensor is symmetric, but they have a diagonal element. People think that's the stretching, and long diagonal elements, they think the symmetric strain. Apparently, it's a mixture. It depends on the coordinates. So the CS decomposition is dependent on the coordinate system, and therefore it's not Gaussian invariant. So we introduce the principal coordinate system and get the principal matrix. Well, the tensor is unique, but the matrix is not unique. It depends on the coordinates. We call principal coordinates. And this means the z direction is parallel to Nutex, and xy direction are orthogonal to Nutex. So in these coordinates, we get a principal matrix. Because the tensor is unique, the matrices are not unique. So we need to give a principal matrix. It's like this, or it's Nutex. Lambda CR are real part of the velocity gradient tensor. And lambda R, it is the real eigenvalue of the velocity gradient tensor. And epsilon, Xi, and eta are shares. So in this principal coordinates, we get this we call principal matrix. It's very easy to decompose to be three parts. One is we call the rotation, the rigid rotation. The second is stretching or compression. The third one is shear. So we call R, SC, and S. Well, I need to explain that some people also have similar idea as our principal coordinates. However, in the principal coordinates, different points have different principal coordinates. So we cannot use we must go back to the original X, Y, Z coordinate system. Otherwise, we cannot do the derivatives, the integration, we cannot do. Because we already rotated the originally coordinates, we must rotate them back by Q and P transform. In the principle, coordinates, we have three parts, R, S, and SC. But now we come back, we get R tilde, S tilde, and SC tilde, representing rotation, shear, and stretching. Well, the rotation part is easy because this mutex is gardening invariant. The SC part, we also can find it. It is, they have two parts. One is a diagonal matrix. The other one is dominant by mutex. Of course, if for laminar, for example, laminar boundary layer, the mutex 0, we just 0. S tilde is too long to show here. So if you're interested, you can see our paper, New Fluid Kinematics, published by Journal of Hydrodynamics. Here, we must emphasize the vorticity is not rotation. The vorticity must be decomposed two parts, mutex and shear, rotation part and non-rotation part. This is very easy to prove that because B is anti-symmetrical part can be decomposed rigid rotation and the shear. Therefore, so we can decompose the vorticity to be the two parts, R and S, or we call vorticity RS decomposition. Well, this decomposition is easy to do for different coordinates. Since R, S, and vorticity are gardening invariant, it's not related to coordinates. We look at this. That's the earlier fluid transition. In the lambda vortex, we pick one point to check what is vorticity, this red one, is large. What is the mutex, the rotation? It is small. So the major part of the vorticity are shear, not rotation. So vorticity is not a rotation. The magnitude is very different. Of course, the direction is totally different. We cannot say vorticity is flow rotation. No. We pick another point on the ring part of the helping vortex. We find a similar thing. The vorticity is large. The rotation is small. They are in different directions. So we also we called Uta Rnr Tensor Decomposition. So the velocity gradient tensor can be decomposed in two parts, R and Nr. R means rigid rotation, Nr means no rotation. It is also easy to be done in any coordinates, in original coordinates, since the mutex, it is gardening invariant. It is not related to the coordinate. We need to list some core issues on the vortex definition identification. We know vortex is a natural phenomenon. vorticity, of course, is a mathematical definition. So we try to find the vortex. There is some issues. One is, what is absolute strength of the vortex? What is the nutex? Nutex is double, twice of the angular speed. Then what is relative strength of vortex? It's omega. Omega is relative strength. Then what is the local rotation axis? This is nutex vector. Where is the vortex core center? That's some nutex core lines. Then what is the size of vortex core? Well, this is still empirical. Now we pick 95% of the central nutex stress. Where is the vortex boundary? Say nutex greater than 0. Well, all these 6 questions can be answered by the third generation of the vortex identification method, not by first generation, not by second generation. Second generation can answer some questions about where is the vortex boundary roughly when the threshold is small. We have a table here to show what we can do by the third generation of vortex identification. We can find it for all these key issues. Only nutex and nutex omega can answer these questions. All the first order, second order cannot answer. They maybe can answer some questions about the vortex boundary when the threshold is very small. Finally, I give some conclusions. First, vorticity cannot be used to represent vortex. Second generation methods are all scalars, strongly threshold dependent and shear contaminant. They are not either. 3. Nutex is the unique mathematical definition for fluid rotation of vortex. 4. The third generation can give answers on 6 key issues of vortex, including the vortex core. Number 5. Nutex and the third generation open a new era for quantified research on vortex science and turbulence, as vortex is the building blocks and muscles of the turbulence. The nutex based on vorticity nutex shear decomposition. That's the vorticity RS decomposition and the UTA Rnr Tensor Decomposition paved the foundation for the new fluid kinematics. So what is contributions by UTA team? So first, mathematical definition, nutex. The direction, it is the real eigenvector of the velocity gradient tensor. And the magnitude we know is twice the angular speed of the local fluids motion, including existence, uniqueness, stability, etc. 2. Principal coordinates and principal decomposition in both principal coordinates and original x, y, z correlate system. Uta Rnr velocity gradient tensor decomposition. Or we say del V equal to R plus Rnr. Then there are several methods, mutex-based vortex core definition and identification. Really, the vortex concentration of the del R, not vorticity, that's the local maxima of mutex, which is unique and threshold-free. Then we also give the new omega method and modify mutex omega vortex identification methods. We further create the new fluid kinematics, where we are developing the new fluid dynamics. We also develop a number of fortune code for the mutex method and modify mutex omega method and omega method. And this code have been published in the UTA website, so you can download free from this website. This is some of our recent publications. As I said, we already published 3 books and over 40 SCI papers. Now, let me see some movies for the fluid transition on the boundary layer. This is from side view. We can see lambda vortex, hairpin vortex, ring generation, and they lose symmetric, become chaotic breakdown. Let me see next. This from the other angle from top. We can see the lambda vortex, hairpin vortex with ring generation and lose the symmetry, become chaotic, the vortex breakdown. Thank you for your patience. Any questions?
Yeah, thank you for the wonderful presentation, Dr. Liu. And now the stage is...
Yeah, I'm here. Yeah.
Yes, yes.
Any question? Yeah. Any questions? No question?
Yes, Dr. Long, you can unmute your mic and ask your questions.
Yeah, if no question, and then they also can ask in the workshop. But I think we are past the time. Maybe it's a good time for the next speak, I think, yeah. The host?
Yes,
yeah.
sir.
Host, yeah. Any question? If no question, you may just go to the next because we passed the time already. Yeah, because of the technical problem.
Once again, thank you for being part in the webinar, sir. Hope you will associate with our future events as well. Thank you so much, Dr. Liu.
Thank you. Yeah, thank you for support. Okay.
So now moving on to the next presentation by Francis Bennett, and he's from Australian National University, and going to presenting on laser communications between space and ground at the Australian National University. So Dr. Francis. Yes.
Thank you. Can you see? That might be the wrong screen. Which one are you seeing here?
Yes, yes, it is visible. You can proceed with your presentation, sir.
Yep. Do you see the full presentation or do you see the presenter mode? I'm not sure.
Yes, yes, I can see the full presentation.
Oops. Okay, so you can see my full screen, okay?
Yes, sir. Proceed.
Thank you. So I'm Francis Bennett from the Australian National University at the Research School of Astronomy and Astrophysics. So I'm going to talk to you today about what we're doing with laser communication systems. So satellite communications permeate our daily lives in everything we do, from predicting weather, from moving data around the globe, to watching TV, space weather to look after our satellites, also space situational awareness to keep those satellites safe. There's a lot of research. There's human habitants in orbit as well. There's exploration of other planets. There are defense applications. There are naval and aviation tracking as well, all done from space. All the communications, well, the majority of communications are enabled through radio frequency bands. These all have to be licensed, and there are license fees which apply for each of the countries where you want to communicate to from space. And those fees can be relatively small to relatively large. There's also a very limited number of frequencies that are available. So this figure shows an illustration of the frequency allocation for the United States. You can see it's absolutely full of all sorts of things. And there's an increasing problem. We have more and more satellites going up into orbit. So there are mega constellations going up around the world. Starlink SpaceX is one of those. They'll be launching thousands of 200 kilo satellites into low Earth orbit to encompass the world for global connectivity. Each of the satellites has an inter-satellite link so they can talk to each other, and they can talk to ground stations, fixed ground stations, and the antenna on your roof as well. They have very low latency because they have quite short path lengths between your terminal, your antenna on your roof, and the nearest fixed ground station, which can then go to a traditional fiber-based communication network. So the issue with launching more and more satellites is that you are starting to remove all of the spectrum that was otherwise available. All of the spectrum is now very congested, and it's very difficult to get what you need. So laser communications is a solution to this. You can use lasers themselves to transmit data. You have a lot of the same physics applies, but with much higher frequency or shorter wavelength. You can take advantage of different things. And curiosity is that for radio waves, you can measure both their phase and their amplitude directly, but you can't for lasers. The wavelength is just too small. There's no way to get a resonant antenna, at least efficiently. You can do it in some special circumstances. Reflections and refractions are relatively simple for lasers compared to radio frequency because the scattering is so much smaller, and any object that it encounters is really going to scatter rather than diffract or refract, as is the case with radio frequency. However, there are some downsides to using laser communications through the atmosphere. The atmosphere itself can distort the laser signals propagating through it. There's optical turbulence. If you look at stars in the night, they twinkle. That's turbulence in the atmosphere causing that to happen. You have issues with transmission through cloud, where that really impacts how much light you can get through just because you're blocked from sending the light. There are some other advantages. You have a lot less power needed to send an equivalent data rate. Lasers are very efficient in how they use any electrical power that you give them. And the lower divergence of the shorter wavelength means that you can transmit that power over a much longer distance. So you can get the equivalent data rate out of a much smaller antenna. So a 70-meter RF antenna could be replaced with a 70-centimeter optical telescope for some deep space communication applications. So at the ANU, we have multiple research themes in our program. We're building and researching optical ground stations. We have a very long and diverse history in adaptive optics, including astronomical instrumentations for some of the largest telescopes around the world. We have a lot of site testing expertise, and that includes channel modeling and link budget for laser communications. We're applying these to deep space communications, quantum communications, and network operations. So the ground station that we're building at the moment is an off-the-shelf telescope. It's a 70-centimeter plane wave telescope. It's really an advanced optical ground station. It has both Naismith and Coude path availability for instruments, and this means that we can have multiple instruments on the telescope at the same time and switch out instruments relatively easily, so visitors can come and use their hardware to do some testing without needing to support a huge amount of infrastructure. We have a lower floor, which is a thermally controlled room where the light from the Coude path will come. And that room will support multiple experiments installed simultaneously. The telescope itself is optimized for high throughput and low loss scenarios, such as deep space and quantum communications, where you really need to make the most of all of the light that you actually detect. We are currently building the facility and should be receiving the telescope early next year and have it up and running after the middle of 2022. This is just another image of the facility itself. So in the upper level is the telescope. Then the Coude path is an optical path where light gets transmitted down the tube in the center of the building. And then at the base of that tube, there's a mirror which can send it out one of the ports onto an optical bench. And that room downstairs where we have 4 optical benches is where we can house some really sensitive experiments, because we can control the environment and the temperature so that we can make sure that all of the optics stay stable and clean, and that we don't have any thermal drift, which allows us to build more precise instruments. ANU itself has a lot of expertise in adaptive optics. This is an image of an adaptive optics system for a 1-meter telescope, which was used to do satellite imaging, so for space situational awareness. Adaptive optics itself is used to compensate for atmospheric turbulence and improve the performance of an optical system. We've done this for satellite imaging, for space debris characterization and tracking, including laser applications. We've done adaptive optics for astronomical instruments, such as the Gemini telescopes and the Giant Magellan telescope, currently under construction in Chile. We've done adaptive optics for optical communications, including space-to-ground, horizontal, and quantum applications. The key to the adaptive optics system is the deformable mirror. That is a mirror which can change its shape to match the distorted wavefront coming through the atmosphere. You measure those distortions with a wavefront sensor, and you have a control computer and a feedback loop to control the shape of the deformable mirror to provide your corrected beam. So on the upper right image there, image A you see is without adaptive optics, and then B is with adaptive optics. So what it does, it allows you to concentrate all of your light in a very small area, so you have a much better signal to noise. And on the lower right, there's an image taken of one of the Swarm C satellites, and that's showing that you can start to resolve features, you can see orientation, and if you look at this over time, you can see how it actually is oriented as it orbits the Earth. This is really important for any space debris programs where you're trying to capture the piece and bring it back to Earth, because you need to know how fast it's tumbling so you can catch it. This is an image of an adaptive optics system for horizontal quantum communication. So the electronics in the foreground is doing high precision frequency transfer, and the image on the right is an image of the graphic user interface that we use to control the adaptive optics system. So the spots there are from the wavefront sensor, and the position of those spots tells you the shape of the wavefront and what the deformable mirror needs to do to correct for the atmospheric turbulence. And the sort of green and red image towards the right there shows the current shape of the deformable mirror to optimize the wavefront for your situation. And this is dynamic. For site testing, it's really important to know the actual characteristics, the atmospheric characteristics of each particular site, so you can design and construct your adaptive optics system to match it. There are statistical atmospheric conditions which you can characterize, and a system that we have developed is called the stereo SIDAR. SIDAR is a scintillation detection and ranging system, and it actually gives you a three-dimensional turbulence profile. So you can actually measure not only how strong the turbulence is, but where the individual layers are. So what you do is you have a binary star system where there are two stars very closely separated, and you image those in the pupil plane rather than the image plane of the telescope. So you're basically taking an image of the primary mirror of the telescope. And when you do this, what you will see is an intensity variation where you see the pupil images, they're sort of speckly pattern. And this is actually intensity variation caused by the atmospheric turbulence itself. And what you can do is you can, because you have two stars moving through slightly different sets of atmosphere, you can correlate those two images. And where you have strong correlation, you know that you have a piece of turbulence, and how far those correlated pieces are apart tells you about the range, so the altitude of that turbulent layer. You can also do temporal correlation, where you correlate multiple images over time of these, and you can see how that layer evolves over time. So we achieved this design using a roof prism to increase the separation between the double stars, and we can actually form both pupil images on a single detector, which is quite challenging and unique. It's another kind of sensor that we're developing called rings, and that's a very much more compact turbulence profiler. This SIDAR system, you need a 1 meter telescope for it to operate efficiently, whereas the rings you can get away with a 30 centimeter telescope. So they're much, much cheaper. You can deploy them to more locations. It's also really important to understand optical propagation and channel modeling through these turbulent media. And so we have programs looking at these as well. Those then feed into your link budget, so how many photons you're going to receive at your detector, and include your adaptive optics correction and any fiber coupling or detector efficiencies you may have after that. One of the areas that we're looking at in detail is for deep space laser communication. The 70 centimeter telescope pictured here that we have is compatible with several planned missions. We have a currently funded project under the Australian Space Agency Moon to Mars program, which is to prototype an optical transmitter for lunar communications. The next step after this will be to build the full detector and transmitter system that we can equip on this telescope. And we'll be then able to talk to some of the NASA Artemis missions, which will be carrying not only crew back to the moon, but also laser communication terminals. And you also operate Siding Spring Observatory, which houses a 2.3 and a 4 meter telescopes. And these are available that we could get time on these to actually do even more deep space communications. There is another NASA mission going to the Psyche asteroid just beyond Mars orbit. And they will also have a laser communication terminal we can do some experimentation with. There are several sites around Australia that are going to be equipped with optical ground stations. We have one at ANU on the east coast, and there's another one at University of Western Australia on the west coast. This is a baseline of several thousand kilometres. We are looking at how we can network these and other telescopes, which are also in development, to create the Australasian Optical Ground Station Network. We would include this with New Zealand, and we're looking for other partners to join so that we can deploy more optical ground stations and have wider coverage. Even with these 2 ground stations, you get very good coverage here. So the green circles show when you would actually be doing your communications. So we only need 1 in between to be able to achieve constant communications over a very large area. Where we have the telescopes themselves are funded and under construction currently, and we're looking for funding to apply the network infrastructure itself. The network itself will be a platform for research and development. So not only for individual ground stations, but also for networking infrastructure. So how do you hand over between different optical ground stations? How do you optimize for cloud coverage so that you can make sure that you get the most data from your satellite in the most efficient way? As a bit of a wrap up, I don't expect people to be able to read this diagram. It's quite small. There is a link below if you're interested. But what I wanted to show with this slide is that the Australian Space Agency, which is newly formed, has a roadmap for advanced communications within Australia. There are a couple of the segments that I've highlighted here with stars where we have projects fitting into each of these. So in terms of the optical ground station segment, we are building a ground station and developing a network, and we're going to be demonstrating deep space communications. We have another project with looking at tactical RF optical hybrid terminals. We combine both a laser and radio frequency communication terminal in one compact system, which you can move around quite easily. Down the bottom, we also have a lot of quantum communication expertise. I haven't covered that here, but ANU itself has some world-leading technology and research in the fields of quantum key distribution and quantum memories. And both of these we're applying to space-based applications, whereby we can not only provide quantum secure encryption between a satellite and a ground station, but we can also look at providing a global network of quantum communication and encryption. So you can transmit data between very remote locations on the Earth within a reasonably short amount of time, say 1 orbit, maybe 45 minutes. And you don't have to actually trust the satellite itself to not read your information. You use the laws of quantum mechanics to actually make sure that encryption is valid end to end. And that's all I have. Thank you very much. I'm happy to take any questions.
Thank you for the wonderful presentation, Dr. Francis. And now the stage is open for questions. Having any questions from the speakers, you can ask to Dr. Francis. Okay, Dr. Francis, I assume that there are no questions from the speakers. Okay, so once again, thank you for being part in our webinar. Hope you will associate with our further events as well. Thank you so much. And now the next presentation will be by Uta Rnr from National University of Singapore, and going to presenting the talk on development of energy efficient air conditioning systems for aerospace industries.
Can you see my screen? Okay. Can you see my screen? Yeah.
Yes.
Okay, okay, great.
So, sir, could you please open your presentation in full screen?
Okay, sure. I'm going to do that soon. I'm going to do that now.
Yes. Okay. Proceed.
Okay. Can you see? Yeah. Okay. Very good afternoon from Singapore. Now here is about it's about 5 o'clock in the evening. My name is KJ Chua. I'm from the Department of Mechanical Engineering. Today, I'm going to present to you my work on a topic entitled Development of Energy Efficient Air Conditioning Systems for the Aerospace Industry. Okay, let's start off by giving you some general background on air conditioning in the aerospace industry. Air conditioning, as we know, is essential for comfortable living, particularly in controlling the desired temperature and humidity. And it's estimated that about 70% of energy consumed in airport terminals is due to heating, cooling, and air conditioning purpose. So with the widespread of pandemic COVID-19 virus, right, more fresh air is needed for ventilation, right, in most terminals and airports spaces. So that results in higher energy consumption for the HVAC, or what we call the heating, ventilation, and air conditioning applications. And so therefore, at this moment, there is real urgent need to properly manage the heat exhausted to the environment as well for cooling of the terminals. As we know, as we cool the terminals, part of the heat from the terminal has to be exhausted to the environment, and that has to be properly managed. If not, they will cause a lot of environmental issues, particularly related to microclimate effect. So beside air terminals, right, air conditioning is also essential for other parts of the airport system, particularly for hangars and airplane cabins, right? And then we know that close control of temperature and humidity are necessary to provide thermal comforts and reduce the growth of fungus and bacteria. Hangars consume lots of energy for air conditioning due to its huge floor space and huge volume as well, right, from the volume perspective. And the conventional vapor compression air conditioning systems consume a significant amount of energy, particularly in a hot and humid climate. Okay, this is due to the fact that in hot and humid climate, a lot of energy is expended to remove the moisture besides cooling the air. Right, so therefore, this vapor compression system need to inject a significant amount of energy, right, to the system, to just not only to remove the heat, but also to release the heat to the ambient during this cooling process. Therefore, a new paradigm in air moisture removal and cooling is urgently needed. So let's look at some of the key challenges that we have been facing, right, for this vapor compression system, which we have been using it for more than a century old. Right. Firstly, this system was invented in 1902 by William Carriers. Right, it's a bit more than a century old that we are still using the compression-based air conditioning technology. It uses chemical CFC or HCFC, and that causes global warming environment, and then also depletes our ozone. And these systems, one of the shortcomings of this system is that it does the sensible and latent cooling in one single process. Sensible refers to removing the heat from the air. Latent refers to removing the moisture from the air. And most of these vapor compression cycles has energy efficiency, or what we call the COP, right? It is a nomenclature that we always use for air conditioning, which refers to the coefficient of performance. It lingers about 3 to 4. And the COP refers to 1 unit of energy that you need to put in to derive 1 unit of cooling that you wishes to derive for X unit of energy that you input. And another very negative aspect of this system is that it constantly rejects heat to the ambient as it cools the room, as it cools the environment, right? And this system is pressurized. Therefore, any leakage in the pipes, right, the chemical refrigerant will be readily leaking up to the environment, and that causes a lot of environmental problems. And one of the last negative point about this system is that it's pretty noisy due to the compressor and the fan working in tandem, right? So the compressor cut in and cut out, so you hear a lot of noise going on. So the first dehumidification technology that has evolved from my group, right, my research group, is what we call a composite membrane. And this composite membrane is a hybrid between a ceramic and polymer material, and is used to synthesize high-performing membranes dehumidifiers. The ceramic material, which is a TiO2, is first layered on a fine metallic mesh to strengthen the base and regulate the pore size of the membrane. Subsequently, a polymer material combining TEG, right, and a PVA is then layered to significantly improve the moisture permeability and selectivity. And some unique features of this composite membrane that includes high water vapor permeability and selectivity, right, high durability and stable, is extremely flexible, and is real low cost to produce, and it can be easily scaled up, which we will show you in subsequent slides. Okay, so what the mechanism behind this moisture sieving membrane, right, can be explained by the principle of hydrophilicity, selective adsorption and diffusion mechanism, and the principle behind capillary condensation. Right, the water vapor molecules is first extracted to the membrane surface due to the hydrophilicity property. It is then sieved. Moisture is then sieved into the channel of the membrane by the process of adsorption and diffusion. Capillary condensation then ensures that the water vapor molecules is driven down towards down through the membrane pores to the other side for a complete separation between the dry air and the water vapor. This composite membrane that has been synthesized in my group has been compared with other research groups that are also having the same focus of trying to produce membrane that can remove moisture from the air, particularly from this group, research group at PNNL in US, which focus on making air dehumidifier membranes. So comparatively, our composite membrane performed remarkably well compared with this PNNL ceramic membrane in terms of water permeation as well as moisture selection ratios. Right? This performance augurs well, right, for using our membrane for air dehumidification in countries, particularly those countries that are residing in the tropics where the atmospheric humidity is consistently high. For example, in Singapore, our typical daily humidity ranges from about 75%, maybe up to 90% or even 100% when it rains. When it rains, is typically the relative humidity is about 100%, and that is really humid. So we have touched on of a membrane mechanism to sieve out the moisture from the air. So next, I will present to you a system that we have developed to sensibly cool the air. Right. So as far as the removal of sensible heat is concerned, we have worked on what we call the novel development of a highly efficient counterflow indirect dew point evaporative cooler. Right. This is different from the typical swarm cooler that you're familiar with. Right. In this particular case, the dew point cooler, in this dew point cooler, the air doesn't interact with the water directly. So briefly, how does this cooler works? Right. The counterflow cooler, or what we call the counterflow IDEC, right, indirect evaporative cooler, filters about 10 to 30% of the dehumidified air, right, from the dry channel. Remember that the first part, we already used the membrane to sieve out the moisture from the air, so the air is really humid. So this IDEC filters about 15 to 30% of the dehumidified air from the dry channel to the wet channel to facilitate evaporative cooling in the wet channel. Right. So when the water evaporates in a wet channel, it takes away heat from the, it has to take away heat from the dry channel, thereby cooling the air in the dry channel. So the key to this technology is that the product air, right, is cooled sensibly in the dry channel without any interaction with the water. So for these systems, this dew point evaporative cooler, we have scaled it up, and then we have improved its cooling process by proper controlling the channel, by a proper channel physical design and the optimizing the airflow. And this has led us to engineer one of the best dew point evaporative cooler in the world. Right, compared with some commercial dew point cooler as well. That's produced in US, for example, the Colorado system in US. Our prototype has consistently outperformed it, right, in terms of improving sensible cooling, as well as consuming less energy by 15 to 20%. So the next part is, the next question is, what happens if we combine the membrane and the indirect evaporative dew point cooler? And that will lead us to the next generation of air conditioner, whereby sensible cooling and latent cooling are innovatively decoupled. Right. So now you have engineered a system where you remove the moisture separately and then you cool the air separately. Right? And then from there you can produce your cool and dry air for air conditioning application. So here I'm going to show you the animation, right? The animation showing the entire air conditioning process, whereby the air is first dehumidified as the membrane sieve out the moisture from the air, and then subsequently the dew point evaporative cooler sensibly cool the dehumidified air. Those of you who are familiar with the psychrometric chart, right? You will know that the path on the psychrometric chart shows that the warm and humid air is conditioned to the desired humidity and temperature, right? By just moving down vertically and then moving to the left. So the coupling of this membrane and the dew point evaporative, the counterflow dew point evaporative cooler basically give us the next generation of game-changing air conditioner. Okay, here you can see a prototype that we have assembled 3 years ago, right? This is to show this prototype is, the purpose of this prototype is to showcase that how this game-changing air conditioning technology works. I'm sorry. Okay. The capacity of this cooling system is about 12,000 BTU, which is about right size to cool about 10 meter by 10 meter floor area. Right. The capacity is about 12,000 BTU. Is slightly bigger than the typical vapor compression system. And our latest prototype, we are able to condense this prototype to about 30 to 40% of its original size. So it's much more compact now, right? So this infographics sums up the performance of this game-changing air conditioner, right, with very impressive statistics, right? It is able to achieve 30 to 40% less energy compared to the vapor compression system. It's cheaper to manufacture because of the fact that it doesn't have any, it has very few metallic components, right? And it doesn't use the compressor. And at the same time, it's able to produce a portable drinking water from the air, right? When the water is being sieved out using the membrane, right? So typically, for about 20 hours of operation, right? Such a system can produce about 12 to 15 liters of water, or portable water from the air. So imagine you are enjoying your aircon during the night, but you are making fresh water that you can use in the morning. Okay, the next technology that I'd like to present is another innovative work that we have done. Is also for air dehumidification, but in this case, it's a polymer-based super absorbent. Okay, what we did was we benchmarked our super absorbent with the best grade A commercial silica gel. Right, this new class of polymer-based super absorbent has about 4 times more moisture absorption capacity, and more importantly, it regenerates at a much lower temperature, about 40 to 50 degrees, right, compared to silica gel, which needs to be regenerated at about 80 to 120 degrees C. And the regeneration time is also relatively shorter, about 30% less, right? And most importantly, that this super absorbent can be easily coated on the metallic surface of any heat exchanger, right? Namely copper and aluminum. So in a recent comparison we made with some ultra absorbent material, right, produced by MIT and Berkeley, we found that our super absorbent compares well, but we have a much higher absorption capacity, and we regenerate at lower temperature and also at a shorter duration, right? And this super absorbent can be potentially be employed for water harvesting from ambient, right? Harvesting water from ambient using low energy for regeneration. And further, this super absorbent has demonstrated antibacterial, anti-germs, and anti-fungus capability. So air that flows through this super absorbent material right, has relatively less bacteria, germs, and fungus count. And we have successfully coated this material on a heat exchanger, right? Coating this material on the heat exchanger will allow the air dehumidification to be carried out in heat exchanger, whereby simultaneous dehumidification and sensible cooling can be carried out at the same time, right? And we have done that for a commercial air conditioner. We are able to make use of the condensing waste heat from the condenser side to regenerate. If you are familiar with your air conditioning system, you realize that the hot box, the condenser, typically throw out heat about 45 to about 55 degrees C, and that amount of heat is just appropriate, right, to regenerate this super absorbent material. And what is the advantage of having coating this material on the heat exchanger, both the cold side and the hot side? So on the cold side, the evaporator coil, right? Your evaporator will now operate at a much higher temperature as opposed to previously when the material was not coated on a heat exchanger, right? If a conventional evaporator coil will operate about 5 to 7 degrees. If you coat this new material on the evaporator coil, now the coil will be operating about 15 even to 18 degrees. The key reason is being that this evaporator coil no longer needs to take away the latent load, or no longer need to remove the moisture from the air. It doesn't need to operate at much lower temperature to condense the moisture in the air because of this material ability to absorb the moisture from the air, right? So now the evaporator coil can operate at 18 degrees, 15 to 18 degrees, and that really saves you a lot of energy. So we have done our experiment in the lab for many of this commercial system by just coating this material. Consistently, we are seeing energy savings in the range about 25 to 35%. There's another technology that I'd like to discuss with you will be the dehumidification technology that employs a novel nano-hybrid MOF material. The MOF refers to metallic organic framework. Okay, this is a new class of desiccating material that has a superior performance in terms of taking moisture from the air. So the MOFs, right, are promising sorbent materials for water harvesting and for air dehumidification. We know that there are some polymer material, for example, the Nipan material, which is this Nipan material are highly thermal responsive, right? It means that it's able to transform from hydrophilic to hydrophobic property, right, at a temperature close about 30 to 35 degrees C. So imagine a material can be hydrophilic at a certain temperature and then transisted to become hydrophobic at almost room temperature condition, right, about 30 to 35 degrees C. So what our group did was we incorporate this Nipan material with the MOF, right? We incorporate them, we hybrid them, and then we develop the next generation of a smart composite desiccant, right? We can be easily regenerated at very low temperature. And we have synthesized a series of such smart composite desiccant containing this Nipan material, right, within the cavity of this mesoporous MOF MIL 101. And this composite material, this new composite desiccant, can absorb up to 440% of its weight, or water weight, right, at 25 degrees. And then it can release 98% of its absorbed water by with temperature below 40 degrees. And this is a true, is a real breakthrough in terms of material performance, in terms of material ability to absorb moisture from the air. Okay, both potentially the super absorbent and the smart composite polymer MOF desiccant can be deployed in moisture control, dehumidification application, water harvesting from ambient air, and also to improve the performance of heat-driven absorption chillers, right, providing higher cooling effects while regenerating at a much lower temperature. So with this new class of material, there's a lot of application that we are looking at. And now your next question is, are you still working in small samples? Right? Are we able to scale it up and see bigger effects? Okay, before we answer that question, we need to know that for most cooling systems, right? For example, if you're building a cluster of buildings, in these buildings, normally you do not use a single small air conditioner to provide the cool and dry air. You are using big scale chillers, right? So at large scale chiller system, right, we can demonstrate by real-time data that if you can provide the chill water, right, at much higher temperature, right, then enormous amount of energy saving is possible. For example, in Singapore, where our outside temperature is about 32 to 35 degrees, our humidity is about 70 to even 100% RH. Right? The chill water that we provide to the buildings, right, by the chiller is about 6 to 7 degrees, right, in order for it to be able to sufficiently remove the moisture from the air, and as well as to cool the air to the desired temperature. And we have done this experiment, right? And then we have in a lab, and then we found using big chillers, we collected the data, and we found that every degrees increase in the chill water temperature easily translate to about 3.5% increase in energy efficiency for the chiller plant, right? So in other words, instead of operating at about 6 to 7 degrees, if you operate it at about 15 to 16 degrees, right, you're going to see about 30 to 35% energy savings for your chiller plant. And that is very significant. So in other words, if a chiller is now able to provide the chill water at a much higher temperature, say from the usual 5 to 6 degrees, now is able to provide the chill water is now raised to 13 to 15 degrees, you are able to realize energy savings of up to 30%. And the next slide will answer your question. Yes, we have done that, right? We have made our membrane much bigger size, big piece of membrane, about 1.5 meter by 1.5 meter. For big buildings, we have like a membranes of 100 pieces, more than 100 pieces stacked up like sandwiches, and we can lock them up, and then we can sieve out lots of moisture from the air, right? And then we have coated our super absorbent material on a large heat exchanger, and also seeing them remove a significant amount of moisture from the air as well. And this application in big air handling units, right? Because this is going to be installed in an air handling unit, clearly demonstrate this impact of this technology in realizing energy savings, right? To produce dehumidified air for the purpose of air conditioning. So imagine, envisage the situation where we install this breakthroughs dehumidification technology in the AHU every building, right? So in other words, the latent load, the moisture component of whereby the AHU need to handle, right, has been taken care of by all this game-changing dehumidification technology. The chill water supplied, right, from the central plant or the central chill water plant now can be provided at much higher temperature, right? Instead of 5 to 6, it's now providing chill water at 13 to 15. And every building is now able to realize energy savings of up to 35%, right, for one single building. And that is very significant if you consider a cluster of building. And this effect can be manifold if you are looking at district cooling, right? District cooling system where a big chiller plant is providing cooling for maybe up to 30, 40 cluster of building at one time. Before I end my presentation, these are two recent monographs that I've authored, right? And it may be of interest to you. And most of these technology that I've mentioned in this presentation are described in more detail some of the fundamental principles are documented inside these two monographs. You may wish to either get the e-version or you place your order through Springer for the hard copies. So I've come to the end of my short presentation. If you have any question, I'll be most happy to take them.
Yeah, thank you for the wonderful presentation, Dr. Shaw. Now the stage is open for the questions. You can stop sharing the screen. Okay. Now the stage is open for the questions. So having any questions from the speakers, you can ask to Dr. Shaw. Dr. Chang, I assume that there are no questions for you.
Yeah, sure. It's not a problem. It's okay. Right?
Yes. Once again, thank you for being part in our webinar.
Yeah, thank you for the invitation. Yeah, thank you very much. Yeah.
Moving towards the next presentation by Uta Rnr and from Tsinghua University, China, and he's going to present the talk on high power density electric ducted from propulsion technology. So, Dr. Uta?
Yes, I'm here. Thank you for your hosting. Could you please open the video which I sent you yesterday?
Okay, Doctor. Please give me a moment. I'll share the screen.
Okay.
Thank you.
Good morning, I'm Yuping Chen from China. My presentation topic is high power density electrical ducted fan propulsion technology. My presentations includes 4 parts. First will be the introduction. The second will introduce the one-dimensional coupling design model between the fan and the motor. The third part will introduce the 3-dimensional coupling effect inside the electrical ducted fan systems. The last one will be the conclusions and expectations. First, as we see, the electrical duct fan has been the key subsystems of the eVTOLs and e-aircrafts. In the utilization of the urban air mobilities, Lilium has developed 36 electrical duct fan propulsion systems, which could support the vertical takeoff and landing. And Airbus is conducting the eFan project, which is contributed for the future electrical airliners. But what is the requirement for the electrical ducted fan? First of all, the high power density is always the issue. And the second, if we take the typical design of a tilt-rotor or tilt-wing aircraft, we can find that the flight mission will determine a high power ratio. The power at the climb stage or the descent stage will be significantly larger than the power used in the forward stage. It's around 5 times. So the flight mission requires the aviation motor must have strong overload capacity. And due to this, the motor cooling systems must be simple, strong, and easy to system integration. The best choice will be the air cooling. How to achieve the higher power density of the electrical motors? Normally, there will be 3 ways. The first is using the advanced materials. The second is using the advanced electrical magnetic design. And the third will be the thermal management. And our group are focusing on the advanced thermal management technologies to increase the power density. From the expressions, if we can reduce the thermal resistance inside motor and the motor surface, then we can increase the motor power density. But we also need to consider the additional mass caused by the thermal management components. If we can get a good cooling, but we must pay for a very high mass of the thermal management system, then the power density will not be increased as we expected. So we proposed an idea that if we enhancing the cooling capacities, can we reduce the weight of the thermal management system so that we can get all the benefits to increase the power density of the motor? This is our research logics. At current stage, we make a simple assumption that all the motor heat loss will be fully transmitted to the motor housing. And based on these assumptions, we are trying to find the maximum heat dissipation capacity of the housing fin. First of all, if we want to maximize the housing fin cooling capacities, we must understand the trade-off between the cooling and the aerodynamics. At the certain requirements of a ducting fan with a fixed diameters and a fixed thrust, if we increase the motor diameters, we can get more airspeed. We can get large airspeed, and which is good for the cooling at two aspects. First, when the motor diameter increase, the cooling fin areas increase, and also the airspeed increase. So this is good for cooling. But when the motor diameter increase, the airspeed increase, we will get more loss through the fan rotor. So which means it's bad for the aerodynamics. So to balance the design between the cooling requirements and also the aerodynamic performance, we need a one-dimensional coupling model between the ducting fan and the motor. And the model is used to find the best matching between the ducting fan aerodynamic performance and the motor cooling requirement. And the second, when we set up the fin near the fan rotor hub regions, the fin will make the blockage to the flow around the fan rotor hub. And if the blockage is large, then we will decrease the airflow speed near the hub region and also near the fin. So this will make the housing cooling capacity poor. So at the three-dimensional levels, we need the coupling design between the fin and the fan rotor to maximize the airspeed through the fin and get the maximum air cooling capacity at the mounting housing surface. Then I will introduce the one-dimensional coupling design model between the fan and the motor. According to the study of the mirror, we found that the temperature distribution is very sensitive to the heat transfer coefficient between the motor frame and the ambient. Based on these understandings, we select the Harp-tip ratio as the key parameters to connect the aerodynamic and the motor cooling requirements. The Harp-tip ratio is defined as the ratio between the motor diameter and the fan diameters. And through the model, we can calculate the optimal point of the best balance between the aerodynamic performance and the motor cooling requirements. And we verified it in our small electrical duct fan unit in Tsinghua University, which is has a 100 Newton thrust and has around 300 millimeters diameters. And also we published our research, and if you are interested in the details of these models, you can read it and find it details inside the paper. And third, I will introduce the three-dimensional coupling effect between the fan and the motor. To study the coupling effect between the fan and the housing fin, firstly, we change the fin type. We take the 4 typical types as our research schemes, including the straight type, the inlet arc type, the inlet airfoil type, and also the tandem type. And then, based on the fin type effect on the performance, we propose a coupling through flow design between the ducted fan rotor and the motor housing fin. From the safety results, we can find that the straight type fin would induce inlet flow separation inside the fin, and which will block the flow area and reduce mass flow rate. So the straight fin has a poor cooling capacity compared to the inlet arc fin and the inlet airfoil fin. And we found that if we want to reduce the blockage caused by the fin, we must have an inlet bend. So the flow angle between the rotor harp region and the fin is important. It will determine the flow distribution along the span of the rotor. And when we designing the fin, we should pay more attention on how to increase the mass flow rate of the fan rotor harp region, which will increase the fin cooling capacity. And then we conduct the tandem fin research, and it's a very interesting result we can get if we're using the tandem fin configurations at the same fin areas. We can get lower temperature around the fin. So, and also the maximum temperature areas reduce significantly in the tandem fin. So the tandem fin has the better potential for enhancing the air cooling along the motor housing. Based on the previous research, we find that the flow angle matching is important to enhance the cooling capacity of the fin. So we propose that how about we treat the fin as a stator inside the rotor through-flow? Based on the traditional through-flow design chart, we add the thermal requirements inside the process and make the best balance between the aerodynamics and also the cooling requirements. Finally, I will introduce the conclusions and expectations. As I described, the thermal management technology is key to increase the power density of the electrical duct fan propulsion units. And the coupling effect between the fan aerodynamics and the motor housing cooling is worth focusing on. And the air cooling technology still has a good potential for application of the electrical duct fan propulsion. But the air cooling technology still has its limitation of the power levels. And how to use the low temperature air to enhance the motor cooling is still a valuable question to us. And in our group, we are researching on the flat heat pipes to reduce to enhance the cooling inside of the motor and also the cooling outside of the motors. We are researching on how to arrange the flat pipes inside the motors and also make the arrangement with flat heat pipes around the electrical fans. That's a new project for us, but we are expecting it could help us to get the best performance of the air cooling technology, and which could help us to get the higher power density of the electrical motor. So thank you very much for your attention.
Thank you very much. Do you have any questions?
Thank you so much for the insightful talk, Dr. Uta. Having any questions from the speakers, you can ask now. Okay, Dr. Uta, I think there are no questions from your side, from speakers. So once again, thank you for being part in the webinar, and hope you will associate with our future events as well. Thank you so much.
Thank you very much.
Moving towards the next presentation by Zen Han, and from the University of Beijing Institute of Control Engineering, China. I'm going to present on diagnosis and stimulation study of injector spray, field of biopropellant, thruster, and epoxy engine. Dr. Zen.
Hello, can you hear me?
Yes.
Okay.
Yes.
Could you please just play my video as
Yes,
well?
sure. Please give me a moment. I'll share the screen.
Thank you so much.
Yeah.
Hello, everyone. I'm very delighted to attend Aerospace and Aeronautics World Forum and share some of my research. I'm from Beijing Institute of Control Engineering, a senior engineer for 16 years. My research is to design the propellant rocket engine and thrusters for satellites. and the focus is on the spray combustion and liquid film cooling. Today I would like to talk some work of injector spray, which is a primary determining factor of the propellant thruster and apogee engine for spacecraft propulsion system. There are 4 sections in my presentation. The first is about engineering background. The second is about some experimental diagnosis method of spray field. The third is spray simulation research, and the last is a combination research based on both experiment and simulation. As we know, satellite and spacecraft have been developed rapidly, with multiple functions recently. Meanwhile, for the propellant propulsion system with apogee engine for orbit control and thrusters for altitude control are requested to satisfy more requirements. In terms of apogee engine, we need it with high specific impulse, long lifespan, adjustable thrust, and multiple launches in orbit. As for thruster, it should be developed with rapid response, small pulse width condition, impulse repeatability, and multi-impulse lifespan, more than a million times under different work conditions. Swirl injector has been widely used in the propellant rocket engine design. It has natural uniformity and stability in spray atomization, and can make the propellant achieve stable combustion under multiple working conditions. After swirling atomization, mixing, and combustion, fuel and oxidizer can generate high-temperature gas in combustion chamber to power the satellite. The gas temperature is usually up to 3000 degrees. The injector is designed to balance mixing of propellant and liquid film cooling by optimizing spray atomization. However, the combustion efficiency and cooling performance often needed to be tested through Turing test at very high cost. However, spray field diagnosis and the code condition and simulation analysis also indicate a large number of data and information. In this way, the early diagnosis of engine characteristics can be achieved, thus aiming for failure prevention and design optimization. The liquid-liquid coaxial swirl injector can be considered as a combination of 2 swirl nozzles. Due to the existence of negative pressure zone between the inner and outer liquid spray, MMH and NTO are mixed with primary breakup and secondary breakup for next evaporation and combustion. As many researchers studied, both velocity distribution and energy transformation in spray field are very complex. So we hope to find an effective way to help us in design of the propellant engines, so that it does make sense to use the information in spray test and simulation at low cost. If we want to diagnose the spray field of swirl injector, a storage and supply system should be firstly constructed for spray test to collect the original optimization information of the spray field. With the aid of high-speed photography and image analysis, both the spray spatial distribution and injection velocity distribution can be effectively visualized. For single image, we cannot figure out any problem, but after pre-processing in these spray images, we can stack and then average thousands of them at different moments. So the structure difference can be visualized immediately. Better spray should have a characteristics of conical liquid film, concentrated on both sides, conducive to mixing. Worse optimization uniformity is obviously poor. We can divide the left and right part of mean image and regard them as two gray matrices and compare them quantitatively by cosine similarity that just reflect static uniformity of spray. Tracking the droplet's position in hundreds of images give us an average distribution of velocity. So this distribution of velocity can just reflect the dynamic uniformity of spray compared to the last one. Moreover, droplet size is also needed to observe. The backlight illumination method used in this study to identify focused droplets and determine their statistics. The accessibility of droplets is constrained based on the minimum intensity gradient at the boundary of individual droplets. Droplets having boundary intensity gradients less than the minimum gradient can be neglected in statistics. And the capability of POD method to resolve spatial modes and the temporal scales associated with those modes in order of their importance is determined in identifying the dominant features in the primary breakup region. The first 6 main modes of most energy contribution can indicate the breakup factors clearly. So we can see abnormal injectors found in POD diagnosis were proven to get corresponding problems in subsequent variant tests. For thrusters, their spray is different. It works under the transient condition. In the process of valve opening, the flow is inevitably unstable with fluctuation, and there is a orifice plate which is sited in the flow passage to control equivalence ratio. The traction spray from downstream's wall injector is significantly determined by the fluctuating flow. The dynamic mesh and the interfoam solver can be used to analyze the fluctuation in the following 5 milliseconds after valve opening under different conditions. In the following simulation, simulations are conducted in 2 sections. The first is to investigate the fluctuating flow rate in the valve opening process using dynamic mesh, and then the fluctuating flow rate can be provided as in-light boundary condition for injector spray in the second section. In matching its transient flow rate. For the first part, it describes the valve opening process. The amateur valve seat moves to open and propellant flows with fluctuation to downstream. That is an axis symmetry structure, so we use 2D simulation with wet mesh in open form to describe valve switch flow. The in-light boundary condition is constant pressure in-light. There are 2 orifice plate layouts. The first is set downstream and the second is set upstream. The same can be said to the next part, injector spray. The wedge mesh with 5 degrees is also used to simulate swirl spray from injectors. The mesh in spray domain is refined as small as 10 by 10 microns. It has proved adequate to capture the breakup droplets, with an average diameter of above 50 microns measured by PDPA. The in-light boundary condition is from the fluctuating from the outlet in the last case. The above image is outer injector for NTO, and the below one is inner injector for MMH. In parametric study, different propellants, switch speeds, valve strokes, and orifice plate layouts are listed in table. These differences can be expected to figure out the different effect on transient spray. In this way, this study shows the better group of valve coverage can improve the thruster's impulse performance in our project. After that, our focus is on steady state now. The first, we hope to see the difference in propellant properties. NTO is oxidizer with low surface tension and viscosity, so NTO is designed in outer walls due to its more easily optimized properties. In the switching process, fluctuation in NTO flow with lower surface tension is more significant. After flowing out from the valve outlet, these two propellants will enter two different separate injectors. NTO flows into the outer nozzle and MMH flows into the inner circular. Different switch speed of amateur affects the fluctuation. Switch speed decreased, and the MMH flow tends to become most unstable. When switch speed drops down to 0.125 meters per second, the fluctuation amplitude of the flow surges significantly. For MMH spray, when switch speed is low, violent fluctuation can significantly strengthen the disturbance so as to obtain comparatively better droplet breakup, but its stability is worse than that of high-speed switch. NTO flow is more sensitive to the effect of amateur speed in opening process. When switch speed is reduced to 0.25 meters per second, is already sufficient to reach the number that causes violent fluctuation. Limited by the structural disadvantage of the outer nozzle, the spray optimization of NTO is relatively more difficult, even though the NTO property is conducive to optimization. Therefore, the optimization of NTO takes a relatively long time. In the instant time of just 5 milliseconds, the high-speed switch contributes to the intact and stable optimization. The valve stroke determines its opening gap, influencing cavitation generation. Increasing the stroke can greatly strengthen the flow stability with lower fluctuation. In these comparative cases, the liquid film can form an umbrella-shaped structure with similar hollow vortex core, film breakup length, and spray cone angle, and the atomizer size of MMH tends to be smaller at larger valve stroke. As you can see in these two images, when we set the valve stroke to be bigger, the optimized droplets of NTO is more dispersive in spatial distribution. But I think that is more combustion friendly for the following diffuse burning process. Compared with the downstream layout, upstream orifice plate can lead to more stable but much lower transient flow rate. The small injection with lower velocity input significantly weakens the aerodynamic interaction, so that can cause worse optimization quality, as you can see in the simulation. For NTO spray, that is the same situation. When we set the orifice plate upstream, the spray in fact is decreased significantly. So, from the result in the simulation, downstream of valve is brighter place to set orifice plate for the equivalence ratio. That is the change of the total surface area ratio over time. Due to the initial strong fluctuation of valve speed, the MMH spray reaches a peak at 2 milliseconds, and the NTO spray reaches a peak at 4 milliseconds. The MMH spray gradually stabilizes after 3 milliseconds, while the NTO spray requires 5 milliseconds back to surface area ratio around 1. In the Harping test, we can see the results at different on-time commands. At on-time of 4 milliseconds command, the impulse repeatability is not good, with 3 sigma over 60%, because you need 3 milliseconds to make the valve to open. So there is only 1 millisecond left. It's not enough for stable spray and combustion. When on-time rises, 3 sigma decrease to 40% at 6 milliseconds command, and just 28% at 8 milliseconds command. Increasing the sway speed and reducing the delay time of valve can be the only way to further improve dynamic response of bipropellant thrusters. The next part is about the liquid film cooling. We need to know droplet wall impact characteristics. Basically, it's believed that the droplet impact characteristics are related to the wall condition, wall temperature, and the vapor number of the droplets. So I hope to use a combination of experiment and simulation to see how the process would be different under the coated wall condition. In the experiment, we focus on the single droplet impactor situation. We establish a system with high-speed camera and microscopy. Those can be used to capture all the information of single droplet impingement on the real coating wall. All droplets are made by droplet generator. The high temperature condition is constructed on the real coating wall sample with heating system to simulate the boundary condition. We use 2 cans of the coating wall to make the difference. Sample 1 is rough, and sample 2 is smooth. At normal wall temperature, we increase the impact vapor number of the droplet gradually from small to large, and observed the development of droplet after impingement. Because it's a curved wall without any heat transfer, the results were rather simple. Droplet will stick to the wall and spread and splash. When the vapor number is over around 600, sample 1 will start to form splash. For sample 2, only when the vapor number increases to more than 850, splash starts. This result shows the roughness of the wall has a significant effect on the droplet wall impact behavior. The rougher the wall surface, the easier the splash. And let's turn to the high temperature situation. Impingement can be different from the coat impact. It's obviously to see the difference between 2 coating samples, left and right. When wall temperature is lower than boiling point, the situation is similar. When wall temperature exceeds boiling point, the droplet starts to break up into many small droplets because the liquid film is subject to a strong perturbation and boiling condition. At the same time, the liquid surface tension decreases with the increasing temperature. The liquid film becomes more unstable. We continue increasing the wall temperature over the leading first point. The impact wall droplets changes significantly. Sample 1 is likely to suspend near the wall, while sample 2 tends to rebound away. The reason is sample 1 is rather rough, with looser surface structure. It's easy to form many macrocoils between the solid and liquid interface. That leads to the increase of apparent thermal resistance and the decrease of heat flux between solid and liquid. However, the sample 2 is smooth. When the droplet enters the latent first state, its lower apparent thermal resistance will increase the evaporation rate of the wall-attached liquid and lead to the broken droplets getting bigger propulsion force and rebound speed to move away. After getting all information like speed, size, and number of droplets after impact, we can continue to establish a classification of impact mechanism. When the wall temperature is low because the critical Weber number of sample 2 is higher than sample 1, more liquid films will be formed in the low temperature region. It's helpful for cooling the engine's injector. When the liquid enters the latent first state, the mechanism of sample 2 is likely to rebound. Rebound can make droplets participate in the central combustion, while suspension will cause propellant to mix and burn near the wall surface. It's risky to form local high temperature on the wall surface. If we want to prove our interference, we have to use simulation technology to help us. So we start to establish a mathematical mode and put that in the simulation and solve for it. This model is based on the results of previous studies of researchers and our experimental observation. When the wall temperature is lower than the boiling point of liquid, the prediction of the mass ratio and the quantity of splash droplets is given based on Gauss-Mann model. We can get a distribution of the droplets diameter based on model of Standen and Rutland. In terms of the splash speed and angle, we can use the method of Calentary and Tropia to describe it. We have corrected the coefficient according to the experiment measurements, matching the data and to get the equation. Let's see the simulation results. The distribution of oxidizer vapor and fuel vapor in sample 1 is separated. That means the mixture is not so good, having negative effect on the combustion. However, the mixture of two vapor in sample 2 is more uniform and overlapped. It's conducive to improving the combustion with high efficiency. Meanwhile, it's also good to shape the central high-temperature flame, making the cooling film attached to the wall survive for a longer time. I make the comparison between the new impact model and the OA film model, which is from the study of O'Rourke and Amston. From this image, we can get a better prediction by using new model, which is closer to the fairing test result measured by infrared temperature equipment. The use of simulation for us is to make the design at lower cost. It can help us get optimized result without using too much money on fairing test. That's all of my presentation. Thanks for your attention.
Thank you for your insightful presentation, Dr. Zen Han. And having any questions from the speakers, you can ask now. Okay, I assume that there are no questions from the speakers, Doctor. So once again, thank you for being part in our webinar. Hope we will associate with the further events as well. Thank you so much.
Thank you.
Yeah. And now moving towards the next presentation, will be a video by QE from Beijing Institute of Science and Technology, China, and going to present a talk on numerical simulation, research on the flow field around a submarine with full appendix based on boundary data immersion method. So, Dr. E.
Hello, can you hear me?
Yes, yes. So,
thank you. Can you just play my video?
Yes, yes. Please give me a moment. I'll share.
Yeah. Thank you. Hello everyone, I'm Yiqu from Beijing Institute of Technology. I'm a student in the third degree. It's my great honor to attend this symposium and present our work with you. My topic today is numerical simulation research on the flow field around the double suboff based on boundary data immersion method. The main content includes 5 parts. Firstly, I will show you the motivation. When sailing underwater, the boundary layer separation occurs over the body, which will lead to complex three-dimensional separation flow and vortices at sail-body junction, resulting in turbulent pulsating pressure. The noise of an underwater vehicle can be divided into mechanical noise, propulsion noise, and hydrodynamic noise according to its causes. For medium and high-speed underwater vehicles, the hydrodynamic noise generated by the complex vortex structures on the surface of the vehicle becomes the main noise source. The problem is that the current software cannot balance accuracy and economy at the same time when calculating large-scale geometric models with complex geometric boundaries. Therefore, it is necessary to establish an efficient and accurate self-programming numerical calculation method. In this study, we mainly focus on the flow prediction ability of boundary data immersion method and the evolution mechanism of complex vortex structures around the double suboff. The flowchart of boundary data immersion method shows the detail of numerical methods for solving Navier-Stokes equations for the fluid-solid system. The finite difference method is employed in the present study. For the BDIM, the original computational domain consists of solid subdomain and fluid subdomain. Therefore, its domain has its own governing equation. As following, where phi denotes the set of independent variables. For both subdomains can then be smoothly coupled by a convolution of its governing equation with a nascent delta kernel k epsilon of radius epsilon. Finally, we can obtain a matter equation of the governing equation based on the whole computational domain. Numerical simulation is carried out through Fortran-based code. The double suboff model with full appendages is adopted in this work. The main parameters of the double suboff and the working condition of calculation are shown in the table. In order to achieve the best balance between calculation accuracy and calculation resource consumption, the calculation field was composed of 108 million nodes. Eulerian local region type vortex identification criteria, including the vorticity, Q criteria, and the omega criteria et al., are widely used for vortex identification due to the simplicity in applications. However, most of these criteria are based on a scalar quantity, unable to identify vortex axis lines. To address this issue, a novel Lutex method, based definition of vortex axis line is applied in this paper. Vortex is a physical quantity proposed by Professor Liu to show the magnitude of local rotation intensity and the direction of local rotation axis. Being different from all other vortex identification methods, vortex is a vector, which provides both the local rotation axis and the rigid body angular speed. We compare with the predicted pressure coefficient along the meridian line of the suburb with the experimental results, and a comparison of the pressure coefficient between the predicted results and measurements by Huang et al. At different heights of the sail is also seen in Figure B. It clearly shows that the predicted no-dimensional pressure distribution is well matched with both the experimental results and the computations. In addition, Figure C shows the measured and predicted no-dimensional axial velocity on the propeller display. It can be seen that as the theta increases, the velocity exhibits a periodic fluctuation. The figure shows the vortex structures around the suburb, which are identified and extracted by isosurface with normalized Q. The vortex structures around the hull can be divided into three types: horseshoe vortex, harping vortex, and necklace vortex, as marked with red dashed line. In addition, the complex vortex structures can also be captured at the tail of the suburb. To further investigate the generation mechanism of the vortex structures around the suburb, the detailed flow characteristics of typical vortex structures are analyzed one by one. Firstly, a horseshoe-shaped vortex can be observed at the joint of the sail body. Figure A illustrates the horseshoe vortex extracted by a normalized vortex method. The transverse vortex can be observed in front of the sail. Due to the great adverse pressure gradient caused by the sail, then the transverse vortex is blocked by the sail and bent into longitudinal vortex on both sides of the sail, with the normalized velocity on both sides of the sail increasing due to the mass conservation, and the longitudinal vortex is drawn into the horseshoe vortex with large stress. It can be seen from the pressure counter and streamline distribution at the upstream of the sail that there is a transversal vortex at the junction of the leading edge of the sail and the hull, due to the existence of the high pressure zone in front of the sail. Similarly, it can be seen from the velocity counter on both sides of the sail that the side flow is speeded by the lateral of the sail, which is similar to the hydrofoil. Figure A illustrates the harping vortex extracted by a normalized vortex method, and shows the spiralized vortex on the surface of the sail, caused by the rotation of the boundary layer, and it bends and rolls up from the surface due to the velocity disturbance, which leads to the formation of the harping vortex structures. Since the hand of the vortex structures gets away from the surface, as the vortex moves downstream, the distance between the hands and the legs of the vortex increases continuously due to the difference of velocity distribution. As shown in Figure B, on the typical sections, the rotation course can be well captured by vector lines, which corresponds to the legs of harping vortex. From Figure C, The Harping vortex has a trend of radial diffusion while it goes downstream, which may be due to the existence of the radial velocity around the Harping vortex. The necklace vortex. Due to the interaction between the side flow and the top flow around the seal, as shown in Figure A and Figure B, a counter-rotating vortex pair is formed behind the seal. With the development of the counter-rotating vortex pair around the hull, the necklace vortex shed from the tip of the seal. From Figure C, the stress of the counter-rotating necklace vortex pair is becoming weaker with the development along the hull due to the energy dissipation of the vortex structure. In order to further compare the influence by different types of vortex, we supplemented the local rotation stress of the rotation axis, which is extracted by Lutex method. The figure shows the Lutex magnitude of the vortex structures, which represents the local rotation intensity of the vortex. In present work, the results show that the average vortex rotation intensity value of the Haussmann vortex distributed along the vortex axis is 40.58, and the value of Harping vortex and necklace vortex are 4.31 and 9.46. Therefore, in present work, the Haussmann vortex plays a dominant role in the influence of turbulent structures on the double above. To further investigate the transient evolution of typical vortex structures, the figure shows the evolution of the Harping vortex structures and corresponding Lutex line. The Harping vortex structure's first structure, as shown in Figure A, is formed, which is induced by the K-type stability mechanism. The Lutex gradient of vortex head is greater than that near the roots. As shown in Figure B, one of the vortex length of first structure disappeared due to the energy dissipation near the wall, and the shape of vortex structure had changed greatly. Then, the outline of first structure is deformed, and the O-shaped vortex is formed, as shown in Figure C. Finally, the fracture of second structure occurs due to the weak intensity with the U-type vortex structure formed. Similarly, the figure shows the evolution of necklace vortex structures and the corresponding Lutex line. Firstly, the necklace vortex structure is observed, which is induced by the interaction between the side flow and the top flow around the seal. As shown in Figure B, the vortex roots of first structure is getting closer, which may be due to the low pressure inside the vortex roots. Then, the Lutex magnitude of the necklace vortex hand becomes smaller due to the engineer dissipation, and it has a trend of fracture in the weak intensity region, as shown in Figure C. At the next moment, the first structure fractures in the weak intensity region and divided into two parts, namely the second structure and the third structure. Finally, the second structure and third structure extend farther along the hull, with the Lutex magnitude of structures become smaller due to the energy dissipation, which leads to significant deformation and shedding downstream. Finally, make a summary of the above analysis. The seal and the star pattern genes strongly affected the flow around the hull, producing various types of vortex structures. which can be divided into three types: horseshoe vortex, harping vortex, and necklace vortex. The results of this investigation show that the horseshoe vortex plays a dominant role in the influence of turbulent structures on double support. According to Lute's method, the evolution of the harping vortex has experienced the dispersion of vortex leg, O-type structure distortion, and then broken into U-type structure. Similarly, the evolution of necklace vortex also experienced extension, distortion, fracture, and divided into two parts. Finally, special thanks to Professor Liu. The Lutex code is released by Chaoqun Liu at the University of Texas. That's all. Thank you.
Thank you, Dr. Yu, for the wonderful presentation. And now the stage is open for questions. Having any questions, please, you can ask.
I'm audible? I'm audible?
Yes, Dr. Sudarshan.
Yeah, so I have one question. What velocity range you have taken, QE?
Sorry, can you repeat?
What velocity range you have considered for this simulation?
It's equal to the direct numerical simulation.
Fine, but what is the velocity conditions?
The velocity is 3.05 meters second.
What is its value? Maybe in terms of Reynolds number?
It's here. Can you see the?
Okay, 3 meters per second. Fine. Thank you.
Okay, thank you.
Okay, now you can stop sharing the screen. Okay. Dr. Yu, can you please stop share the screen?
Okay.
Oh, yes, thank you. Any other questions? Okay, I assume that there are no questions. Okay, once again, thank you so much for being part in our webinar. And hope you associate with our further events as well. Thank you so much.
Thank you.
Yes. So moving towards the next presentation, will be by Time Bechen from Beijing Institute of Science and Technology, China. And he is going to presenting the talk on numerical investigation of cavitation vortex structure around a hydrofoil. Okay, Dr. Bechen.
Can you hear me?
Yes. So will you share the screen or shall I share on behalf of you?
Could you play the video?
Okay, thank you. Please give me a moment.
Hello, everyone. I'm Tian Beichen from Beijing Institute of Technology. It's my great honor to attend this symposium and present my work with you. My topic today is numerical investigation of cavitation vortex structures around a hydrofoil. I'll introduce my work from the following aspects. Firstly, the motivation of this work. The aesthetic cavitation occurred in the high-speed flow is complex, involving multi-phase flow, turbulence flow, compressible flow, and also phase change. The occurrence of cavitation will lead to the change of local turbulent kinetic energy, and the shear in the turbulent field is the premise of cavitation. Therefore, the structural analysis of cavitation turbulence is key to study the unsteady flow mechanism of cavitation turbulence. Next, I'll mainly introduce the numerical model adopted in this work. Compressibility is an important characteristic of the cavitating flow. In this work, we employ the artificial compressibility method to investigate the compressibility of cavity region. A pre-time derivative of the pressure multiplied by an artificial compressibility factor is added to the continuity equation. What's more, the boundary data emerging method is employed. The convolution of governing equation with a nascent dirt kernel is applied to smooth the transition region between the solid and the fluid subdomain. In this work, the numerical results were obtained using a Fortran-based code. The structured grid of the computational domain is about 8.1 million nodes. The experimental studies are also conducted in the high-speed cavitation tunnel in Beijing Institute of Technology. The model of heterofoil is NACA-66 with a chord length of 100 micrometer. The experiment and the numerical work are both carried out with a fixed attack angle of 8, and the real number of the flow is about 1 million. Through this displayed picture, we can observe that the evolution of cavity structures and the length of attached cavity consist while between the experiment and the numerical results during one period of cavitation flow, which validates that the developed coupling algorithm can actually capture unsteady cavitation characteristics. Meanwhile, as depicted in this left picture, the transient cavitating flow can be divided into 3 typical stages. Stage 1. The growth of the attached sheet cavity. Stage 2. The development of a reentrant jet. And Stage 3. The cloud cavity shedding. Next, we use the numerical data to discuss the vortex cavitation and turbulent cavitation interactions in transient cavitating flow. The accurate identification of cavitation vortex structure is the premise for analyzing the relationship between cavitation and turbulence. 4 different vortex identification methods are used to present the vortex structure for this instance of cloud cavitation. In particular, the Liu-Tex method proposed by Professor Liu can effectively identify vortex structures. The magnitude of local rotation intensity and the direction of local rotation axis are simultaneously represented by Liu-Tex vector, which can more accurately describe the vortex structure for aforementioned 3 typical stages of cavitation flow. This picture shows the colonic vortex structures and corresponding Liu-Tex lines, as well as the distribution of entropy. The gray at the surface indicates the interface between water and vapor, and the vortex structures around the attached sheet cavity are identified by the at the surface with a normalized Liu-Tex value of 0.75. In stage 1 of cavitating flow, the discontinuous vortex structures clustered in the interior of the closed cavity, and the high-intensity entropy located on the surface, especially at the rear of the cavity, which indicates highly intense interaction between water and vapor. As plotted by Liu-Tex vector lines, a straight vortex tube is located at the head of the stable sheet cavity, The twisted vortex tubes dominates the rear of the cavity, where there is a stronger interaction between water and vapor. In stage 2, under the action of the reentrant flow, the vortex structures in the middle and rear areas of the cavity becomes disordered, and is dominated by twisted vortex tubes and U-type vortex. Meanwhile, when the reentrant flow interacts with the cavity as it moves upstream, it motivates the phase change and fluctuations in the velocity field and pressure field, leading to an increase of entropy inside the cavity. For the third stage, the vortex structure is dominated by the U-type, omega-type, and stream-wide vortices. As the shedding cloud cavity approaches the trailing edge of the foil, the vortex legs move away from each other and eventually develop into stream-wide vortices. In addition, the high intensity of velocity gradient caused by cavity collapse at the trailing edge vortex leads to a high entropy concentration in the inner region of the cloud cavity. The entropy represents the magnitude of vorticity, and its transport equation can be divided into 4 terms. In stage 1, the vortex viscosity term and the baroclinic torque term have smaller magnitudes than the other terms. The stretching term makes a positive contribution to the entropy transport, and is mainly concentrated along the interface. The baroclinic term is mainly distributed at the anterior interface of the cavity, which indicates that the pressure and density gradients are not aligned in this region during the growth of the sheet cavity. Additionally, the viscosity term is mainly located at the upper portion of the cavity as a result of the stronger water and vapor interaction. In stage 2, the vortex stretching term and the dilatation term increase with the movement of the reentrant flow. Moreover, the viscosity term are remarkably enhanced, because the dynamics of the reentrant flow tend to promote the unsteady phase change in these cavities, and increase the fluid viscosity and flow unsteadiness. For the third stage, the sheet cavity is lifted away from the suction surface of the hydrofoil and moves downstream as the cloud cavity. We can observably detect that the completed cloud shedding has a more significant impact on the wake dynamics. Additionally, a considerable expansion of the distribution of vortex stretching term can be observed. Furthermore, a relative increase in the baroclinic torque as well as a decrease in the dilatation term appears in regions where the vapor structure has collapsed. On the other side, cavitation flow has the characteristics of stronger unsteadiness and turbulence. We use the kinetic energy transport equation to investigate the cavitation turbulence interactions during the development of unsteady cavitating flow. The comparison between cavitation flow and non-cavitation flow indicates that cavitation not only increases the distribution error of those terms of turbulent kinetic energy transport equation, but also increases the response value. The results also suggest that the dissipation term is much smaller than the production and diffusion terms, so its effect on the rate of change of the turbulent kinetic energy is weaker than that of the other 2 terms. Furthermore, we detailedly analyze the mechanism of turbulent kinetic energy generation and transport. The first stage of the flow cycle is the growth of the attached cavity, where the mean vapor is concentrated on the front region of the hydrofoil. Stronger evaporation occurs at the region of the attached cavity, while the turbulent kinetic energy and each term of the transport equation are quite small, because there is no strong velocity pulsation in the flow field during this stage. In the second stage, the reentrant jet appears from the tail of the cavity on account of the adverse pressure, and gradually advances towards the cavity front along the hydrofoil suction surface. Therefore, the rear of the time-averaged cavity apart from the foil. The evaporation rate shows a consistent trend with the cavity. The turbulent kinetic energy and the production and the diffusion terms of transport equation increase significantly due to the strong velocity fluctuation caused by the reentrant jet. However, the dissipation of turbulent kinetic energy is not obvious. While in the third stage, the cloud cavity region becomes unsteady with the collapse of the cavity, and the intensity of the turbulent kinetic energy gradually increases. These high-value regions of turbulent kinetic energy are located around the shed cavity. The dissipation term occupies the shed cavity region in the cavitation shedding stage due to the viscosity and large velocity vector gradient of the fluid. But this does not happen in the other two stages of cavitating flow. Finally, we take a short conclusion of this work. Firstly, the development of cavitation plays an important role in the formation and deformation of vortices. The detailed development of the cavity and the corresponding vortex structure can be divided into three phases. Stage 1 is the growth of the attached shed cavity. Cavity grows towards the trailing edge of the hydrofoil. Small-scale twisted vortex tubes located in the later half of the attached cavity. Stage 2 is the development of a reentrant jet flow, causing U-type vortices to appear at the rear of the cavity. Stage 3 is the cloud cavity sheds downstream, and the combined effect of the mainstream flow and the clockwise vortices. The vortex structure generally evolves from U-type to omega-type vortices, and finally forms a streamwise vortex. Then, the entropy distribution was used to analyze the dynamics of vortex intensity in the development of cavitation. During the growth of the attached shed cavity and the development of the reentrant jet flow, the high-value regions of entropy are generally located near the cavity interface, particularly at the rear of the cavity region. However, the maximum value of the entropy occurs inside the shed cavity in stage 3. Analysis of the entropy transport equation indicates that the stretching and dilatation terms are dominant during the cavitating flow process. Moreover, the baroclinic torque term and diffusion term gradually reach their maximum values as the cavity sheds downstream, which indicates that the reentrant jet and the collapse of the cavity have a significant influence on the generation of vortices. Lastly, the turbulent kinetic energy transport equation was used to investigate the influence of cavitation on turbulence. The results indicate that cavitation promotes turbulence production, especially during the development of the reentrant jet and as the cloud cavity sheds downstream in cavitation flow, and the effect of the fluid viscosity and the flow unsteadiness. The results also suggest that the evolution of the reentrant jet and the unsteady collapse of the cavities tend to promote intense velocity and pressure fluctuations, which are important mechanisms for the production and diffusion terms. The dissipation term only acts in the cavitation shedding stage as a result of large-scale vortex shedding. Okay, that's all about our work. Thanks for your attention, especially thanks to Professor Liu for his support. Besides, this is my email address. Due to the limited of time, I really hope to have a follow-up communication through email.
Thank you, Dr. Bichan, for the wonderful presentation. Now the stage is open for questions. So, have any questions for the speakers? You can ask. Just I assume that there are no questions from the speakers. Okay. Once again, thank you for being a part in our webinar. Hope you associate with our further events as well. Thank you so much. Okay, moving on to the next presentation by Dr. Sudarshan from BMS College of Engineering, India, and he's going to presenting his talk on a study on aerothermal effects mitigation by forwarding phasing cavity in a hypersonic flow. Dr. Sudarshan?
Yes. You just confirm me. My screen is visible?
Yes. Yes, Dr. Open your open. Yes, yes. Please open in full screen mode.
Okay, yeah. Just check now.
Yes, Doctor.
Okay. Okay. Shall I continue?
Yes.
Yeah, okay. Thank you for the opportunity given by the Aerospace and Aeronautics World Forum. I am presenting on a study on aerothermal effects mitigation by a technique called forward facing cavity in hypersonic flow condition. So, Dr. Sudarshan B, assistant professor from Bangalore, India. So, my content is organized in this way, where I'm talking first about the introduction part, and then in the second part, I'm going to discuss about experimental model and what facility I've used. Then finally, 3, 4, 5, 6 are the important techniques which I have explored in my research. So that I'm going to discuss 3 to 6. Then finally, based on the results, experimental results, I'm going to conclude with the future scope as well as the publications out of. So in the introduction part, the hypersonic vehicles, which you are seeing in the screen, like projectiles, interceptor missiles, space shuttles, aircrafts, re-entry vehicles. So all these actually have to withstand severe heat loads because they fly in very high speed of the range, Mach number more than 5. So hence, the heating and the material ablation are some of the critical problems which leads to uncontrolled perturbation of the vehicle and leads to failure of the vehicles. So in this direction, in the recent time, if you see the first graph, so till 2010, the data has been the flight velocity is increased tremendously. If you see the figure 2, this one, so we can see space shuttle goes of the order 7.5 kilometer per second speed, and all Concorde aircrafts and X-43, X-15, all these of the order of kilometer per second. So hence, our requirement of higher speed has been increased. The penalty is, you can see in the right side 2 diagrams, the heating rate is tremendously increases from, so heating rate in terms of kilowatt per centimeter square, just by changing velocity from 3 kilometer to 6 kilometer per second, there's a huge jump in the heat flux. Okay, happening at very fraction of time. So at the beginning itself, this high heating rate leads to failure of the vehicle, and there is an enormous density gradient over the altitude. So by aerodynamic, the simple boundary layer theory says the wall heat flux, which is actually proportional to velocity in the power of 3. Hence, as we increase velocity, wall heat flux will be very dominant. It has been reported in the literature that if we have a vehicle, hypersonic vehicles, its nose will lead to exponential increase in the heat flux as velocity increases. So I think it's you can see the right side. So construction number increases very high, and as altitude goes for a different velocity conditions, there are different effects, real gas effects going to affect. For example, to depict one, for a velocity about 8 to 10 km/s speeds, for an altitude about 50 km, we can see the air-assisted orbital transfer velocity vehicles comes under the effect of ionization, radiation, and strong real gas effects, as well as low density effects. So just I want to emphasize that as velocity increases at a different altitudes, the hypersonic vehicles affected with a lot of different effects. So, and for example, recently in 2003, the demise of Space Shuttle Orbiter Columbia. So it's very well a reminder how aerothermodynamic environment, hostile environment under higher velocity condition. So to address this, there are different techniques has been explored by the researchers, passive, semi-passive, and active. For the hypersonic vehicles, majorly the ablation technique is in use, and some researchers they have explored transpiration cooling and film cooling. So recently in literature, it has been mentioned forward-facing cavity, energy deposition technique, and combination techniques. For example, the forward-facing cavity with upstream energy deposition, or forward-facing cavity with opposing jet, and spike with opposing jet. These different combinations has been reported in the literature. So I am specifically exploring on forward-facing cavity technique, where it has been already used for different purposes. But in this, my research work, I am exploring for peak heat flux controlling technique for hypervelocity projectors. So it has been used in sounding rockets, acoustic generator, and active flow control actuators, and sonic energy and chemical engineering processes. So in the perspective of heat flux controlling technique, I'm going to present. And in the same perspective, the literature has been explored for about 100 years data, where at the beginning from 1918 to 1979, so majorly on mechanism aspect of the forward-facing cavity, which you can see in the left side. So there is a nose surface, and there is a cavity, and these are all different sharp lip, shock oscillations, and a nose surface, cylindrical cavity. So only on the mechanism aspect has been explored at the beginning. Later on, from 1987 to 1998, so different parameters like what should be the length, what should be the diameter of the cavity, what should be the radius of the nose surface. So these, and also because of shock oscillations, what is happening on the nose surface? So those things also has been explored in the later time. In the 2000 to 2009, there are some optimization aspect has been reported along with the energy deposition technique as well as some ablation related studies. Recently, from 2012 to 2017, some combination techniques, which I told in the previous slide, like opposing jet and forward-facing cavity, and also the different geometry paraboloid and ellipsoid cavity geometry also has been reported. So after reading all this literature, we found that so there are still there is a scope to, there is a gap in the explorations where what exactly happening in the cavity region it is exposed to such a higher speed condition has not been explored, and L/D ratios is not very higher L/D ratios are not being explored, and also so cavity geometry is more or less on the cylindrical geometry and very few on computation. And energy deposition upstream has been reported, not at the downstream of the shock position. And opposing jet combination is reported for very low preservation. So to address all these with these motivations, to address these four important problems, so objectives of the current research has been so energy deposition and higher L/D configurations and high pressure ratio injection and changing the parabolic, cylindrical cavity to parabolic and ellipsoid kind of different geometry. Here we have explored parabolic geometry. With these important 4 objectives, this current research has been explored, and which I am going to share the details. We have designed the model considering the literature, where literature has been explored from 6 mm to maximum about around 5 cm. So taking our shock tunnel conditions, we have explored a 2 mm diameter with a preliminary safety study. And L by D length also, it is reported from 0.85 to, we have restricted to 4. And L by D should be greater than 1. And D by Rn, this is nose radius and diameter of the cavity. This parameter should be greater than 1.5 for stable oscillations. And Mach number should be more than 3. So then we will get a stable oscillations. So considering all these reported literature conditions, we have designed our model. We have considered the preliminary computation studies for our shock tunnel conditions. And we come to know that for a 1 millisecond test time, there are 3 oscillations are happening for 12 mm diameter. And we checked it both temperature and pressure variations. So there are 3 oscillations are happening. With this preliminary data, we started designing the model. So model looks like this, where, so this is the experimental model, how exactly it looks like this. So there is a cavity, and this adjustable plunger, we can move it either towards the left, towards the right to set the particular L by D ratio. And then L is length of the cavity and D is diameter of the cavity. And inside the cavity, there are sensors. And on the plunger head, there is a pressure sensor. And over the nose surface, there are a number of thin platinum sensors. So through thin platinum sensor, cavity region and nose surface region, heat flux are evaluated. And by the pressure sensor on the plunger head, pressure variation in the cavity region has been investigated. So this is how you can see different wire connections and thin film sensors, and over the nose surface, how it has been formed. And this is the plunger, how it looks like. So with this basic aspect, so let's see the experimental facility part. I've used a shock tunnel of shock tunnel and a free piston shock tunnel to reach higher flow enthalpy conditions. So here we have reached 1.2 megajoule per kg Kelvin, and here we have reached 3.4 and 5.4 megajoule per kg Kelvin high enthalpy conditions. Correspondingly, Mach number increases. So here it is of the Mach number 6, and here we are going to the Mach number 10 and 11. So those details will be shared. And I think aerospace community is well aware how shock tunnel is basically works. So I skipped these 2 things because reflected mode, straight mode is well known. And using simple compressible relation. So the free stream conditions, P infinity, rho infinity, T infinity, and V infinity can be calculated. So this is for the straight through mode. So we have used basically both the mode conditions based upon the requirement. Okay, so technique of higher cavity length, where, so for the Mach number 6 we have worked out, L by D 1 to L by D 4 we have checked it. Explain this technique in detail so that later remaining 3 techniques will be, I can go a little bit in a higher pace. So we measured heat transfer through 1D semi-infinite principle, where the platinum thin sensor will see the heat flux available at the infant of it. So using Cook and Felderman relation, by knowing beta and alpha, which are all the property of the Meccar substrate, and alpha is the property of the platinum thin film, we can, by knowing the voltage differences by the measurement, we can calculate what is the heat flux available at the in front of the or over the platinum thin film sensor surface. So by knowing that, we can normalize in terms of standard. And this is how we have prepared the thin film sensor in-house in Institute of Science, and we have calibrated both the Meccar property and the thin film sensor property. You can see here, this is for cavity sensors, this is for no surface sensors. So you can see clearly that how thin film sensors have been encountered. And first we have tested the run test. The run test, that means in a shock flow, we should get cavity flow oscillatory kind of flow situation where we can measure the its enthalpy. So you can see here, this is the pressure sensor nozzle supply condition. It shows that so much reservoir is existing in the shock tube. And this is the pitot test time. It's about 1 millisecond. And in the 1 millisecond, we are getting the run test time of base pressure oscillations. This is the oscillation sensed by the sensor installed inside the cavity base. So we can clearly say that in a nozzle reservoir condition, we are getting a pitot steady time. In the pitot steady time, the oscillatory flow is happening in the because of the forward facing cavity. So same thing has been done for different L/D conditions, taking cavity base pressure sensor into account. So L/D1, L/D2, L/D3, L/D4. So finally, you can see here for a pitot steady time of 2900 to 3960, all run test time is in between. I mean, run test time lies with, and till L/D4, we are able to do the experiment. If we go to L/D5, it is going out of our pitot steady test time. Hence, we restrict it to L/D4. And I will just show you a video for L/D1. You can see the shock oscillation, and for L/D2, you can see it becomes very slow. And these are all captured at the run test time condition. For L/D3, you can see it become much more slow, and L/D4 it is very, very slow. We may get only one oscillations. So now we quantified these oscillations, shock standard distance in front of the model. So shock standard distance increases as L/D increases, and the frequency is decreases as L/D increases. Very well known from the video also. And then pressure measurements also, we checked it. Base pressure keep on increases as L/D increases, and we evaluated without cavity condition is well matches with the reported experimental results, and also with the analytical results also. Whatever we have measured, it is almost closure. So by evaluating the blend body, we went with the cavity model run test time heat transfer variations. You can see here in the run test time for L/D1 to L/D4 how exactly signals we have captured, and this is what important. Blend model without cavity condition, because of the cavity L/D1 to 4, you can see how gradually it has come down in terms of Stanton number, and then you can see here there is a kind of oscillations. It shows that there are vortex recirculation. I mean rotating bubble, so it is sitting over the nose surface. When it is under L/D4, there are two vertices are formed, primary vertices and secondary vertices. For L/D3, there are only one vortex is sitting over the nose surface. Whereas inside the cavity, for L/D4, you can see in the column, for L/D4, at the near to the cavity base, there is a very high heat flux. And before that, there is a vortex ring is sitting inside the cavity region. Whereas for L/D3, only vortex ring is sitting. There is no stagnant fluid lying inside the region cavity. So this we have reported for the journal, and it is got published. So it when we go to L/D4, there is a stagnant fluid sitting inside the cavity base region, get accumulated, and augmentation of the heat flux taking place within the cavity itself. It is not participating in to and fro oscillatory flow condition, which fluid get filled inside the cavity and come out of the cavity. So that is not going to take place for L/D4 because of stagnant fluid near the base. We also cross-checked with the computational simulation. Second technique we verified with, as I said, upstream heat deposition has been reported, but we worked out with inside the cavity. We dump the heat by chromium plating, chromium coating, and this heat pushes the shock very far away. So this we checked it for very high enthalpy conditions. As I said, Mach number 7.5, 10.9, and 10.2, which leads to 2.2, and 3.2, and 5.4 megajoule per kg conditions. This is a novel in its nature because we have tried first time this kind of technique. So these are all arrangements, and Mach condition I have already. And shock standard distance you can see here for a enthalpy 1, 2.2 megajoule per kg. So green indicates the blend body, and you can see with chromium blue color it's having a rampant high amplitude oscillations. And here also very high amplitude oscillation for enthalpy 2, 3.2 megajoule per kg Kelvin. For 4 megajoule Kelvin, you can see shock is moving very much far ahead of the model. These are all measured in the run tested conditions. So then frequency of oscillation, we also compared with the theoretical. You can see here, the frequency of oscillation comes very, very down for the chromium coated conditions. So by this, heat flux measurements, when we measure over the no surface, you can see clearly that for a smaller enthalpy, there is not much change. Higher enthalpy, you can see this purple color with cavity with chromium coated, heat flux distribution coming very, very low, significantly low compared to the blend one. So here for a 5.4 megajoule condition, you can see very lower compared to the blend. So it's very clearly show that from 13% to 49% heat flux reduction is happening when we use the energy deposition technique. So similarly, we have tried, it's a morphological study, chemistry study we have carried out. The specimen which we have put inside the cavity has been taken for the XPS photoelectron spectroscopy studies. You can see clearly here for different enthalpy conditions, the peak changes. So this is for the without, without coating, and this is for enthalpy 1, enthalpy 2 condition, 3.2 megajoule, this is 5.4 megajoule. So when we deconvoluted, we got what different species are being formed. This is for the chromium, this is for the oxygen, and this is for the nitrogen. And we have tabulated what different species are formed over the model because of chromium exothermic reaction. We quantified that those are all exothermic of enthalpy, which has been quoted here. And the reactions, what are all happened because of high enthalpy conditions, that also we have quantified and published in Physics of Fluids. Second, third one, so high pressure jet is injected from the cavity base, facing with cavity combination has been explored. So here, these are I'll skip, directly go to the result part. So you can see here, because of high pressure jet, there is a formation of two mark discs in front of the cavity, and shock is pushed very, very far. So whereas we also tried with parabolic cavity, so parabolic cavity has not pushed so much far. So shocks and applications you can see here with reference to the blue line blend body. So green is parabolic cavity and yellow is for cylindrical cavity. Shock is pushed very much far away from the model. Due to this, there is a higher heat flux reduction near the cavity lip region. You can see here with injection parabolic cavity green. So near to the lip region, very higher heat flux reduction is observed for the parabolic cavity with injection. We have also tried a parabolic cavity, changing the cylindrical cavity for 3 enthalpy conditions. So I can show you cylindrical cavity oscillations looks like this. Whereas parabolic cavity shock is pushed very much far away, but oscillations are not so much rampant as happening for the cylindrical cavity. So when we test time evaluation in the same way it has been done, has been calculated. It clearly shows that with reference to the blend body, shock stand-up distance is increased 10 to 30%, whereas only cylindrical cavity means it increases till 70.43%. So cavity helps very much as enthalpy increases, shock stand-up distance increases, correspondingly heat flux distribution reduces to no surface. So base pressure also is reduced for the parabolic cavity, frequency also is reduced, and you can see here heat flux distribution as enthalpy increases, the green color parabolic cavity, no surface heat flux distribution coming very much lower compared to the blend body and cylinder. This also we have published in the journal. The conclusion to change the flow nature and its effect on the no surface as well as cavity surface heat flux are being experimentally investigated for different conditions. It's seen that cavity fluid pushes the shock downstream for higher values and from oscillatory flow with the lower frequency and higher amplitude. And correspondingly, you can see for higher LVD conditions, increase from 12 to 35%, and correspondingly heat flux distribution has been reduction has been increased to 29 to 54%. And when we have energy deposition, shock stand-up distance increase 50 to 35%. Correspondingly, energy convection heat transfer is reduced from 13 to 49%, and the XPS study showed that there is a formation of nitrates inside the cavity. With high Pressure ratio also short standard distance very significantly and led to parabolic cavity very significant reduction of 35%. So for different geometries also, as enthalpy increases, the heat flux reduction is increased for the parabolic cavity, and parabolic cavity work well. So when we compare together parabolic cavity as well as energy deposition, you can see here for enthalpy 2, 3.2 megajoule condition, and this for 5.4 megajoule condition. So you can see blend, blue color is energy deposition, here also energy deposition technique, and red color is for parabolic cavity. So with reference to the blend body at higher enthalpy condition, both energy deposition technique and parabolic cavity technique are giving very good heat flux reduction compared to the cylindrical cavity, and this can be explored for the space applications. So there are plenty of recommendations can be worked out using parabolic cavity chromium coating, and this has been published, as I said, in 4 different peer-reviewed journals and presented in different international conferences and even national conferences. So I'm thankful to my guide as well as the professors who have helped me, as well as my lab members. This is my lab people and professors as well as my colleagues. These are all different references which I have referred. Thank you. So I'm open for questions.
Okay, thank you, Dr. Sudarshan, for the wonderful presentation. And now the stage is open for questions. So having any questions from the speakers, you can ask now.
This is Lakshmi Sankar from Georgia Tech. I hope you are able to hear me.
Yes, sir. Yes, sir. I'm able to hear.
Yeah, it was a very, very good presentation. Very interesting to say how the 3 ways of measuring, came up nicely at higher X over R, larger distances. But there were some discrepancies up in the front. I'm sure you're looking at it. And also I was wondering.
Could you tell me which exactly?
The last figure, you showed that 3 ways of measuring, and they agreed well at the larger distances downstream, at higher X over R. Yeah, the middle curve, for example.
Okay.
And there's some differences in the earlier X over R. And it'll be very interesting to see, where it's coming from and understanding it.
No, actually this difference, there are 3 curves here. One is blend body, and second one is cylindrical cavity, and third one is parabolic cavity.
Yes.
There are not discrepancies. 3 geometries results have been plotted.
Oh, I see. It's 3 different geometries. Okay.
Yeah. So I have compared parabolic cavity with cylindrical cavity conditions.
Okay, great. Thank you.
Yeah.
Okay. Any other questions? Dr. Sudarshan, thank you for answering the questions.
Yeah.
And once again, thank you for being part in our webinar, and hope you will associate with our further events as well.
Sure. Yeah. Thank you.
Thank you so much. Yeah. So now you can stop
sharing. Yeah.
Yes. Okay. Thank you. And moving towards the next presentation by Sergio Montenegro from the University of Würzburg, Germany, and he's going to presenting the talk on CUBE venturing new technologies in space, wireless satellite, and storing energy in the structure. So, Dr. Sergio. Doctor, can you please talk a little louder?
Okay, I hope you can see and hear me clearly. Yes.
Now, yes.
Okay, then I have to talk very loud. Okay, then I would like to thank you for this opportunity to present our CUBE project. It's funded by the German Aerospace Agency, and it's a cooperation from 2 universities in Germany, the Technical University of Berlin and the University of Würzburg, where I am working at. Okay, from outside,
Dr. Sergio,
yes?
sorry for interrupt you. Can I share the screen?
I have no screen sharing.
Can I share the screen? I think you have provided.
Now it's okay?
No, doctor. Your screen, your complete screen is not visible here.
Yes, I have only this presentation and no screen sharing.
Yes, yes. You have to share this
It's
presentation.
okay, or shall I try to do it in another way?
So, Doctor, I have your video. So, shall I present it now?
Yes, then present my video, please. Sorry
Okay.
for the.
Thank you, thank you.
Okay, then
please,
present my video.
Yeah, please give me a moment.
It worked. It worked at my video.
Sorry.
It's Christian back. The presentation. I could see the presentation.
Mm-hmm.
Yeah, I was also
now when you interrupt, I can see the ones that speaks.
So as you want, I can continue here, or you can show the video as you want.
Okay, okay.
Please tell me.
I'll play the video on behalf of you, Doctor.
Okay,
please,
I'm going to stay here ready for questions.
Yes, yes.
There is no video. Good morning, I am Sergio Montenegro, and I would like to thank you for this opportunity to present our InnoCube project. InnoCube is a small satellite which is a cooperation from the Technical University of Berlin and the University of Würzburg, where I am working. It was funded by the DLR, the German Aerospace Agency. Well, InnoCube is a 3U satellite. It's in this size. If you look from outside, it seems to be a quite normal satellite. Seems to be nothing special, but there are two very special things inside of the satellite, which I am going to show you next. But first, let's see the content of the satellite. This is the 3U structure. On the top, we have retroreflectors, which is going to be used to find the satellite using laser ranging to determine the orbit in very precise way. Then we have here antennas. We have the transceiver for communication to get commands and send the telemetry from the satellite. And something a little bit special, we have an ORCOM modem, so we can communicate with Earth using other satellites as relay satellites. Then we have the power distribution unit for Wally, which is going to be explained later. We have the board computer, we have some batteries, we have the power unit, we have an attitude control box, and we have an GNS receiver. First, let's take a look to this attitude control box. It's a very nice thing. This is a small box which includes everything which you need to control the attitude of small satellites. We have 3 wheels, here you can see, and 3 magnet torquers. We have a IMU to measure the magnetic field of the Earth and to measure the rotation speed, and a computer node. So everything is built in this box, so we can take this box as is and install in different types of satellites, and then you have your attitude control in the box. So a very nice concept. But that's not the very special thing of InnoCube. So what is special? I said before, we have two very special things in InnoCube. First, it's a wireless satellite. So inside we have no wire, no harness for the communication. Everything is done using wireless. And the second thing is we store the energy in the structure. We have still batteries because we are not very sure if it is going to grow properly. So we have batteries as backup. But if it works, then we can build satellites without batteries. The energy will be stored in the structure. First, let's talk about the wireless satellite, which is the contribution of the University of Würzburg. Okay, why do you want to build a satellite without harness? Okay, harness is a very big problem. It's very complex, it's complicated. Sometimes it's very difficult to find errors, wiring errors in satellites. I have seen cases where you are looking for weeks and weeks until you find where is the wrong connection. Okay, it's difficult, it's not so simple to make these interconnections, it's very expensive, it costs a lot of time, it's heavy, and it's error prone. Because of the vibration of the launchers, we can lose some connections and then the satellite can go lost. If we don't have harness, we don't have these problems. These are some examples of how complex and how difficult is the harness. This is in helicopters, this is in small satellites, and this is in bigger satellites. So you can see how many wires we have. And a very nice example is from a very big satellite. Here, these three workers are almost flying, they are hanging to make the last connections of the satellite, because these are on the top of the satellite. So you can imagine how much work they have to invest for these last connections. Okay, and these are problems which we can avoid if we don't have harness. Another thing is harness is heavy. Let's see about the weight distribution of components in a typical satellite. For example, we have the payload with about almost 20% of the weight of the satellite, and this is very, very good already. Then we have the structure with about 21% of the weight. And this is another important thing. We can use this 20% to store energy, and then we can save batteries, space, and weight. Then we have a thermal control with about 30%, and attitude control with about 8%. And so if we continue, we are going to find at this position the harness. About 10% of the weight are only wires. And maybe you know, to bring spacecraft in orbit is very expensive. You have to pay many thousands of dollars of euro for every kilogram you want to bring. So for every kilogram you save here, you are saving thousands and thousands of euros or dollars that you want to count. Okay, what is the situation? This is yesterday for telephony, this is today for telephony. In space, that is today, and this is tomorrow, where we want to go. Maybe you remember, some of you can remember this kind of telephones. We have many wires. For each telephone, there was a dedicated wire to a box to distribute. And then we have such a mess of communication network. Nowadays, we have something like this. There are no wires. And if you want to install a new device, you just turn on and it will integrate it in the wireless network. So much more simpler, and you can have millions of devices which you cannot have here. So even if you don't have wires, it's better to scale. And now today, this is the typical case of satellites today. You have a lot of wires, so you can see from every box to every box you have a wire or many wires, and this is what we want to do in the future. So no wires, and do the same. And now this is a very nice cartoon. It represents the situation which we have. The boss says, okay, good news, we won the bid to build a national-wide wireless network. And then the employee says, bad news, we don't know how to build a national-wide wireless network. And then the boss replies, it's wireless, how hard can it be not to install wires? And that is the truth. If we don't install wires, we don't have problems in the hardware. The problems are in the software, somewhere else. Okay, you know how much effort, how much research is done in communication using wires, and we have to do now all the same real-time communication with the wires, and then to demonstrate in space in a real satellite. And this is what we are doing now in the project InnoCube. But first, before we go to space, we want to demonstrate it on Earth. For this is the fire test on Earth. We built a wireless quadrocopter. So, you know, a quadrocopter, we have 4 propellers, and normally you have in the center the control unit and some wires to control the motors and sensors. In this case, the center is empty. Everything is here on the arms of the quadrocopter. So you can see in each arm we have a battery, we have a motor controller, and we have a small computer. And these computers are communicating all together to compute the current attitude and take common decisions how to control all motors to reach the required attitude and make the maneuvers we would like to have. So this communication is very critical, because if something was wrong, then one motor is going to be doing something wrong, and then the attitude will be lost, and we have a crash very fast, and then you can see very fast something is going wrong. Okay, this is a communication cycle of 3 up to 5 milliseconds, and in this time we have to measure all sensors, take the decision how to control and communicate with the local motor. And this is done all wireless. We have demonstrated this for a long time. This quadrocopter is flying a long time without crashes. So we know our communication system is working properly. Okay, now it's demonstrated on Earth. Now the next step is to demonstrate in space. Okay, it looks like this. These are the communications modules. They are very small. If you compare with the size of this communication module with a typical avionic plug, you can see the weight is much more less and is much more smaller. So you are saving a lot. It's true, you need a little bit power for the communication, but here you need power too. So it's not for free. So if you are changing the polarity of so many wires, you need to invest some power to drive this wire. So the power consumption is there, but here too. And then we have this module, which is about 3 centimeters per side. And this can be included in every device. And inside of this module, we have a small computer. So this module can be already the board computer of the satellite for simple small satellites. It looks like this. So we have an ARM processor attached to a radio communication link. And this can be done for computation or as interface to other devices, because we have here SPI, E2C, UARTs, and many other interfaces to connect to any other device. So, and we have many of these in the same satellite, and then that is the communication without wires. On the software side, there is something to do, of course. We are using our real-time operating system Rhodos, which includes a middleware. And this middleware is a published subscriber middleware. In every node, we can have several applications, and these applications are publishing data using topics, and any other application can subscribe to a topic and get a copy of the published messages to this topic. This works very nice locally. Now we go outside of the node. For this, we have these gateways. These gateways are listening to all topics, and when they recognize something which shall go to other node computer, then we copy this and send it to the local radio communication link, and the other is going to receive this data from the radio communication link. It will compute it for me, and then it will be distributed locally in these topics. So any application in any node can communicate with any application in any other node or in the same node. So the communication is transparent. Any application doesn't need to know is the communication partner in the same node or is in other nodes. So it's transparent for the communications protocol. Okay, and this is the typical structure of a normal small satellite. You have a board computer, and this board computer has a lot of interconnections, and they are many different connections. So some are CAN, some are I2C, SPI, UARTs, or who knows what, and then you need many interconnections. If you change something here, you add new wires, you add new connections, then you have to modify the board computer because you will need new connections. What we are doing now is we remove all these wires and we use only for every device an interface to the wireless communication. This is what we call our SCID module. And the board computer are used for of these SCID modules. We don't need extra computer because inside of these modules we have already a small computer, and using for we can have enough power and memory to control the satellite. So you can see there is no wires anymore, and to add a new device, just bring it to the satellite and that's it. You don't have to make new interconnections, very simple to do. And something very nice, the external diagnosis. Maybe you know from enterprise, if someone is sick, then the doctor comes, they call a recorder, then look, and the recorder makes beep, 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 and then the doctor can see, what's the problem and what to do. Without having to make any connections, just coming with the recorder, and then you have the data. Okay, in the satellite, we can do the same, because we don't have wires, and the signals are not going to end on the physical boundaries of the satellite. We can have an external receiver. We come close to the satellite, and then we can see all messages going inside of the satellite, and we can do an external diagnosis without having to plug anything in the satellite or opening and seeing what is going on. And something very important, we need a time trigger protocol because the communication has to be in real time. and it has to be secure, safe. Okay, what we are doing is we have a director, and this director is going to distribute a schedule when everybody shall send. This schedule is distributed periodically, and this is a few milliseconds. So for every big cycle, the director distributes the schedule when shall communicate each node. This is first node 0, then node 1, and so on. And we know how long shall be the slot for each node, because we know how much communications we are expecting from each node. So we are sending this schedule, and then the messages it shall distribute. Then the next node is waiting to the time from this schedule. Then it begins sending until give enough gap to allow the next node to begin in his slot. And so we are doing this, and this is going to be repeated maybe 100 times per second or 10 times per second according to the requirements of our satellite. Okay, now there is something very important. We need one director. One director is very good, everything is properly. If we lose the director, then we lose the satellite. Or if two directors are working at the same time, we have chaos. So we have to implement something to be sure we are going to have only one director or conductor of the orchestra of the satellite. So, and therefore, this director, this conductor is attached to the power distribution unit. We have two of them for redundancy, and the power distribution unit has different types of power control. We have some lines which you can turn on and off, and it is going to stay on and off as you said. And then we have keep on and keep off lines. When you say a keep on, it will be turned on, but only for a period of time, maybe 1 second. If you want to keep this on, then you have to repeat keep on, and keep on. If this signal is not coming, then this line is going to be turned automatically off. We have the opposite, keep off. These devices are going to be turned on automatically, and to keep it off, you have to send in less than 1 second the signal keep off, keep off, keep off. And this is what we are doing now for this communication to be sure we are going to have only one and exactly one director. Okay, if there is only one, then there is only this way to do. But it's not so bad. This bullet, it doesn't kill the other director. It keeps him sleeping only for 3 seconds. So how it works? First we get power, the satellite will be started, then everyone is going to wait for a random time. This is a true random generator, so every time will be different. Then one is going to be activated first, and then it sends the signal keep off to the other, and then till this will be turned off. You keep sending keep off, keep off, keep off, as long as everything is going properly. If this crashes, then the signal keep off is not going to come. In 1 second later, this will be activated, and the first thing it will do is send and keep off to the other, and the other is going to be turned off, and then stand off until this fails. And as long as this is working, this keeps sending the signal keep off, and the other is going to be turned off, and so we can be sure we have exactly one node at one time to control this. Okay, we are ready to fly. We made a radiation test, and the results are very promising. We went up to 47, almost 50 kilorad, and everything was working properly. So for normal satellite in this size, less than 10 kilorad is enough for 3 years in orbit or maybe 5 years in orbit, but we demonstrated we can almost 5 times higher than this, and all devices survive the expected radiation, 5 times the expected radiation for such satellites. Okay, the other important thing, special thing, is storing energy in the structure. This is done by the Technical University of Berlin. Okay, what we want, using the load-bearing fiber composite structure to store the energy, something like this. I'm going to show that in a few moments. Okay, the background, this fiber is being increasingly used in satellites and in other aeroplanes and other structures, because in terrestrial applications too. And the advantages, if we store the energy there, we can save up to 50% of the mass, because the the batteries are one of the most heavy parts of the satellite, and beside us, we don't need separated batteries. We have a considerable volume reduction. The room from the batteries you can use for something different. And now the challenge is to store sufficient energy without reducing the structural characteristics of the structure. Okay, and this is how it works. We have different layers with different materials and some contacts to store and receive the energy. And the structure will look like this. Here in this structure, we have these 3 layers, which are enough to store the energy and for the structural stability of the device. Okay, and this is going to be tested in this direction. We have 6 of these, 1 per side of the cube. And then we have the power generator from the solar cells. We are going to store the energy in all sides of the satellite, and then we are going to measure how much energy we can store and take using some resistors. And this is going to be done for a long period of time, so we can know if we know it works on ground, but we want to know how it will be working in space. So to conclude, I would like to say danke, also thank you very much. And if you have any questions, I will be glad to try to provide some answers. So to conclude, I would like to say thank you very much. So if you have questions, I'm ready to answer.
Yes. So thank you, Dr. Sergio, for the wonderful presentation. And now the stage is open for questions.
Hi, Sergio. Rafael speaking. I have a question. What is the level of space qualification of all these innovations? Because we all know that very good things can work on Earth, but maybe not in space.
Well, let's say we have qualified everything already on ground. We have not demonstrated it in space. We are going to fly in 2 years or 1 year and 6 months, and then it will have a TRL of 8 or 9. But at the moment, we know everything is working properly in labor stress. Everything is done. Radiation is done, so we are ready to fly. If this is what you asked.
Yeah, I was asking a qualification in relevant condition like space vacuum and temperature and so on.
Yes, the qualification in labor is done. We are ready to fly.
Okay, thank you.
Any other questions? Okay, thank you for answering the questions, Dr. Sergio. And once again, thank you.
Yes.
Yeah, thank you for being part in our webinar. Hope you will associate with our further events as well. Thank you so much. Okay, and the next presentation will be by Mostafa Taflo, but I think he's currently not available at this moment. So we will proceed with the next presentation. And the next presentation will be by Rafael Jaja, and he's from France, ISAE Supero, and going to presenting the talk on sensing of atmosphere density at the border between atmosphere and space, potential of drag and torque sensing and science applications. So Dr. Rafael?
Yeah, thank you. I'll try to share my screen.
Yes, yes.
Okay, do you see my screen?
Yes, yes, Doctor.
Yeah.
So please proceed with your presentation.
I may close my video. My bandwidth is not great. Yeah. So okay. So thank you for giving us giving me and these 2 students that are working on these topics the opportunity to present this work. Okay. So what I will speak about today is the sensing of atmosphere density at the border in between atmosphere and space. And discuss a bit what are the potential of drag and torque sensing and what are the science applications. So this is an overview of the talk, but I have already too many slides, so I will go fast. Okay, first, as an introduction, forces applying on a satellite. So you know that a satellite is subject to various forces. So There is a gravity field, gravity gradient, external forces, solar radiation, albedo, drag, among these. But also magnetic forces due to residual or control magnetic moment, in particular in low Earth orbit, and also attitude control mechanism. So the effect of these forces can be felt by variation either of the satellite accelerations. And for this, we have a very good example, which is this Gautier mission. I will talk about this in the next slide. And also you can sense these forces in variation of satellite rotations, because if your center of figure is not at the position of your center of mass, you will have the drag will exert a moment on the satellite. So I will discuss this in more detail later. So in terms of drag monitoring, we had this wonderful ESA mission, which was Gautier mission, which was a drag compensator platform designed for gravity field measurements. So the basic principle of this platform is that you have thrusters that are pushing as much as it needs for the satellite to compensate exactly the drag. And this is absolutely necessary for the 6 accelerometers that are inside the satellite to measure the gravity field gradient. However, by doing this drag compensating platform, you can already read the air density or the drag coming from the air density directly on the thruster push. And plus, if you have the information from the accelerometers, you can even deduce lateral winds cross track. So my colleagues Ilko Donbos from Delft and Shen Brisma from CNES made a lot of publication, and they produced a lot of air density models from this data. So it's a clear demonstration. So you have here an example comparing the MC's model to the Gautier derived density, and it was working quite well. In addition, you can also monitor the gravity wave activity at the altitude of Gautier, which is about 270 kilometers. So we published a paper by using both air density and the measurement of the accelerometers. You can see where you have gravity waves at this altitude. And finally, this was a kind of hit for me. So we detected a quake and tsunami following the large Tohoku quake that unfortunately created the Fukushima nuclear plant issue. However, the quake was so strong that it generated air density perturbation, and the satellite crossed the wavefront of these acoustic waves generated by the quake. It crossed it 2 times. So it crossed it the first time in the Pacific, and then because the satellite is going faster than the seismic wave, so it doubled it above Mediterranean Sea approximately. So we had 2 signals from the seismic waves coming from the quake, but we were also able to see the gravity waves created by the tsunami. You know, the tsunamis are coupling with gravity waves in the atmosphere. And so Gautier felt in air density and in accelerations these gravity wave signals that you can see here. So overall, Gautier mission demonstrated a lot of things. It demonstrated the interest of having a drag compensated platform for an high precision accelerometer for atmosphere monitoring. However, this mission had some drawbacks that are limiting such missions. So there was no other Gautier, there was no Gautier 2. And the main reasons are the following. First, it's a large cost. Why? Because you need very precise accelerometers that were done by Uta Rnr here in France. But you also need a very precise thrust because the push of the motor is compensating the drag, and so you must push very precisely the exact amount to compensate the drag. And you need this thrust over a large range of thrust values. So this is quite complex. Also, the concept of drag compensation inside the satellite is a bit complex. So what I will try to demonstrate today is that maybe drag torque monitoring may be a better option in terms of cost and in terms of complexity to recover the atmosphere density. So in fact, this drag torque compensation was not performed in Earth orbit, but it was performed in the last orbits of Venus Express. So what they've done during the last orbit is that they change the center of figure and the center of gravity by rotating solar panels in this position. So one solar panel facing the flow and one solar panel parallel to the flow. And what they've just done, they read the reaction of the reaction wheel. And you know the control torque that is exactly compensating the rotation of the spacecraft. And what you can see on the right is the type of density that were recovered by using either the reaction wheel and the torque experiment, or by using the accelerometers on board the spacecraft. And so you can see on this particular platform that the torque experiment allowed to recover lower densities in the orbit in the atmosphere of Venus than the accelerometers. So it's already a good sign that maybe you can do better with torque and reaction wheels than with drag force and accelerometers. So I want to mention that there is already existing concept to apply this in CubeSat. So you may have understood that if you want to reduce the cost, you want to go to CubeSat. There was this paddle wheel concept that was designed but not implemented in this particular paper. And there is also this spacecraft, SOAR, which is from Manchester, that is targeting different objectives, but it's also using large deployables with a motor allowing to rotate this deployable. So what we've done here at ESA SuperAero is before trying to implement such kind of things, we need to demonstrate, at least on paper, it's working. And so the idea is to play with this equation, which is a torque equation, in which you have the rotation speed of the satellite, the inertia matrix, and the rotation acceleration. And this sum should be equal to the torques. And you have various types of torques, so the drag, the gravity gradient, the solar radiation, the Earth albedo, the residual magnetic torque, and here the control magnetic torque. So the first slide I will present were published in a paper asking if CubeSat are able to sense the atmospheric densities with torques. And for this example, we used a simple 3U CubeSat that we designed and launched at ESA SuperAero. And in fact, all this equation can be modeled as soon as you know all these parameters. And among these, the one we try to recover is the air density. So to do simulations, we implemented a full modeling tool in Simulink, and we tested various attitudes, either fixed attitude, or we can let the attitude vary due to dynamics in uncontrolled matter. So what we do within this tool is that for a given attitude, we compute the torques in a realistic atmosphere, and we try to also manage the error bars due to the satellite component or the attitude knowledge. So one output of this study is first the torque magnitudes, how they vary for this type of platform. So you have two different attitudes when the 3U area is facing the flow or when the 1U area is facing the flow. And the drag torques they are mentioned here, you see that they go over the residual dipole, magnetic dipole torque, only in a range which is usually below 300 kilometers. Why? Because the difference in between the center of figure and center of mass here is quite small for this particular example. And you see also that if you face the 3U area instead of 1U area, you increase a lot the drag torque. So then what we try to do is to have an error budget for this. So as you see in the design of our EntriSat 3-unit spacecraft, we did not add a dedicated subsystem to do such kind of experiment. So we have large errors on the orbit on the position of the spacecraft, but also on the attitude and the angular accelerations. And I should mention that the mission duration was quite short because we faced a radiation failure a few weeks after the launch, and so we are not able to perform this on real data, but I will present you the simulated data. So what we've done, we've produced data plus noise, and then we compute the theoretical torque, and we try to extract the value of the density by inverting again the data. And what you see here is what we ingested as a real density, and what we recover in blue by adding all these error sources, either at 200 kilometer altitude or at 300 kilometer altitude. So you see that with this particular platform, we can expect only to recover the density around 200 kilometer altitude, and again with a large, quite large error bar. However, what was interesting in this study is that we made a sensitivity study on the various parameters that we need to do this experiment. And what quickly come is that we need to have a very precise attitude restitution. We need to have very precise rotation acceleration measurements. The transverse wind also are an issue for this kind of experiment. And we need to know quite well what is the attitude control torque. Here it was the magneto-torquer, so it was a bit difficult to know. Okay. So from this first implementation, what we try to do right now is to have a phase zero of a torque compensated platform. So now the objective of the mission would be to measure this torque and to measure the atmospheric density. So I describe how we tried to, what was our strategy to overcome the limitation we've seen before. First, we need a precise IMU to measure precisely the rotation. And currently we are developing precise IMU, not for this purpose, but in the framework of H2020 Pioneers project. So we may have this IMU ready within 1 year. Then we want a star tracker because we need to know precisely what is the attitude. We need also reaction wheels because we need to know precisely what is the control torque. Maybe we need more than one type of reaction wheel, one with a large torque and one with a small torque. And a very important ingredient is that we need control deployables to increase, decrease, or reorient the torques. And this would allow us to first increase the torque when we want, and to avoid also the saturation of the reaction wheels. So the phase zero is not fully finished, but we did not have an answer to this question. Do we need thrusters? We think that maybe we need thrusters to gain margin and to avoid the saturation of the reaction wheel. So I describe you quickly how we do this. So we have two models of the satellite and the mission. We have a first model, which is a concurrent design facility model from CNES that allows us to do the full system analysis of the mission. So not only the spacecraft, but also the communication session and so on, the amount of data, the amount of mass, volume, and so on. And then we have this MATLAB Simulink model to demonstrate the performances by computing the dynamic of the spacecraft and the torque equations. So up to now, our best model for implementation is to have very large solar panels and to orient this solar panel in the same way than Venus Express. So one facing the flow and one parallel to the flow. So compared to the previous implementation you've seen here, where we have the paddle wheel configuration. So these solar panels are 90 degrees one to the other, but 45 degrees relative to the flow. This configuration is much more efficient. So it creates 100 times larger torques. So you see here that the torques, the aerodynamic torques are fully dominating over the other torques. Whereas here, we may have an effect of the residual magnetic dipole, which is always a very difficult thing to measure on a satellite, and even worse for a CubeSat. So up to now, our best configuration would be with these very large solar panels. I should mention that we try to have all these things off the shelf, ready to fly, so from CubeSat providers. So what is missing currently in this phase 0 is we did not fully explore the control loop. How if we control the torque by rotating the solar panels or the action wheels. What is sure is that the advantage of having large solar panel is also a way to have a large power available for IMU and also for electric thrusters. So we think that such a torque experiment would require such large solar panels and able to rotate. So I will conclude now. So what I try to demonstrate in this mission is that the drag force compensated mission already demonstrated the interest of measuring the air density along the satellite tracks. We think that we can design torque compensated CubeSat missions, but maybe cheaper for the same objectives and the same performances. The noise analysis indicate that we need a precise knowledge of attitude, so we need star trackers, we need a precise knowledge of rotation acceleration, so we need a very precise IMU, and also we need to know precisely what are the control torques. So we have an ongoing phase 0 analysis that suggests that for doing this you need large deployable, and maybe thrusters also may be required. But this phase 0 suggests that all these things can be done with CubeSat components that are already available on the market. So this is in good shape. So thank you very much.
Yes. Thank you for the insightful presentation, Dr. Raffel. So now the stage is open for questions. Dr. Raffel, you can stop sharing the screen. Yes, thank you. So having any questions from the speakers, you can ask to Dr. Raffel now. Okay.
Professor Garcia, this is Lakshmi Sankar from Georgia Tech. How are you? Are you able to hear me?
Yes.
Yeah, I have seen at Georgia Tech, the people use acoustic transmitters and receivers, and the time that it takes for the sound wave to travel, from the time delay that takes place between the transmitter and receiver, to get an estimate for the speed of sound, and then from that, back out the ambient temperature. And then usually they will use some form of an isentropic relationship with some reference conditions to get the density and so forth. My question was, I do not know whether these would be feasible in your space applications, but whether you're looking at alternate techniques such as acoustic techniques to look at ambient conditions, besides density.
Yeah, what you describe is maybe also the same technology that is used in acoustic anemometer. I'm not aware of having this implemented at altitudes larger than 20 kilometers. So it may be interesting that I got the information. So in QB50 project, there was also sensors sensing the atmospheric density. Obviously, we would like to have such sensor on our platform, because it would be also a good way to separate various variables. And as you've seen, we have a lot of space left in our design currently. So yeah, we thought integrating such kind of sensors that would give an independent measurement of the density. So that's a very good point.
All right, thanks. Thank you.
Okay, any other questions? Okay, thank you for answering the questions, Dr. Raffel. And once again, thank you for being part in our webinar. Hope you'll associate with our further events as well. Thank you so much. And the next presentation will be by Christian Bach from University of Denmark, and he's presenting on design and performance of the Paul Law core tunnel. So, Dr. Christian Bach.
Yes, I'm here.
Yes.
I will share my screen.
Okay.
Can you see this one?
Yes, yes. So Okay.
I will try to. Can you see this one?
Yes, that's perfect, Doctor. Go ahead.
Okay, thanks. Well, yes, thank you for coming to this conference. I want to take us to another field that is about aerodynamics and aeroacoustics. And I want to tell about the design and performance of the Paul Lacour tunnel. And I want to acknowledge my colleagues, Jimmy Beckerli, Andreas Fischer, Oliver Lyloff, Robert Mikkelsen, Sigurd Ilvedsen, Anders Olsen, Mark Gavner, Jens Østerlund, and Peter Davidson, a lot of people, but it is because we have designed a very big wind tunnel that I just want to show you in a moment. About me, my name is Christian Bach. I'm a professor. I'm also heading this wind tunnel now, and I am also heading a section called Airfoil and Rotor Design within wind energy. And I'm from the the Technical University of Denmark. So this university is about many topics, and one of the institutes and one of the departments of the 20 departments in the at the university is DTU Wind Energy. So we are dedicated to make research in wind energy, and we are situated in Denmark, at Risø, that is close to Copenhagen. In Denmark. I want to give you a background for this. I want to show you how this was designed, also show you the final design, some, you could say, performance and validation of the wind tunnel, and some conclusions. This started up a long time ago, in 2011, where we had a green light from the Danish Agency for Research and Innovation, where our task was to make a large wind tunnel for wind energy, and it should be a Danish national research infrastructure. We submitted a project description, and that was based on discussions with the wind turbine manufacturers Siemens, Vestas, blade manufacturer LM Wind Power, and manufacturer Suslon, and Danish universities and other stakeholders in Denmark. So in 2012, we had a grant from the Danish Agency for Research and Innovation. And then we started out in 2013 to 15 to do the design work. The first thing we actually did was to go to different wind tunnels. One of the wind tunnels were the Audi wind tunnel in Ingolstadt in Germany, and we also visited the DLR wind tunnel, acoustic wind tunnel in Braunschweig. And we made several different designs, investigated advantages and disadvantages of each design. And one of the issues in this process was that we had to match the quality, the specifications, but also the cost of the wind tunnel. So in 15 and 16, we made detailed design of the wind tunnel, and we put it to center. And then in April 16, we started the construction of the tunnel. And then 10th of April, we inaugurated the airline. In January 2020, we had then a full setup with instrumentation, both aerodynamically and acoustically, and this was then inaugurated. As I said, it was decided by the Danish stakeholders to design a wind tunnel dedicated to aerodynamic and the aeroacoustic test of airfoils. And it should be available both for research and commercial tests. And the daily operational cost was important, and it should be manageable. So that was what I talked about before, that we had to match both quality and price together. And that was kind of a challenge. So we had a set of specification that we established, and then at a point we realized that this is actually going to be more expensive than we thought. So we had to shrink it 10%, but that was not to balance the cost, but it was not a super big drawback. So it was okay. So what our specification was a test section that was 3 meters wide, 2 meters high, and a length of around 7 meters. And then a model in the test section that should be around 1 to 2 square meters and a drag coefficient of 0.1. And then we had some design points at 60, 82, and 105 meters per second. And with a flow quality that was below 0.1%. In turbulence intensity. And then we wanted to maintain the temperature at 25 degrees, so we have constant temperature. And then it's also an aeroacoustic wind tunnel, so we wanted to measure between 100 Hertz and 10 kilohertz, and then with a background noise that was less than 70 dB at 60 meters per second. So that was our starting point. Some of the specification, they were not super obvious. We had a turbulence intensity that we should find out, and that was not obvious how we should do this, because when we are operating wind turbines, we might say that okay, we are operating in a very turbulent environment, but actually in blade, the surrounding of the blades and in blade surroundings, the turbulence intensity is actually rather low. So we have made full-scale measurements on wind turbines and realized that the turbulence level was actually as low as 0.1% as we prescribed for this wind tunnel. So that was one thing that we had to find out from the start. Another thing was also the noise. And then we could see from other wind tunnels where we have tested, and for instance, the Virginia Tech wind tunnel, that we could set up a specification for the noise. And you can see to the right how we wanted the noise to behave according to the red line. So it was our target was a maximum of 6 dB above the expected noise level, and that is because we know that it is very difficult to make a wind tunnel where we have the background noise level below the expected noise level. So we wouldn't be too demanding about this. Yeah, and then if we have a background noise level that is above the expected noise level, then we know that we have to measure with a microphone array. But here you can see a sketch of the wind tunnel. So that is the different components in the wind tunnel. So we have a test section here. We have a diffuser there, and the diffuser is all the green ones. We have the corners, they are blue. Then we have the heat exchanger, and that is the blue or black one. Then we have what we call transformers. They are called number 5 and they are yellow. We have the fan, that is number 6. We have the screens over here, the red one, number 7. And then the settling chamber, that's number 8. And a contraction, that's number 9. And then the anechoic chamber, that's number 10. And each component in the design process is described with a pressure loss, and also that is dependent on the velocity and the sectional area. So that is, you can say, a simple way of designing the wind tunnel, and actually rather efficient. Yeah. But the airline is optimized to obtain high flow quality and at the same time have low losses. So if you just go through the wind tunnel, and I will just show 3 different components. So we have the test section, And this is designed with a traditional closed test section, as you can see to the left, and then a hybrid aeroacoustic test section, as you can see to the right. And these photos, they are actually from the Virginia Tech hybrid aeroacoustic wind tunnel, and the photos are from there. And we have had a very good cooperation with them to establish this facility. And the walls in the test sections is then slightly diverging due to the boundary layer development through the wind tunnel. The corners, they are also special, so they have a expansion ratio of 32%. So you can say it is 1.32, and that means that the area where the flow goes in is, or the area where the flow goes out is 32% bigger than where the flow goes in. And in this way, we can actually shorten the wind tunnel. So these guide vanes, they ensure that we can expand the flow over the guide vanes. So that's pretty smart. And then we also use the guide vanes to absorb the noise. So we have some perforated steel plates with very small holes, and then with some absorbing material behind these steel plates. In this way, we use the guide vanes to reduce the noise that is emitted from the fan. And that the fan can actually be pretty noisy, but when we want a silent area of test over here, then it is important that we can actually reduce the noise. So we use the guide vanes for this. And then we have the anechoic chamber there. And that is the surrounding for the test section. And it's the boundary conditions for the design of the airline. And it ended up that the length of this chamber was 12.7 meters long, 10.7 meters high, and 5.9 meters in width. That's right. That's a requirement, but it is actually the height is actually 12 meters high. So that's the size of this anechoic chamber. And this is then the final design, and that's is only, you can say, what came out of the optimization process. And we could see that there were losses through the airline, and we could also see that the major part of the losses are generated where the flow speed is high. So about, you could say, 50% of the losses are in this part of the airline, where the rest, there are some losses, but they are not so big. So that's it's important that we take care of the losses, and that was much about what we investigated in the design process to reduce the losses in this part, so we could make an effective wind tunnel. Also the background noise was very important. So the pink line here was our target. And this was then the result if we just had the fan. The fan is over here, and this curve is then measured around the test section. So if we wanted this curve to appear with this noise from the fan, then we should do something very drastic designs, and that was what we did with the guide vanes. And we also had some absorption of noise around the fan. So in the below plot, you can see how we actually succeeded. And this is then the computations from this, but actually the measurements have shown similar trends, that we have the target there, but then we succeeded to reduce the noise with 60 dB around 500 Hertz, and with 33 dB around 1000 Hertz. So that was a pretty big reduction of noise. So the background noise in the tunnel is low. And then you can see this is then the result after some civil work has been done, and it is made in concrete. So we have the airline as we designed, and then some support structures and support rooms around this with workshops, etc. So this is you can say a sketch of the real wind tunnel in the end. And here you can see some photos. So this is from the architect from the start, and the rest is then real pictures. So this is actually taken this summer. So it's actually a pretty good comparison between the architect and the real one. Here you can see the test section, and you can see the hard walls. So this is not the Kepler wall or the acoustic configuration. You can see guide vanes there. So this is where the guide vanes, they are around 5 meters high in this area. You can see the screens, the contraction and the screens down there. And then the fan, it's hard to get the fan in one picture, but this is then just the inlet to the fan. And then this is the top of the test section. Sorry, this is the top of the test section. You can see the anechoic room. So you can see also the wedges made of foam, and how this foam absorb the noise. So it is, even though we have some structures in the room, this room is anechoic at the part of the measurement space that we have just on the side of the test section down here behind the test section. So this is actually working well. So we have, you can say, both anechoic conditions down there and over here. And then we have also a crane that can move around with the heavy stuff. So we have the possibility of moving around with bottles up to 500-700. Actually, the crane can take 5 tons, but we have moved around with 500 to 700 kilo heavy models. And then we lift the models through the lid into the wind tunnel, like you can see here. We can see also here the test section. Here you have the aerodynamic test section. So this is the hard walls, and then you can see the acoustic walls, the Kepler walls here. And behind this Kepler wall, you can see a microphone array. And in this microphone array, we have 84 microphones, and this is then pointing towards especially the trailing edge of this airfoil, so that we can measure the noise that is emitted through these Kepler walls. So these Kepler walls, they are there to contain the flow, but let the noise from the model emit through the Kepler sheet. So that is actually a very good way of measuring both aerodynamics and acoustics in the same way, without too many corrections to the wind tunnel test. And this is then an example of the measurements where we have the microphone array pointing towards the model inside the tunnel. And this is then a result of the measurements where we have the flow coming from right to left. This is the leading edge of the airfoil, and this is the trailing edge of the airfoil. And then within this area, dotted area, this rectangular section, we integrate the noise. And you can see how the noise from this map shows at 1000 hertz show most noise at the trailing edge, and almost no noise from the rest, neither the leading edge or other parts. So that is evident that the trailing edge noise is very important as a noise source. And here you can see some of the instruments in the tunnel. We have 384 pressure sensors, angle of attack, humidity, temperature, 84 microphones, force gauges, and we have also the turntable, as you can see there. And here we can turn the turntable with 24 degrees per second, and with a maximum torque of 17 kilonewtons per meter. And we also have a wake rate, as you can see down here, where we can measure the wake and thereby the drag from a model. So we are able to characterize airfoils very precise. And we are able to test up to 105 meters per second. And what about the tunnel as such? Well, we started out with a predicted efficiency of the tunnel, and this efficiency is then fan power divided by the wind power. And we predicted that it would end up with 38.9% in deep stall, and with no model mounted, it would be 34.8%. But we designed actually the tunnel so we could run the tunnel even though we had an efficiency of 50%, because we were a bit cautious and we were a bit afraid that some of the loss calculations was not super certain. For instance, the corners, we had seen some tunnels that actually failed in the corners. So we wanted to ensure that we could actually make it with the fan that we bought. In reality, we saw that the efficiency was 43.7 compared to these 38.9, and without the model included, it was 34.9 compared to 34.8. So it was actually a very good prediction, and these corners, they did not fail. So apparently the design was well done. So that was nice. So the observations, they compared very well to the predictions. And then we also wanted to know about the acoustics. So did we actually obtain this target? And then we realized that when we measured, it ended up here. So it seemed to be apparently very bad, but it was actually not bad, because we realized that these target curves, they were made for open wind tunnels. But now we have closed the wind tunnel with this Kevlar ball, and then we cannot make a plot like this when the test section is closed. And this is because the noise generated along the walls are kind of significant compared to an open tunnel, but we have the possibility to move the array very close to the wall, and in this way we can actually get much closer to the source of the noise, and thereby actually get a better signal to noise ratio, and that's the important part. So here you can see that we are actually able to measure the noise from about 50 hertz to 1 to 2,000 hertz, just measuring with one microphone, where the background noise is lower than the noise source in itself. So you can say we designed with the background noise 60 dB above the level to be measured, but we actually got the noise around 60 dB below the level in an important part of the frequency range. So that is actually interesting that we realized that we actually got a better tunnel than we from the start designed for. So that was a very good experience. When it comes to aerodynamic performance, we could see that the airfoils that we tested compared well to different wind tunnels. I have compared to the Delft wind tunnel, the Nasal Langley wind tunnel, the Stuttgart wind tunnel, and this tunnel compares very well to all these tunnels. And here you can see also the lift curve, but this is actually just the top of the lift curve. So this is just to highlight that there are some differences in the maximum lift for different airfoils, or actually not different, but even for the same airfoil, but in different tunnels. So we can see that even though we are measuring the same airfoil, we can see that there are differences in max lift between 1.3 and 1.4. So this is it's not new, but it is just highlighted that there are some differences, and we actually had some maximum lift in between the ones that we have seen. And this is then the lift to drag ratio, lift as a function of lift drag ratio. So we can see that we also get the lift drag ratio pretty good. And ours are the PLCT. The green curve is from our tunnel. Yeah. Another example is the 30% airfoil from Delft, the DU97, and we can see how the blue curve and blue and green dots that are from our tunnel, the PLCT tunnel, compares to the yellow dots from Delft, and that's actually also a good comparison between the two. So we can conclude that this tunnel also measure with very high quality. We also made some noise measurements, and this is an example from 3 million, and this is compared to some computations, and we can see that we also get very good results. And we have compared to the Virginia Tech tunnel. I can unfortunately not show it here, but we can see that we also have very good agreement with their results. So also in terms of acoustics, we are doing very well. So to conclude, we made a wind tunnel with the size that we had specified. The model is also as we specified. So you can say the standard airfoil is in 1 meter in chord, and then 2 meter in span. And then you can make the chord even bigger, or you can make it smaller, but you can say default is a 1 meter chord, and then default is also a maximum Reynolds number of around 7 million. But we have actually measured on airfoils that has a bigger chord, and we have been up to more than 9 million in Reynolds number in the tunnel. We designed for the different speeds at 60, 82, and 105 meters per second. And we also obtained a turbulence intensity below 0.1%. And we can run constantly at 25 degrees Celsius because of a cooler in the wind tunnel. And we also obtained an anechoic chamber that is anechoic between 100 Hertz and 10 kilohertz. And then the background noise, we actually also obtained this below 70 dB. And then I wrote kind of, because that was actually a surprise that we couldn't really reach this specification as we set out, but we actually got it better than we had hoped in the end. So that was nice. The last slide here, it is important to be aware of the specification. So when we have a low turbulence intensity, then we need, or when we want a low turbulence intensity, then we need a large contraction ratio, and possibly also only a one propeller instead of multiple propellers, because there's a tendency that the tunnels with multiple propellers actually show a bigger turbulence level. And with this big contraction ratio, we also need a long airline and a specialized propeller, and that means higher cost. We also wanted low noise, so we need absorption panels and a low noise fan. That also means higher cost. And it's also important to be aware of the applications. So if you want a wind engineering type tunnel, then you need one tunnel. And if you want an aerospace type tunnel, as we wanted, then it is also different. So we have to choose between a long test section, that is the wind engineering type, and the shorter test section, that is the aerospace. And also want to choose between high speeds and low speeds. So these are two different tunnels when you choose between wind engineering tunnels that are typically up to 30, maybe 40 meters per second. And then the aerospace type, that is, in our case, it goes up to 105 meters per second. And the performance of the wind tunnel showed that we actually obtained our specifications. We are able to carry out high quality airfoil measurements, both in terms of aerodynamics and aeroacoustics. So that was a nice experience to see that we succeeded. So even though the wind tunnel is dedicated to wind energy, we can also easily use it for aerospace applications. So there's not as such a difference between these tunnels, the wind engineering type and the aerospace type, but we have a lot of the applications for airfoils and so on has been dedicated to the wind engineering, wind energy topics. So that concludes my talk. Thank you very much.
Yeah, thank you for the wonderful presentation, Dr. Bach. And now the stage is open for questions.
This is Shankar again. A very good presentation. As you know, in wind turbines, the inflow through the rotor disk is a very important issue. Are you planning to do some LDV measurements or some non-intrusive measurements of the inflow velocity distribution for wind turbines in your study, or are you primarily limiting to power measurements? Or, I just want to get an idea of what you plan to do in terms of future measurements.
When it comes to the wind tunnel, we want to measure more of the inflow, both the flow mechanisms around the airfoil, both in front of the airfoil, the inflow part and the wake part. But we also want to put the wind tunnel in the context of, you can say, the chain from going from laboratory, that is the wind tunnel, to the full scale. So we want to, and we have measured on full scale wind turbines, and we are want to develop this further. So we will go and measure with pressure belts and pitot tubes on a wind turbine, and also use wind scanners to map the flow both in front of the wind turbine in the inflow part and also in the wake part. So we map the flow as precise as possible, but mapping the flow of the wind turbine is a very challenging thing to do. But that is actually our goal, to measure full scale and try to connect the wind tunnel measurements to the full scale parts, because it is what is going on at the turbine is not two-dimensional. Part of the blade is behaving somewhat two-dimensional, but not the entire part. And it's very important to know which part of the blade is actually 2D-like and which parts are influenced by the rotational flow and the tip flow.
Yeah, your department has been a leader in wind energy for a long time. It's great to see the tradition continue. Wish you all the best with it.
Thank you. Thank you.
Thank you for answering the questions, Dr. Back. And once again, thank you for being part in our webinar. Hope you will associate with our future events as well. Thank you so much.
Thank you.
Okay, moving towards the next presentation, and the next presentation by Dr. Sidney Goossens from VG University, Brussels and Flanders Make, Belgium. And he is going to presenting the talk on optical fiber sensors for barely visible impact damage detection on CRFP components. Yes.
Thank you very much. Can you hear me, see me, and see the screen?
Yes, sir. Please proceed.
Okay, thank you. So, good day, everyone. My name is indeed Sidney Goossens from Brussels Photonics at the Vrije Universiteit Brussels in Brussels, Belgium. And welcome to my talk about optical fiber sensors for barely visible impact damage detection on carbon fiber reinforced polymer components. Well, the work that I'm going to show you today is part of Sherlock. It is a project within Horizon 2020 Clean Sky 2 joint undertaking. Now, this joint undertaking is a European undertaking that aims for developing innovative cutting-edge technologies aimed at reducing CO2 gas emission produced by aircraft. And within this joint undertaking, the Sherlock project stands for Structural Health Monitoring, Manufacturing and Repair Technologies for the Life Management of Composite Fuselage. And within this project, it was our task to develop advanced technical capabilities for making the integration of optical fiber sensors in modern composite structures practical and efficient for industrialization. Well, composite materials have many advantages over traditional metals, as you all know. However, care is still required. Composite materials are increasingly used because of their stiffness over mass ratio that's much higher than for metals, and that allows them to reduce in fuel and CO2 emission. For example, the Airbus A350 here, that's already made out of more than half with these carbon fiber reinforced polymers. However, these composites are prone to damage. More specifically, that is barely visible impact damage, or BVIDs, as I'm going to call it in the rest of the presentation. And they can be caused by lightning strikes, bird hit, hail strikes, or even a tool that's dropped accidentally during maintenance. Now, they leave a 0.3 millimeter indentation on the surface of the component. That's why they are barely visible, but they also create a delamination inside of the component. And that delamination can grow and possibly even cause failure of the component if it's not detected on time. So to detect these BVIDs as soon as possible, airplane manufacturers are looking at structural health monitoring, because today these BVIDs are searched for by frequent and lengthy scans that increase the maintenance time, the downtime of the airplanes, and the maintenance cost. This can be overcome by a permanently installed sensor network that can perform this structural health monitoring. And we are looking there at optical fiber sensors, more specifically FBG sensors, because they are lightweight, they can be multiplexed, they're immune to electromagnetic interference, and they are minimally intrusive when looking at embedding them in the structure. And we're going to use these to detect the BVIDs as soon as possible and before they can grow. Now, an optical fiber, you probably all heard of them as the backbone of the internet. You can see one here. They have a diameter of about 125 micrometers, but they can also be used as sensors, where the sensor is then inside of the optical fiber. For example, here they then act as optical strain gauges, more or less. So in one optical fiber line, you can have multiple sensors, for example, here on a curved stiffened panel. Now, for the remainder of the presentation, I need to explain shortly how such a sensor works. So an optical fiber is typically made out of two parts, the core of the optical fiber and the cladding. And when light propagates to the fiber, it reflects on the core cladding interface, and like that is guided through this waveguide. Now, when we inscribe, or when we inject broadband light into the optical fiber, naturally it will emerge on the other side. However, when we inscribe an FBG sensor, fiber Bragg grating sensor, in the core of the optical fiber, that sensor will reflect a narrow bandwidth of light that will come back out on the entrance of the fiber, while all the rest is transmitted through the fiber, except for this narrow bandwidth, of course. And this spectrum, or this reflection signal, that will be the signal of our sensor. That's what we call the reflection spectrum, that is centered around the Bragg wavelength. And by creating multiple such sensors in an optical fiber with different pitches, you can create what we call wavelength division multiplexing to have different sensors, hundreds of sensors in one optical fiber line. Now, this technology is well established for load monitoring in aerospace applications then, but for damage detection, not so much. So how can we now use these sensors for damage detection? Well, we're looking here especially at damage-sensitive locations where we mount the optical fiber onto the structure here with the FBG sensors inside. And then when a BVIT is created, the strain field around that sensor will change, and that strain redistribution we can measure. If the strain redistribution due to the damage is uniform, then, and that's the way this sensor works, the Bragg wavelength or the reflection spectrum will shift. That will be our first damage indicator. However, if the strain over the FBG sensor is non-uniform, then there will be a non-uniformity in the sensor as well, and that will deform the shape of the reflection spectrum, and that we can measure by correlating the shape before and after, and that will be our second damage indicator. So we will search for damage by comparing the spectrum before and after the damage. And this is still at a very low technology readiness level. You can find these things in literature, of course, but they are typically proof of concept demonstrations at lab conditions. That's why it's the objective of this project to bring this technology from, we estimated it to be at technology readiness level 3 to a TRL 6. And we will do that by looking at real aerospace grade CFRP components with geometrically relevant details and stacking sequences, and by performing calibrated impacts to create repeatable and calibrated BVIT sizes. And that we will do by using a building block approach. That building block approach, we start at the coupon level. There we looked at a total of 250 coupons or small panels, which are generic components that allowed us to create a statistically relevant database. When we learned what we had to learn on the coupon level, we moved to the element level, where we looked at 5 components with more geometrical details, as you can see here. And those were tested in more relevant aerospace conditions. And what we learned at this level, we took to the subcomponent level, where we looked at 3 large stiffened panels, where we instrumented our optical fiber sensors on, so to have a testing environment on more realistic components with relevant aerospace features. Now, this building block approach will also be the outline of the continuation of this presentation, because on the coupon level, we will look at the installation of the optical fiber sensors, more specifically at how can we now install these optical fiber sensors to be compatible with airspace conditions, to survive in-flight conditions. Second of all, when we have our robust optical fiber sensors, we will look at how to detect damage in real on-ground relevant conditions. And then thirdly, on subcomponent level, we will look at the interpretation of the data, namely how can we simplify the data of hundreds of these sensors for quantifying the health of a component in one single number. So let's start at the beginning, that is the installation at coupon level. In literature, you typically find demonstrations that look like this. So first of all, you can embed the optical fibers inside the composite. That's often done. However, this is not highly compatible with the industry yet, because as you can see here, you create actually a weak point not only in the composite, but also for the optical fiber. Here it's protected with Teflon tubing, so it's a little thicker than the fiber itself, but still you can see that there is a weak point introduced here. And second of all, of course, this is not compatible with standardized trimming of these panels because your fiber has to come out somewhere. Then you can also look at surface mounting the optical fibers, which is what we will look at today. But lab demonstrations typically look like this. You have your substrate, which in this case was a plexiglass board, but it in this application field would be a composite, of course. You have the FBG sensor mounted to the structure with tape or with a standard adhesive. And then you have the rest of the optical fiber, which is here coated, it doesn't say, well, it's coated, of course, with the black coating that is rolled up and taped to the structure like that. Now, these are perfect for lab demonstrations, but are obviously not suited for harsh aerospace environments. So that's the first problem we want to tackle. And for that, we looked for and selected a robust optical fiber sensor that is available for purchase. And this sensor is the optical fiber, as you can see here. So the glass fiber coated with a layer of Ormos and then additionally packaged with a packaging of glass fiber reinforced polymer and an additional layer of high density polyethylene for humidity protection. Now this fiber we developed in, and then we still have the optical fiber sensors, the FBG sensors inside of the optical fiber, of course. And we mounted this fiber to the structure by completely encapsulating it with a layer of optical fiber adhesive by HBM. So not only the sensor portions, but the entire optical fiber, not to leave any optical fiber unprotected. Now, one question remains, of course, can this robust fiber and the installation survive in-flight conditions? To test that, we instrumented a total of 48 coupons from 3 aerospace-grade composite materials with our surface-mounted optical fiber sensors. We had here on the left, you see a thermoset coupons with our optical fiber here mounted at the sensor location. On the right, you see the thermoplastic coupons with 2 sensors mounted over the entire length. And then we still had a liquid resin infused material system also that's not shown here. So here you see the dimensions of the coupon with the 2 or 1 FBG sensor inside. These coupons were then submitted to selections of standardized in-flight conditions. These tests were as follows. So we first of all had a temperature profile, room temperature to in-flight temperature or high airport temperature, all standardized values, also shock from one to the other. Pressure, we had atmospheric pressure in flight pressure. We had high humidity levels for a longer duration, standardized vibration, engine vibration profile, submission to or immersion better in hydroic fluid for 24 hours, and tensile fatigue testing. Now, to test if the sensor, the installation, or the fiber was affected by any of these in-flight conditions, we obtained the sensor response, so the reflection spectrum before a test sequence. Then the coupon with the sensor, of course, went through a sequence of tests. In this example shown here, that was temperature, pressure, and humidity. And then the spectrum was obtained again. And the same for the second example here, where an additional vibration profile was applied to the coupon. Now, to see if anything affected the sensor at its mounting location, we compared these spectra before and after. And remind you, that was our second damage indicator. If there is a local damage, we expect the Bragg peak shape or the reflection shape to distort. So we correlated the shapes of the peaks before and after, and these correlation values were sufficiently high to conclude that there is no peak deformation relative to any detected damage, so no local damage to the sensor packaging or the sensor, its packaging, or the installation better. So we concluded here that we developed indeed a robust installation that is compatible with standardized in-flight conditions, which brings this technology one step closer to industry and hopefully also inspires others in literature demonstrations to not overlook this important aspect as well. That concludes the coupon level of the building block approach. So now we have our robust optical fiber sensor and the installation method. We can move towards the detection of damage. And there we looked at what we have to consider when detecting these BVITs in real on-ground conditions. That scenario looks as follows. So we typically take a baseline measurement in the pristine state when there's no damage present and the airplane is grounded. Then the airplane takes a flight. There might be possible damage, and that we will find out by performing an inspection measurement, again in an on-ground condition. Now these, or to see if any damage is present, we compare the baseline measurement to the inspection measurement. That's typically done in lab conditions, of course, because the situation is exactly the same. However, in a real industrial environment, there the baseline could have been taken, for example, on a cold airport with the engine off, while the inspection measurement could have been taken in a hot environment while the aircraft engine was on. And the question is, of course, can we still compare the baseline to the inspection measurement, which is typically overlooked in literature, but of course, still a very important aspect to consider. To investigate that, we instrumented selected panels, again, from the same material system. So we had thermoset, LRI, and thermoplastic. We instrumented those with our optical fiber sensors in the following layout. So here you can see the panels. They were about 25 by 20 centimeters. You had the optical fibers mounted on top. So here you see the adhesive with in every arm of this cross 3 sensors. So 6 sensors per fiber or 12 per panel, of course. Now, these FBG sensors are also sensitive to temperature. So if we do the inspection measurement at a different location as the baseline measurement, these sensors will measure a difference due to the difference in temperature. That will result in a wavelength shift that is similar to what we expect in the presence of damage. So we have to make sure, of course, that we do not confuse this wavelength shift due to temperature for possible damage. Now, to inspect or to study the effect of these temperature differences, we exposed these panels to standardized on-ground survival temperatures because the measurement will happen on ground. So these are defined as temperatures from -45 till +45 degrees centigrade. And we tested the panel every 5 degrees, so in steps of 5 degrees. Every step, we then obtained the Bragg wavelength of all the sensors, so all 12 sensors for all the selected panels. This allows us to do a calibration of the Bragg wavelength in function of temperature, as you can see here for just one of these sensors. That quadratic relation we can then use to compensate for the temperature difference after performing a measurement. Of course, no sensor is perfect, no sensor is identical to the next sensor, so there will always be a compensation error. And again, we have to make sure that this compensation error is not mistaken for possible damage. So we combined all the compensation errors for all the sensors, all the panels, and all the tested temperature steps into one large database where you can see the histogram here. And as expected, of course, most of those compensation errors are around 0, and that's a good thing. However, there are still compensation errors up to wavelength shifts of ±15 picometers. So up to these values, we can expect possible temperature effects. Now, what does that mean? Well, that means that if we measure a Bragg wavelength shift in our or due to our inspection measurements, well, then everything under that 15 picometers could be attributed to a temperature effect, and everything above, we can certainly say then that that is contributed to damage or to a BVIT. We did the same for the on-ground engine vibration profile. So there we submitted selected panels to a standardized vibration profile. And again, we obtained our wavelength shifts during that vibration, obtained the data set, extracted the near certainty interval, so the 3 sigma interval from that data set to obtain similar thresholds. So everything below that threshold could be accounted to vibrations, and everything above, we can be sure that we are talking about BIVITs. Now, of course, we can have a combination of the 2 effects. So we concluded that the threshold should be the addition of the 2. So the thresholds obtained for the temperature difference compensation and the thresholds for the vibration profile. I just showed the data for the first damage indicator, so the wavelength shift. There is also still the correlation coefficient damage indicator for the non-uniform strain that we, of course, also tested. And then the obtained values were the following. So for our wavelength shift indicator, we have a threshold, or we obtained a threshold of 17 picometer. So we have to be sure that we measure damage above that value. For the correlation coefficient, that was 2.3%. Now, one question of, so we indeed obtained these minimum detection values, but one question remains then, with these values, can we still detect BIVITs? To test that, we submitted these panels. So you can see one here clamped into an impact setup with here the optical fibers mounted on top. And we submitted them to 24 calibrated impacts to create similar BIVITs on all of the panels. And that you can normally see now in a slow motion video, where you will see the impactor hitting the panel here at a certain distance from these optical fibers. So here we have the 12 optical fiber sensors. We performed an impact at this location. And then we looked at which of these sensors were still able to detect the impact by having a wavelength shift or a correlation value that was higher than the just established threshold. And for the examples shown here, that were sensors 2, 3, and 9. So that allowed us to draw a detection radius through these sensors with the BIVIT or the impact location in the center. And from that, of course, for not just for one impact, but for all the impacts we performed, we obtained the following values. For the wavelength shift indicator, depending on the material type, that was 2 to 3.5 centimeter. That's the range you can be from the sensors. For the correlation coefficient, we noticed that the BIVIT or the damage actually had to extend until under the sensor for still being able to detect it. So this wavelength shift indicator is the better damage indicator, or at least it has the larger range. So to conclude here, we considered the presence of real on-ground conditions for the first time to see what effect that will have on the damage detection. From that, we obtained minimum threshold values, and those we used to establish the maximum range, spatial range, then to still detect BIVITs. Something that is typically overlooked in literature, but is of course very important to consider in a real industrial environment. This methodology we also verified on elements with more complex geometry. We first of all had 2 thermoset monostringers. We had 1 liquid resin infused floor beam, and then an additional 2 thermoplastic window frames. Now, we instrumented, of course, these elements with our surface-mounted, aerospace-grade surface-mounted optical fiber sensors. So the monostringers we instrumented with 1 fiber with 12 FBGs. The floor beam was instrumented for a portion with 15 FBGs, and the window frame, there we instrumented the fiber, 1 fiber with a total of 40 sensors. Now, I don't have the time to discuss all these examples, so let's have a look at a structure that's very representable for an aerospace component, and that is, of course, the monostringer. Because there, this bond layer between the stiffener and the skin is a region that is very sensitive to BIVIT, because there a delamination can start occurring. So for that, we instrumented these, the foot of the stiffener with our 12 FBG sensors. Again, we we measured the spectrum of our FBG sensors before. We performed a calibrated impact to create damage, and then we measured the spectrum again after. And for every of these 12 individual sensors, we obtained then our wavelength shift. That's what you can see here now for all of the 12 sensors. So you can clearly see that around the damage, you have larger wavelengths, while going away further from the damage at the end here, you have almost no wavelength shift, which is, of course, what we expect. Now, to compare this with the just established thresholds, are we actually able to detect damage? Well, these were the thresholds, and indeed the wavelength shifts are high enough here to detect damage. So we can use our optical fiber sensors in this damage sensitive location here, often found in aerospace structure. Similar conclusions were obtained for the floor beam and the window frame, but I will not go into detail there. So we verified this methodology on more complex geometries, which also supports it to be used on real aerospace components. And that concludes the element level. And now with this detection methodology, we can move to the subcomponent level, where we look at the interpretation of hundreds of these sensors in one optical fiber for quantifying the health of the component, for being compatible with condition-based maintenance then, of course. And that will be the last panel of the presentation. So for that, we instrumented 3 flat stiffened panels of 1.6 by 0.9 meters. As you can see the cat drawing here. We instrumented our fibers in one of the 2 bays of these 3 panels, and again on the damage-prone locations, that is here the feet of the stiffeners. We had 2 optical fibers per stiffener, so yeah, here is 1 fiber going over the omega profile. Every fiber had 30 sensors, so 15 sensors per foot, 15 here, 15 here, 15 here, and 15 here. And then the reflection spectrum, or the signal of these sensors, looks as follows. So fiber 1 gives this reflection spectrum. You see here the 30 sensors, and fiber 2 gives the following. Of course, data like this is quite complex to interpret, and is not highly compatible yet with condition-based maintenance. So the question is, how can we improve that? And to look at that, we measured our spectrum before damage. We performed a calibrated impact, as you can see on the back side of the flat stiffened panel, here in slow motion again, to create our calibrated BIVIT. We again obtained the spectrum after the impact, and we obtained our wavelength shifts from these measurements. Again, here you can see the temperature compensated wavelength shift for all 60 sensors. So most of these sensors there, the wavelength shift is around 0, as expected, of course. But here you can see the damage signature for these sensors around the damage. On this data set, or on these wavelength shifts, we performed statistical analysis. So as you can see here, ordered from small to large, the wavelength shifts. And from that data set, we obtained the 95% confidence bound. And that number will be the global damage index. So one single number that gives us an idea of the damage situation of the component based on these 60 readings. So in that number, we have, first of all, of course, the calculation of the wavelength shift for all sensors. It is compensated automatically for temperature based on the bulk reading of the other sensors that do not see the damage. Statistical analysis is performed, and from that we obtain our global damage index that can easily be used by technicians to see if no damage is present since the last measurement, or if this global damage index has risen and a more thorough inspection is required at that location. So to conclude here, we indeed developed our global damage index that allows for fast quantification of the health of a subcomponent, but also track that health through the lifetime of the component. As more damage is created, that number will go up. That allows for the easy access to the component's health for implementation in a structural health monitoring condition-based maintenance scheme. And that concludes the last panel of this presentation. So in general conclusion then, for the FBG-based local damage monitoring methodology, we estimated this technology to be at TRL 3, and we brought it to TRL 6, so an industrial environment application, by first of all looking at airworthy installation, then on-ground detection in relevant environments, and lastly, the health quantification of a component in one single number. And with that we achieved our objective within the Clean Sky joint undertaking, that is for contributing to a more durable and less CO2 emitting aviation of the future. Thank you very much.
Yeah. Thank you for the wonderful presentation, Dr. Sidney Goossens. And now the stage is open for questions. So having any questions from the speakers, you can ask now.
I had a quick question. This is Lakshmi Sankar. Are these fiber optic sensors permanently embedded in the composite structure, the way I understand it?
Yeah, yes, indeed. So the idea is to create a permanently installed network that flies with the airplane. So that's why we had to look also at the compatibility with in-flight conditions. Understand. So we know that our network is still reliable after flight. The measurement only occurs on ground. So there is no interrogation or no readout equipment on board. So it doesn't add additional weight or additional power consumption to the aircraft, but the sensor network itself will be permanently installed. Yes, indeed.
So that would add a little bit to the cost and weight of the component. I'm assuming you have an estimate and it's not very, very high, I assume. Is that right?
Indeed, of course, additional sensors will add cost to the component. Now, these, first of all, these optical fibers are standard telecom fibers, so these are very cheap. The sensors are written inside of the optical fibers also. So by mass production, this will not be a very great additional cost. Moreover, by implementing these sensors, we can actually reduce the amount of material that is necessary in the composite components. Now, these components are also at certain locations made with extra material to protect them against these impacts, and that could be overcome by implementing these sensors. So with the total fuel reduction, reduction in CO2 emission also, and the reduction in weight that we can accomplish, the overall picture would be to have a saving actually on the aircraft, instead, I mean, of an additional cost due to the sensor network.
Thank you.
Any other questions? Yes, thank you, Doctor. So, and the next presentation will be by a video by Dr. Lakshmi Shankar, Georgia Institute of Technology, and he's going to present in the talk on aeroelastic modeling of offshore wind turbines.
Okay, are you able to see my screen right now?
Yes, sir. So great. Please keep it in full screen.
Okay, all right. Are you able to see now full screen?
Yes. Okay.
Yeah. Thanks again for the opportunity to present this work. I thought there may be only one person in the audience by this time, so I may be talking to myself, which is not unusual. But our talk is titled Aeroelastic Modeling of Offshore Wind Turbines. And, the authors are Dr. Aurora Pichitkul. She is now a lecturer at the Uta Rnr University of Technology. She just graduated this past summer and returned back to her country. My name is Lakshmi Sankar, and I'm a professor here at Georgia Tech. And Dr. Jagoda was also on her dissertation committee and contributed greatly to this work. So we are very pleased to give this presentation at the Aero Forum virtually. I want to give a brief overview, a background of the wind turbines, what are some of the issues. Then I'll go through the research objectives. And then we will also talk about how we approach this particular problem, what type of aerodynamic solver we are using, what type of structural solver we are using, and how we are coupling the two things together. Then I will talk about the rotor that we considered, which is a very large scale 5 megawatt power production wind turbine designed by the National Renewable Energy Lab. We'll give the specification of that particular rotor. Then we'll jump right into our aerodynamic modeling and also aeroelastic modeling. And then summarize our work with some conclusions and recommendations. I'm going to give a thumbnail sketch of Dr. Aralak Pichikul's outstanding work. So I'm really not doing justification to her work. So I hope after this talk, if you could visit her dissertation, a lot of information is available, the full thesis. She has done a lot of other analysis also for very different rotors. So everything would be there. So let me start with the background. As all of us know, wind turbines are getting bigger and bigger, not surprisingly, because the power production is proportional to the pi r squared, where r is the radius of the turbine, and is proportional to the velocity cubed. So if you have a lot of velocity, high velocity, and also a large disk area, then you can produce a lot of power. Unfortunately, when you produce large wind turbine rotors like this, the mass of the blade varies as a mass rotor radius cubed for the old generation turbines. And now more modern turbines, they vary somewhere between radius cubed and radius squared. So when we are talking about 50 to 60 meter radius, we're talking about a very, very heavyweight rotor, which costs a lot of money. Plus, when such a large component is rotating in an unsteady wind field, any vibrations are transmitted to the shaft, to the gears, and any kind of a breakage or a cracks in the gear teeth or a damage to the generator costs a lot of money. Also, if the rotor is very big, the tower happens to be very big, then the tower cost increases, the foundation cost increases, everything goes up in cost. So it's necessary not only to characterize the aerodynamic characteristics of the wind turbines, but also the aeroelastic characteristics of the wind turbines, and understand what type of stresses, strains, loads that we're going to be facing. So there's a lot of work that has been done in this work. Now attention is shifting to offshore wind turbines because they have a very high wind sources. Plus, they could be placed away from the shore, so people are not able to see them. Noise is not heard from them. And then they have all these attractive features, but they do have challenges because servicing them, maintaining them, insuring them is very, very expensive. So understanding the aeroelastic behavior of large offshore wind turbines is essential for designing and developing the next generation, very large scale aeroelastic turbines. So here are some of the pictures of configurations that are being done. Some are directly mounted on the ocean floor. There are various ways you could mount it. But once you get off to deep waters, they become like a floating oil rig. So a lot of things that are learned about oil rigs are being now used. Then they are tethered to the ocean floor by tethers. So the whole thing is floating. So there are lots of fluctuations in the structural loads, not only from the wind hitting the rotor, but also the wind hitting the tower that connects the rotor to the foundation. And of course, the waves hitting the foundation, transmitting the rotor. All these things is a complex multi-dimensional problem, multidisciplinary problem. These need to be understood so that we could design them, construct them, maintain them, insure them, and reduce the cost of ownership and cost of operations. So National Renewable Energy Lab in this country, and also European energy and organizations, and of course the Asian organizations have done a lot of work on understanding these features. So we need really a multidisciplinary analysis that can model not only the rotor, but also the tower, and perhaps the flexible shaft, flexible hub. They need to be able to model the gear dynamics, gear fatigue, gear cracking. They need to be able to model the rotor, the generators. They need to be able to model all the controllers, pitch controller, RPM controllers, yaw controllers. So lots of work need to be done. Obviously, we cannot do it all. So we depend on other solvers that could do some of the work. Our work is primarily focusing on the aeroelastic behavior of the rotor. So what we plan on doing it, or we have done some in part, is to start with an open source software called OpenFast, developed at the National Renewable Energy Lab. If you just go to nrel.gov and search for OpenFast, you will find it as in the open source. It's in the GitHub. You could find it also. It's got models for modeling the towers, for modeling the blades, for modeling the gears, for modeling the controllers. It's a wave dynamics, you name it. But the aerodynamics is very, very simplified for obvious reasons. They want a fast solver. So it uses a blade element momentum theory with a dynamic inflow model. And then it uses a quasi-steady aerodynamics. That means the 2D CL versus alpha curve, CD versus alpha, and so forth to model the blade itself. So what we are trying to model is to improve this aerodyne with our CFD solver. Then we also want to replace the elastodynamics for the rotor elasticity with our own elasticity solver, so that at least at the blade level, elasticity is fed back into the aerodynamic solver. Then we take the hub loads, that means at the center of the rotor disc, then we pass it to the OpenFast. Then OpenFast, at the center of the hub, that load gets transmitted to the tower, to the foundation, and then the rest of the systems are handled by OpenFast. So this is how we are approaching this particular problem. So OpenFast, as I mentioned to you, is a time-defined aerodynamic module. It uses classical blade element momentum theory for inflow model. It uses 2D strip theory. Blade is divided into small segments. And each segment, they find the effective angle of attack. Then they compute the lift and drag, then convert that into forward directed force, which is a propulsive force, which is what is driving the rotor, producing the torque and also the power. So our objective is to develop a very, very efficient CFD-based solver for modeling aeroelastic behavior of large offshore wind turbines. We do want to explore innovative wind turbine design concepts, which was done also in Aura's thesis. But because of the time limitation, I'm just referring you to her dissertation. And so we are just going to look at a classical wind turbine, a very large scale 5 megawatt wind turbine that we are going to be looking at in this particular talk. What type of CFD solver we are using? Previously, Riso, at Denmark gave a really nice presentation. They have a 3D CFD solver. Other people around the world, and including the United States, have 3-dimensional Navier-Stokes solvers for wind turbines, but they take a lot of memory and time, computer time, because they model the whole flow field, including the blade, the wake, and everything else. Okay. We decided to simplify by modeling the aerodynamics using 3D Navier-Stokes solver, fully unsteady 3-dimensional Navier-Stokes solver over a single blade. But once the loads are generated on the load, we convert them into equivalent vortex strength using what we call the using the Kutta-Joukowski theorem, which says rho times velocity times the circulation equal to load. So we compute the circulation of the filaments, not only the trailing filaments such as these, but also shed filaments which are running from root to tip, just in case the loading is changing from azimuth to azimuth, okay, as the blade is rotating. Okay. So that wake structure is kept as Lagrangian elements. So we are not modeling the wake itself. So we are modeling it as a freely floating filaments of wake, and they influence what's happening on the current blade and also the neighboring blades using something called the Biot-Savart law. Because we are reducing the computer time just to a single rotor, instead of taking a tens of millions of grid points for the whole rotor, we are talking about maybe a 1 million points or a 500,000 points, or if you want to be really cheap, 250,000 points. Okay. That means this part of it can be done, including the wake and the Biot-Savart law, on a desktop computer with the four nodes or 8 nodes or 8 core processors in about 2 to 4 hours per full revolution. Obviously, you need 5 to 10 revolutions to get the air loads. Then we couple that into an elastic solver. So we have our own grid generator. We can handle pretty much any rotor people give us. We have our own Navier-Stokes solver. It efficiently produces the information. It has a very, very fine grid in the boundary layer so that we are able to resolve the boundary layer fairly accurately. We typically run it for 10 revolutions. It takes about, I would say, about 6 to 8 hours on a desktop computer. If you have a faster cloud-based computer, depending on the number of cores that you have, you can bring it down to 1 to 2 hours per run, including 10 revolutions. After we get the lift and drag and pitching moment all along the rotor from root to tip, then we want to couple it to the aeroelastic solver. Aeroelastic solver is a separate solver. So it provides us information at every azimuth location, every 3 degree in this case, from root to tip, how much is the blade deforming in the X direction, Y direction, Z direction because of bending. So these are linear deformations. How much is this deforming in the torsional, rotational direction, about the pitch axis of the blade, about the rotating axis, and about the yaw axis. So it gives the 3 linear motion deformation, 3 angular deformation. So our program reads this information. This is a text file. It could come from any analysis, come from ANSYS or SolidWorks, or it could come from CATIA, it could come from OpenFast. We can use a small Python-based script to convert it into the format our program needs. Then we read the text data, and our program dynamically deforms this blade based on this bending, torsion. It basically bends and twists the rotor. Our grid that I showed you earlier on bends and deforms. So the whole thing happens in every time step in a very efficient fashion. We want to be able to compute our own solver. So we do our elastic solver offline. That means when the CFD is done, we take the lift and pitching moment, which is shown as L and M per unit length per meter of span, feed this into the solver. This is the classical Euler-Bernoulli equation solver. Normally, the pitching motion, which is the theta, twist of the blade, is coupled to the bending, which is W, bending deformation, by the offset Y theta between the mass center and the elastic axis. But this NRAL 5 megawatt rotor there's no offset, so this went away. We could keep this term, then we'll have a coupled system of equations. If this terms goes away, and if you're only in steady state equation, then each equation can be solved independently. So we use a standard 4th order central difference scheme. By the way, E and I are the elastic properties and the inertia properties of the cross section that is given for the rotor. Same way, G and J are the area moment of inertia, and then the G, is the elastic properties of the rotor, need to be known. Then we can solve this to compute the W and theta, and then we can convert it into this particular file. All this happens fairly quickly because, as you could see, this is a very, very simple solver. We could even couple it every time step. Aeroelastically, we could model a stall flutter. All we have to do is turn on this time derivative. And if there's a structural damping, then we need to turn on the 1st order derivative. If there's a mass offset, then we have to turn on this Y theta term also. Then we can solve this very, very efficiently. We need boundary conditions. At the root, we set the cantilever beam type of a condition, no deformation, and derivative of the deformation is set to 0. At the tip, the 2nd derivative and the 3rd derivative are set to 0. So these are easily implemented in this particular problem for the W. There are similar boundary conditions for theta. There's no torque at the tip. There's no deformation at the root. So we use those as the boundary conditions. Then we solve the problem. So the whole thing happens this way. We run our hybrid CFD solver for 10 revolutions. Takes about 6 to 8 hours on my desktop, 1 to 2 hours on a cloud-based computer. Take the loads, feed it into our in-house CSD solver, or you could feed this into ANSYS or anything else, OpenPass. Then you get the deformation, create this blade motion file, then start my CFD solver, our CFD solver. So this goes round and round, 4 to 5 coupling iterations, everything is converged. We normally monitor a non-dimensional coefficient called the power coefficient to see whether it is converged. By the way, the blade mass and sectional properties should be known to us. This should be supplied by the blade manufacturer or from the blade designer. So the rotor we are looking at is a 5 megawatt rotor designed by NRAL. It's got 3 blades. The radius is almost 64 meters from root to tip. And it's designed for a wind speed of 11.4 meter per second. It's spin at 12.1 RPM. Then it's supposed to produce a 5 megawatts of power. So this in geometry's information is available. For example, they give us at various radial locations, what is a twist distribution of the blade. They talk about what is a chord. What is the spacing? The spacing is simply the distance between the 2.86 and 5.60 is a spacing, for example. They give us a chord. They give us the aerofoil coordinates, aerofoil profile. So I have all the information. Aura has all the information to generate the outer mold of the geometry. Then we take it and put it into our built-in grid generator. Then we put it into our built-in solver. Then we get going. So the mass and structural properties are also known. I'm just showing you some snapshots of these things. If you go to nral.gov and then search for NRAL 5 megawatt turbine, you'll find all the information. Or you could go to Aura's PhD dissertation, that PDF file, that PDF link. You can email me if you wish, and we'll be very happy to share all this information with you. So what we do is within our CFD solver, we compute the lift, not normal to the total velocity direction, but in the plane of rotation. So it's called a normal force coefficient. And we take the propulsive force coefficient, the forward direction. So if you have this force, if you multiply by this forward velocity, then you get the power. Then you get the power integrated from root to tip, you get the total power. Pretty much it's as easy as that. But sometimes we also monitor non-dimensional quantities. Just as in air, in the wing, we do a CL and CD. We non-dimensionalize normalized coefficient and the normalized tangential force coefficient. We know that the tip region produces a lot of loads because the total velocity is very, very high. So we normalize, multiply the Cn by r, lowercase r, or uppercase r, which is the blade radius squared. Same way, the tangential force coefficient is multiplied by r over r cubed, because it's not only the proportional to the dynamic pressure, but also this extra velocity that we are seeing in here. So we also monitor radial distribution of the non-dimensional coefficients. So let's look at the power coefficient. Basically, the computed power from our analysis divided by the energy that is available in the oncoming airstream. Density times velocity times the disk area is the mass flow rate. 1/2 times the velocity squared is the energy per unit mass. So this is the available energy. This is the extracted energy. The maximum power, according to BETS, is limited to 66%. Most modern turbines will reach about 50% or so. Okay. We compared our prediction, which is shown here in black. This is initially the rigid rotor with Aerodyne, which is within the open phase. We found at high wind speeds, the open phase Aerodyne was producing less power. So we looked at the output of Aerodyne. We noticed that at high wind speeds, the blade was stalling. Notice that the wind is coming from bottom to top. Therefore, the angle of attack of the blade that is showed in this picture is alpha is increasing because the wind is increasing. So the blade was stalling. So Aerodyne said, I'm stalling, I can't produce the power. But in reality, you have a radial flow because of the centrifugal force, so-called centrifugal pumping, that improves the performance. So we get more power than what Aerodyne is giving. This has been observed also by other researchers. So we can capture the stall delay in our program without any extra corrections. We don't need to make any kind of a correction like a tip losses or induction losses, anything else. Everything is coming from first principles. Therefore, it's a very efficient way of calculating it. So let's go to the coupling. We start with a rigid rotor of CP. Then after one iteration, second iteration, this is coupling with the elastic solver, our solver. By the time you reach the fifth iteration, you start changing in the third significant digit. Again, at 10 meters per second, you start with 0.455, 453, you drop to 448. We notice that it's within 1%, 0.5%. So our solver quickly converges. So each time, each iteration is on a desktop computer is 6 to 8 hours. If you want to push it for more iterations, 10 hours. This is 50 hours. In 2 days, we can get it on a single desktop. But if you have a multi-core, a distributed computer, we have an open MPI, then we are talking about this entire simulation, aeroelastic simulation, in a matter of hours. So you not only get the aerodynamic loads and power, but you also get the elastic loads, out-of-plane deflections, torsional deflections, various wind speeds, structural loads, bending moments, shear forces, you name it, we get out of our solver. Then we take the hub load, then that can be fed into OpenFast, because an OpenFast now does not use its own hub loads. It would use the hub loads that we prescribe, whether it's a steady load or an unsteady load, and then look at the tower dynamics, the base dynamics, and so forth. So this is the philosophy that we are currently following. So this is the NRAL aeroelastic analysis. It's a very busy chart, but I have shown our rigid GT hybrid, which is a black curve. Then our rigid Aerodyne, which is the blue curve. Then elastic CFD, our solver, which is the black cross. Elastic OpenFast. They're all within, I would say, 1 or 2% over a broad range of wind speeds. But it's very satisfying that physics-based model like ours are able to capture it from very accurately, these phenomena, not only at low wind speeds, but also at high wind speeds where stall occurs. As I mentioned to you, you could also monitor the radial distribution of the normal forces, tangential forces, look at the effect of elastic iterations on the loads. You could look at a rotor A versus rotor B to see how can I improve the power production. Lots of extra data may be obtained at different wind speeds. As I mentioned to you, you don't need to use our solver. You could use ANSYS. ANSYS uses a rectangular cross-section rather than our beam theory. It's a more sophisticated analysis. So it gives a slightly different answer, but it is again within, I would say, 0.3 meters near the tip. Our rotor radius is 60 meters. So 0.3 meters by 60 meters is very, very small. I would say about 0.5%. Okay. So we can capture the differences within 0.5%. So in summary, we have developed an aerodynamic analysis for very large scale, aeroelastic analysis for very large scale wind turbines. They can be efficiently analyzed it. And they are in good agreement with NRAL data. We have other models we are looking at, such as Timoshenko beam theory model, but we have also looked at other solvers, other rotors, lots of good work going on. Dr. Oralak in Thailand is continuing to work in this area. We hope to do more work. In the interest of time, I'm going to yield the floor at this point. and kind of open up the floor for questions. I will stop sharing so that you could see my face and answer any questions that you have. Thank you.
Thank you, Dr. Lakshmi Shankar, for the wonderful presentation. So now the stage is open for questions. So having any questions, you can ask.
I have a question.
Yes, sir.
Thank you very much for a very nice and interesting presentation. Nice with this CFD structural coupling, very important.
Yes,
I wondered, so yeah, I could see that the deflections, they were rising even above 12 and 14 meters per second. Did you run the turbine as a stall regulated turbine, or is it a pitch regulated turbine? Because normally you would see the biggest loads just around rated power.
Yes. Yes, it could be done either way. This particular rotor was a pitch regulated turbine, and also designed for RPM regulated turbine. That's how they designed it. But for all our calculations I have shown here, we ran it at a fixed pitch and fixed RPM just to get the comparison. Yes. But if there's an interest, we could run it at other pitch and other.
Yeah. Okay.
I know VSO is doing a lot of great CFD work. So we have done in the past some other rotors that they have looked at, and we are following your work and getting a lot of inspiration out of their work. Yeah.
Yes, nice.
Thanks.
Thanks.
Any other questions? Okay. Dr. Lakshmi Shankar, I assume that there are no questions from the speakers.
Thank you.
And thanks for answering the questions. And okay, once again, thank you for being part in our webinar, and hope you will associate with our further events as well. Thank you so much. So moving towards the next presentation by Dr. Vladimir Frolov from Samara National Research University, Russia, and presenting the talk on optimum fuselage width to achieve maximum lifting properties of wing body combination. So Dr. Frolov. Yes, please share the screen.
My presentation?
No, sir. It's not visible now. Yes.
Yes.
So, yes, please make it a full screen. Yes, sir, that's perfect. Go ahead.
Okay. Good afternoon. Let me introduce myself. My name is Vladimir Frolov. I am associate professor at Aircraft Design and Construction Department of Samara National Research University. The Samara city is located approximately on 1,000 kilometers from Moscow on the river Volga. I'm going to talk about optimal fuselage with to achieve maximum lifting properties of wing body combination. I will talk for about 20 minutes. I will be happy to answer questions at the end of my presentation. Outline. My lecture contains the following questions. Introduction, review of method of calculation lift wing body combination, mathematical model of wing body interference, review of calculation results, results of optimization problem for lift curve, slab for mid-wing body monoplan configuration, and then to conclude. So, introduction. An analysis of a lift for the wing-body combinations nowadays still plays an important role in theoretical research of an aerodynamic and preliminary design of modern aircraft. Goals of the picture of the lecture show possibilities approximate calculation method for calculating the lift curve slab of the wing fuselage combination. To emphasize the presence of the maximum value of the lift curve slab of the wing fuselage combination. Emphasize that the maximum value is greater than the same value for an isolated wing. Show solutions of optimization for the elliptical cross section fuselage wing combination. As you can see from the table of the slide, number 4, you can see total number of Russian and foreign scientists approximately are same. The main idea of paper, you can design the combination of the wing fuselage so that maximum value of lift curve slab of this combination will be greater than the same value for an isolated wing. That is, I want to see you Formula 1. In this slide, you can see geometric characteristic of the fuselage wing combination. An important parameter is the ratio of the fuselage diameter to the wingspan. The effect of exceeding the lift properties of the fuselage wing combination over the original wing was noted by a number of researchers. Figure 2, the date from Cornell's book indicates the presence of the maximum lift properties of the fuselage wing combination. In this value, greater 1. In this slide, you can see mathematical model of wing-body interference. Mathematical model consists discrete vortex method for wing and potential flow for fuselage. The potential flow model is based on a numerical analytical method. This method includes conformal mapping for elliptical section and Cornell method for another form section fuselage. In this slide, you can see realization numerical analytical methods for a potential flow around an ellipse and two vortices, right vortex and the left vortex, cross section of fuselage. The problem as a whole is reduced to solving a system of linear algebraic equations. In this system, left part discrete vortex method for wing, and right part panel method for fuselage, or analytical method for fuselage, use conformal mapping. Solving the problem when the wing has an angle of installation relative to the fuselage, but fuselage has an angle of attack, and the wing has an angle of attack same. And case when angle of attack for fuselage and angle of attack wing equal is same. We have two formulas, 6 and 7. Several subsequent slides show the agreement of results according to the proposed mathematical model with the calculations of other authors. You can see slope curve slope for combination with body, interference coefficient, and right plot you can see distribution curve curve for along wing. Distribution lift curve slopes along the span of the rectangular wing for case mid-wing body combination. In this slide, you can see combination with swept wing. In this slide, you can see triangular wing combination. In this slide, you can see solution problem delta zero problem for combination fuselage and rectangular wing and fuselage plus swept wing. Present method and Vernier from Tsagi Russia method. In this slide, you can see effect compressibility for lift for derivative of the lift coefficient with respect to the angle of attack of the fuselage wing combination increasing. Number Mach increase, and this value increasing also. In this slide, you can see simulation optimization problem for lift curve slab of mid-body monoplan configuration. The optimization problem is formulated as a non-linear programming problem as follows. Formula 8, where x is a vector of the project parameters connected with geometrical characteristic of the wing body configuration for formulas. The problem 8.9 is a problem of unconditional optimization. Unconditional optimization for which there are relative diameter and a parameter depth. In this slide, you can see simple solution to the optimization problem, formula 10, where K W plus body total coefficient of interference, taken into account the influence of the fuselage on the wing and the additional lift force arising on the fuselage due to the presence of the wing. This value is a lift curve slab of the alone wing, a wing composed of two consoles. This value is area of the isolated wing, and C is the area of the original wing with under fuselage part. Formulas for interference coefficients for fuselage wing combination of the mid-lap scheme. The total interference coefficient KW plus body is equal to the sum of two interference coefficients. KW from body is the interference coefficient taken into account the influence of the fuselage of the wing, and K body from wing is the interference coefficient that takes into account the additional lift force arising on the fuselage due to the presence of the wing. formula 11. Jamming interference coefficients were first obtained by Kirby and Robinson using the strip method and are determined by the following formulas. Well, where is D is a ratio of the fuselage diameter to the wingspan. Ratio of the arrays to isolated and original rectangular wings can be represented by the formula, where C is wing chord. Substitution of the total interference coefficient KB plus B and air ration into the formula, then this formula. We use formula Jones 15. In this slide, you can see the depends lift curve slab of the rectangular wings versus using aspect ratio. Discrete vortex method and red line Jones formula. You can see a good agreement of the calculation results. We can write formula, use Jones formula for combination wing plus body in this formula 18. To analyze the ratio of the lift curve slab of the wing of the fuselage wing combination and lift curve slab of the original wing, we write the ratio of these derivatives, where value is the lift curve slab of the original wing with the under fuselage part, which can also calculate using the Jones formula 15. For incompressible flow and aspect ratio of the original wing, you can write 20 formula. Where aspect ratio, wing aspect ratio for original wing, relation between the aspect ratio of the rectangular isolated and original wings is expected by the formula 21. The substitution of formulas 18 and 20 into formula 19 after simple transformations allows us to write the formula 22. From formula 22 can be seen that the ratio of the lift characteristic equal 1 in the absence of the fuselage and 0 in the absence of the wing. This plot is the ratio of the lift curve slab of the body wing combination and the original wings versus the relative fuselage diameter. You can see maximum from figure 23. It follows that there is an optimal relative diameter of the fuselage, which ensures that the lift curve slab of the fuselage wing combination exceeds the same characteristic of the original wing. Finding to optimal fuselage diameter. To determine the optimal relative fuselage diameter, we write the derivative with respect to the relative fuselage diameter of the function described by formula 22 and weight it to 0. Then we get formula 23. From formula 23, you can write equation 24, where aspect ratio of the original wing included in equation 24 can be considered as a parameter. Numerical solution of the equation 24 by a golden section method dependent on the aspect ratio is shown in figure 24. Optimal relative diameter wing aspect ratio. Here for comparison, the results of the calculation by the numerical method are general, taken into account the transverse flow of the circular cylinder fuselage in the discrete vortex method for an isolated wing. In figure 24 follows firstly good agreement between the results of calculation according to this approximate method and the numerical method for range of the wing aspect ratio. 3.9, which allows a simple method to be applied in engineering calculation. Secondly, the optimal relative fuselage diameter in the body wing combination can research 20% and more of the span of the rectangular wing with the aspect ratio more than 7. And optimal relative fuselage diameter increasing with increasing wing aspect ratio. In this slide, you can see relative lift curve Lattice of wing body combination of elliptical cross-section fuselage. A, wing aspect ratio is variable from 6 to 12. But the compression ratio of ellipse is constant, equal to. Second, figure B, comparison for two wings, aspect ratio and compression ratio of the ellipse is variable. Wing aspect ratio and compression ratio of ellipse is variable. However, you can see in this and in this picture maximum. Result of the optimization problem for lift curve slab for with wing body monoplan configuration. In this, you can see lift curve slope maximum. In this wing aspect ratio. For wing fuselage combination of an elliptical cross-section, the optimal relative width of the fuselage increasing with increase in compression ratio of the ellipse. So, conclusion. The report gave a brief overview of the works on the wing body interference. A good agreement of the proposed model with the results of others are shown. The present results of the optimization problem for the wing body combination allowed to select the optimal geometrical characteristic for combination to maximum the value of the lift curve slabs of the wing body combination. It was relative that maximums of the lift curve slabs for the optimal wing combination with elliptical cross-section body had a sufficiently large relative width of the body, more than 30% of the wingspan. The lift properties of the wing fuselage combination may be greater than the lift properties of the original wing with the sub-fuselage part. Thank you for your attention.
Okay, thank you for the wonderful presentation, Dr. Frolov. So now you can stop sharing the screen. So now the stage is open for questions. Having any questions from the speakers, or you can ask to Dr. Frolov.
Thank you for your attention.
Yes. Dr. Frolov, at the top of the screen, you can find stop sharing.
Mm-hmm.
Yes, thank you. So having any questions?
Just want to tell it's a very nice presentation, Professor Prado. I enjoyed listening to it. As you know, at the MIT, they have a program called AVL, Athena Vortex Lattice program, which can do wing body calculations, even a complete airplane calculations. It'll be very interesting for your students, perhaps, to compare your predictions with what MIT software AVL can do. So that'll be something interesting for future work. Very nice work. Thank you.
Thank you. Thank you. I understood you. Thank you for remarks.
Okay. Once again, thank you for being part in our webinar, Dr. Frolov, and hope you will associate with our further events as well. Thank you so much. And moving towards the next presentation will be a video by Widong Zhu from the University of Maryland, USA. And his title of presentation is Vibration-Based Structural Damage Detection. Please give me a moment so that I can share the screen.
Hello, thank you for inviting me to give a keynote talk at the conference. Today I want to talk about vibration-based structure damage detection. So I will first talk about model-based damage detection method. So in this case, mainly we want to address accurate modeling of structure, and that include fillet modeling, bolted joint modeling. We have often done the work on interference pin modeling, riveted joint modeling, and welded joint modeling. And those will not be covered in this talk. And some of the work you can see in the paper and that we have recently published. We'll also talk about the robust algorithm that can detect a location extent of damage using change of natural frequency. And in this case, we are dealing with severely underdetermined system, which means the number of stiffness parameters we want to identify greatly exceed the number of measurements. And then I will often talk about non-model based damage detection method and how we use curvature of beam or plate to detect damage. And we'll talk about the continuous scanning laser vibrometer to measure the motion. And we also will talk about the imaging-based tracking, continuous scanning laser vibrometer for rotating structural vibration measurement, and the 3D continuous scanning measurement, ground logging test. And we'll also talk a little bit about the using digital imaging correlation to detect damage. So first talk about the model-based damage detection method. Traditional methods such as ultrasonic testing have limited depth of penetration, and you have to inspect the every point of the structure to detect damage. You cannot detect the damage at the joint or boundary of the structure. So our vibration-based method, we want to develop a global vibration-based method and develop finite element model so that we can model structure with L-shaped beam, bolted joint, and both other joint. And then we'll develop iterative algorithm that can detect the location extent of damage from change of natural frequency of the system. So we want to use a minimum number of measurement. It's difficult to measure the mode shift, so we only want to measure the natural frequency. And we'll apply this to a variety of structures such as space frame structure, lightning mast, and pipeline. So the challenge is the forward problem. You have to develop accurate finite element model of structure, which has fillet modeling and bolted joint modeling. And then we'll develop an inverse problem for the system. So we have to capture the physics for the finite element model so that you can model a large number of natural frequency and with minimal error. And the inverse problem, we want the system to converge to a local minimum of the system So we are dealing with underdetermined system with a large number of unknown than the number of measurement. So this example of a beam, you have some damage here. Okay, for a mode ship, you cannot see much change. Okay, and later we will see where you look at the curvature in order to identify the damage. And the natural frequency, you can see the global vibration property. You can see 4% difference in natural frequency. For modeling error within 2%, and we can identify the damage of the system, the location and extent of damage. So this is the basic idea. We divided the system into n segments. So we have n stiffness parameter. Then we measure the m natural frequency, where m is much smaller than n, so that we formulate the optimization problem. We want to minimize the error between measured and calculated natural frequency, and from which we can identify all the stiffness parameter. So once we identify the stiffness parameter, we know where the damage is and how much is the damage. In a space frame structure, and often occur, and local method cannot identify the damage. So we build a space frame structure in the lab with the L-shaped beam and a bolted connection. So it will be challenged how to model the stiffness of bolted connection. If you say they are completely welded together, you can cause 50% error in modeling. And also L-shaped, the L-shaped beam have a fillet, and how you model the fillet can also play an important role. If you don't model the fillet, you can significantly reduce natural frequency, and you can also cause mode shift, can also change significantly. So Mach number can only be, between theory and experiment, can be only 20%. The ideal case will be close to 100%. So here our modeling approach, we a simple model for the fillet. We use a shear plate element for the flange here, and use beam element in the middle, and then use rigid link to link them together. So the traditional model in the literature, this is the model of bridge for the fillet, and that can only model the in-plane effect. You cannot model the out-of-plane effect. And it can all cause large error, 7% error. If you use solid element, you will take a large number of elements, and you have also shape function inconsistency between the plate shear element here and the solid element there. And similarly, you use a step beam element, it often have a large degree of freedom. So this is our simple model. We have plate shear element and the beam element and the rigid link that connect them. So you can model not only the in-plane vibration, you can also model the out-of-plane vibration. So this is first we try to model the in-plane vibration. So we take the fillet out. We model this as a plane strain problem with unit length. And then we look at analytical model, this due to symmetry of this fillet, we can assume the displacement here is 0, and then look this as a curved beam. So we can look at the curved beam here, and we can look at the strain energy due to internal force, bending moment, shear force, and axial force. And then you look Castigliano theorem, you can do the partial derivative, effect to the load or internal force, you can calculate the displacement there. So you can replace the integral by the summation, and then you can do the free body diagram to calculate the internal force. So you can then calculate the displacement at the cross section. Here we can see the bending moment and the axial, the shear force play an important role there. So this is the element model. This is the shear plate element, and this is the beam element. You have rigid link that link them. And you can use from element model, we can also look at the stiffness matrix of the system, and you can look at compare the analytical model with the animal model. We can see the relation between this coefficient Cs and the length and the thickness of the element. So you can, from this model, you can get good accuracy. And we can also model the autoplane effect, that include the beam here, that include the bending and the torsion. So for the bending, this is a torsional stiffness factor. And the bending, we need to look at the bending moment, which is the area moment inertia of the cross section. And we can also look at the equivalent modeling between animal model and the analytical model. This is the animal model. And for torsion, we also look at the equivalent modeling, look at the torsional equator, torsional deformation. With that, we can get a very accurate result, for this beam animal can model both 28 modes with error less than 2% and a Mach number over 95%. And this is the mode shift from our simple model. And you can deal with the other cross section with the fillet there, with this box beam. And this is the I-beam with a double fillet. And then we look at the bolted joint. We can use a model updating method, use a bracket, and we try to update the Young's modulus of a bracket, and so that we can find the effective Young's modulus of the bracket. So we can model the bolted connection. In this case, you have to do experiment and compare experiment and the final element result. So this is usually you use a nonlinear model in Optics, okay? But in our case, we can find when the bolts are sufficiently tightened, the bolted connection essentially is linear. So we can use a different impact force. You can see you get the same frequency response function in a large frequency range. You can also do a reciprocity test by exchanging the location, excitation, and the measurement. And we also see the FRF, measured FRF, are basically the same in a wide frequency range. So what we want to do, we want to find the effect contact area of the two clamp components. And we see the contact area, the natural frequency are more sensitive to contact area, and it will be less sensitive to shear modulus, and it will be least sensitive to Young's modulus. So we can look at the two clamp component and apply some force here. The pressure between clamp components, we see it's essentially behave linearly, and it goes to 0 here, which means this is the contact area radius. So it's independent the friction force between the two clamp component, whether it's small or large. And you can also look at different material for clamp component, and the pressure always change linearly. And also they goes to 0 at the same point. Using this approach, we can use 3D model, 2D model, and even 1D model. So you see the pressure force is changing linearly, and this goes to 0 here, and this is essentially clamp area radius. Now we can find analytical expression to calculate clamp area radius. So this we can get very accurate result about 1.1% error compared to the 3D model and the 2D model. And so for the clamp component, we can calculate the clamp area radius, and we can use logic cone to calculate the cylinder here, and then we can find the stiffness of the cylinder. So with that, we use some both are loosened, some are tightened, and so if you lose some bolt, you can get the error about 4%. And for the loosened case, and you have model and experiment result, the error less than 2%. And this one you have to do experiment. You will update the shear modulus. And if all the bolts are tightened, model and experiment result, the error is also within 2%. And in that case, we don't need to do experiment. We can do predictive modeling. So with that, go back to this space frame structure. We can model 30 modes with error less than 2%. And this is the mode shift from our modeling method. And we also did a lightly masked model of lightly masked and pipeline, the joint for the pipeline. And then we can use the inverse problem to identify all the different parameters of the system. Here you can use both natural frequency and motion, but in reality, we only want to measure the natural frequency. So this is our new method called Lunar market method. We can estimate all the different parameters very accurately. So we can look at this case here. If we lose some bolt here, 2 bolts here, and you see this member have almost 100% stiffness reduction. So simulation and experiment result give you both very accurate result. And we measure 10 to 15 natural frequency, and we can identify all the 39 stiffness parameters of the system. So this one, we lose some of the bolt at 4 bolt here, 4 bolt below at the joint 9. And then we can also estimate the stiffness parameter of those loosened bolt, which are loosened to hand tight. Similarly, if you have some damage in the boundary, we can also estimate that. So we can often identify the loosening of the joint. And lightly masked, we also identify the damage. If this lightly mask is healthy, we make some damage to the mask with some reduced stiffness. So we can identify all the stiffness parameter of the system. In the pipeline, similarly, if you lose the pipeline, you can also see the pipeline is healthy, but the joint here is loose. So now I will talk about some non-model based damage detection method. We look at the beam with the embedded crack there, and we want to look at the mode shift and the curvature of the mode shift. So when you take the curvature, you need to differentiate this, the mode shift, which can cause noise. So if we take for a difference method and take some point away from the center point, okay, let's say an end point away from the center point. In that case, you can significantly reduce the differentiation noise. So m equal to 15, you can get very good result. The idea is that we don't need the baseline information. We measure the curvature of the beam, and then we look at for the baseline information, we do curve fitting. If your order of the polynomial is not very high, you didn't capture the detail here. So you capture the global trend of the motion. And then you subtract one motion from the other, and you can amplify the anomaly caused by the damage. So in that case, you look at one is the measure the curvature, the other one is the curvature from polynomial fit. Okay, and that you can amplify the local change due to damage. So from here, if you can look at the 3D printed beam, and you use a speaker to excite that, and then you use the third mode, you can see we can identify the 2 ends of the crack. And you can apply this also to a plate. This is you have some cut there, and you can also use a 2-dimensional polynomial curve fit, and you can look at different curvature, maximum curvature, minimum curvature, Gaussian, and the mean curvature, and you can get a similar result. So this is our make a cut here on the back side. Okay, we use a speaker to excite the plate, and then we can detect the damage here. Now we also use a continuous scanning laser vibrometer to get the dense measurement of the motion. So this is basically an illustration of continuous scanning laser vibrometer, and this is the system we have developed in-house. Okay, this beam you have a cut on the back side. Okay, and you can use a laser to continuously scan over the beam to get very dense mode shift measurement or operation diffraction shift measurement. And we can excite the beam at different frequency. Okay, mode shift or ODS, you don't see the damage, but if you take the curvature, you can, and then use the damage index we talk about. You look at the polynomial fit and subtract that from the measure the curvature, it can amplify the anomaly due to the damage. And then you can introduce different cut, and some cut are really small. And we excite this, use sinusoidal excitation at different frequency, and then scan the beam, and you can measure the operational deflection shape. And that is the ODS. Now, if you look at the curvature of ODS, you can see, there are some bigger change. Okay, if you subtract from the baseline information from polynomial fit, and we can very amplify the effect due to the damage. And if you can, look at this CDI, curvature damage index, and average the CDI at different frequency, you can even more clearly see the damage. And then you can also do a plate. You can scan the plate like this in a zigzag fashion, scan horizontally or vertically. And this is our composite plate with some delamination in the plate that we can scan that. If you use we use speaker to excite this also. If you use the second mode, you can see the damage here. If you use the fourth mode, you can see damage there. Now, if you combine the two results, you can really see the damage here. This is, and this is the delamination from the C scan, and the result match quite well with our vibration-based method. So, we have also recently done rotating structural vibration measurement. So this is the rotating blade, and you can put a mark there. And at that time, and right now we don't need a mark. We can just look at the edge of the blade, and we can have a laser that rotates with the blade at the same time scan over the blade. So we use a fan to excite the this wind turbine blade, and then give some excitation, and we use this laser to rotate at the same speed with the fan blade, and at the same time scan over the blade. So that is the measurement over one line, and at different speed, different rotation speed. And this is the full field measurement over the entire blade. And we also have done continuous scanning laser vibrometer. We have 3 lasers that can focus at one point. At the same time, we'll scan over the structure. So this is our system that has been recently developed. And this is the some experiment that we have done. Here is the in-plane vibration of a plate. Usually it's very hard to measure in-plane vibration of the plate. So this is our measurement. And you can see with the continuous scanning vibration measurement, you can get very smooth mode shift measurement. Now we'll talk about long-loving test. This was organized by Society of Experimental Mechanics, and the 5 organizations in the world did the test, and we're the only group that detected both damage. And there was some 2 delamination in the plate. One is the 15 millimeter by 15 millimeter, and the one is the 5 millimeter by 5 millimeter. And we detect both damage, and the other group did not detect any damage. So we separate the plate into 2 parts. In the top bottom part, we use a speaker to excite that. And also we don't need to have the healthy plate. They gave you 2 plates, one damaged, one healthy. So we only need the damaged plate. And we can excite the plate at different frequency. Okay, and that is and this is the top area you scan at different frequency. Okay, and at this 2 frequency, which is shown here, that you can detect the damage there. And the scan area 2, you can also see in this at this 2 frequency, we can excite the damage. Okay, and if you combine the result at different frequency, for top area we identify the location here. For the bottom area, we identify delamination there. So this is our identify the damage, and the solid line is the prescribed damage. So they match quite well. And using a similar method, we also use digital imaging correlation to identify the damage. So this is the membrane, circular membrane, and we make some cut here. And this is the rectangular membrane, we'll also make some cut. And then we use digital imaging correlation to estimate the mode shift, or ODS. and then use our damage detection method, we can identify the damage. So this is basically the cut that has been introduced, and those are the damage that has been identified. So in conclusion, we have developed a new method to model structure with a fillet, boulder joint, and an interference pin riveted joint and a welded joint. And we develop a robust iterative algorithm to detect the location extent of damage, and it can be used to detect damage in boulder joint. And we develop a new non-model based method that can identify local damage of structure without using baseline information. And our experiment result validate a theoretical prediction. So we have some funding that support our research. Recently, we got funding to purchase digital imaging correlation system, and we also get some NSF funding to do damage detection, and as well as purchasing 3D scanning laser vibrometer. So here are some of my graduate students, most are PhD students, who have to contribute to the work. And here my collaborator on the digital imaging correlation work. Thank you very much.
Yes, and that was a wonderful presentation by Dr. Widong Hu. Currently, he's not available, and I can share the email ID of Dr. Hu in the chat box. So if any questions, you can directly drop in the chat box. Okay, and yes, Dr. Lakshmi. So now we are wrapping up with the meeting. Once again, I thank you all for making this webinar a huge success and hoping that our association continues for further events as well. So if you have any queries, please write back to your program manager, Stephen, and he's get back to you with the further information. So now we are closing the session now. Thank you, everyone. Thank you so much.
Thank you. You did a great job.
Thank you so much, sir.